Good afternoon, everybody, and welcome to day 2 of track 2 for the Hack in the Box live stream for lockdown number 2. Our first speakers of today, first talk of the day, I should say, are by Himanshu Sharma and Aman Sachdev with swapping aspirin formulas with MDMA while red teaming a $1 billion company. It's not in the slide. Guys, floor is yours. Take it away.
All right. Thanks a lot, Cooper.
Yes.
Hi, everybody.
Hey, guys. We can't see you today, but we hope to get a feedback from you guys.
Yes. So, of course, it's a different experience this time to be presenting to my own PPT. So, I think we should start. So, swapping aspirin formulas with MDMA while red teaming a $1 billion pharmaceutical. That's the suspense over there that was missing. First of all, who am I? I'm a hacker by profession, around 7-8 years of experience. I'm a developer at heart. I started with development in my early days, school times. And I am right now a red team expert at buzzbounty.com, which Himanshu and I have founded. I am specializing in web application exploitation, social engineering, and all of that part. Any technical kind of stuff that happens where the team gets stuck and things like that. That's where I hop in. As you can see, I talk security, work security, and special needs security. So that's me, Aman. And I'll let Himanshu take over from here. Himanshu, go ahead.
Yeah. Hey, guys. So my name is Himanshu, and basically I've been doing bug bounty since 2009, and I've been into security for like 10 years now, and I've written a couple of books, as you can see. We started, Aman and I started bugsbounty.com 4.5 years ago sometime, and we have been ever since been going around Europe, talking, giving various talks of our experiences and our researches throughout various conferences. Hack in the Box is one of them, and we are glad to be a part of it again. So let's just start the presentation. So this is how our typical red team activity looks like. We are usually approached by the CISOs or the CXOs of the companies, and they basically we act as a watchdog for them. So we are basically requested or asked to check, like, okay, they come to us and say like, oh, all right, we have done our pen tests, we have external vendors, we have internal vendors, we have all the audits complete, we have compliances in place. Can you guys come and actually see if an attacker was to attack us right now, how much damage would he have been able to do? And if there was a real attack happening, can or will my SOC team be able to pick it up? So this is how a typical day in our activity looks like. So this is a story of a pharmaceutical company. The CISO approaches us, and initially we only got the permit for the POC because it's a $1 billion company, and he wanted to see what we can do first. So yeah, so basically our goal initially was set to, can you guys breach or get inside the intranet from the digital perimeter only? This was our initial objective. So keeping that in mind, we guys started. Phase one began from internet to intranet. So initial POC was obviously to find anything and everything which is available outside and use that to get access to inside. So we started. So basically we are like 32 people in our team, and we usually do things in batches. So one of the teams started doing extensive recons. We look at subdomains, we look at acquisitions, we start doing recons, heavy subdomain enumerations, and who is reverse who is. We map the entire web applications, mobile applications which are available online. Then public servers, what are the different cloud services they use? Then what exactly services which are used by internal employees of the organization, if there is an SSO, if not. Moving on to the next part is that the outcome was basically it took a couple of days. The activity went through, and obviously we had a couple of SQLIs leading to remote code executions. We had some IDORs, etc., which will lead to customer information disclosure. We had some issues in the SAP being used by the company. Then we had a couple of misconfigurations as well, and we'll be covering some of them in the talk, which led to RCs. But yeah, see, this was not our objective. We still had to gain access to the internal network, right? So we'll, here's a couple of findings. We basically discovered an SQL injection, which led to the DBA was true. It was MS SQL based, and we got it. So we got access to the internal network through the RC we achieved. And this was another interesting find where we saw that, because since it's Kentico CMS, it actually stores the credentials, SMTP authentication. And as you can see that it says username says no reply, right? So this was another story. We'll cover it up later parts of the talk. Now,
Yeah.
and another one was that we had a couple of SAP misconfigs, as you can see from the screenshot itself. This is a username disclosure vulnerability we found. But now the interesting part comes. This was one of the forgotten installations. So the company actually, went ahead and tried to use MDM's mobile device management across their network. Now they tried a couple of products. AirWatch was one of them. Now what they ended up doing was that they actually had an AirWatch console installed, but they claimed, or according to them, it was not being used by anyone because they tried it, they didn't like it, so they switched to some other vendor. So, we thought, why not? So we tried the default password, which is usually administrator and AirWatch, and we were logged in. So as you can see that we logged in, and to our surprise, we actually had like a few hundred employees still connected, and still the application was installed on their phones, and people were actually using it.
Yeah,
So
even when the client said that this is just a test installation, it won't have any real users. It was just a trial, and even with the trial, they had a couple of hundred employees, so we could actually see what everybody is doing, what is there on their phones, their location. We could install applications, anything and everything that a mobile device management software could do. So this was
the most interesting part was actually that AirWatch allows you to configure your own personal, like a Wi-Fi setting onto the user's phone. So we thought, why not, right? We could have installed a certificate and accepted that proxy and all that, but yeah, we had evil jinx too, and so why not? We just configured, set up a hotspot and then configured the Wi-Fi on the employees, and we started looking around. A couple of people connected back to us, and we were able to fish the credentials of Outlook and all that. So about 10 employees sort of fell for the actual attack, and we had the O365 logins for the same. So this is like everyday vulnerabilities that we discover during a standard pen test.
these things everybody finds, right? Yeah, you, I, when we are doing our standard red team exercises, even a standard infiltration,
BAPT. Yeah.
yeah, APT or infiltration assessment and things like that. These are standard kind of vulnerabilities that everybody finds. But one interesting thing that has been really successful for us carrying out pen tests and red team exercises is leaked credentials. Now, leak credentials, they seem like a very small thing and very obvious thing that it would lead to something. But if used properly, leak credentials could have been giving us access to organizations for a very long time, and has been really productive for us. So the standard approach that we take for leak credentials is, of course, going through deep web links and Telegram bots like Shiverbot. Then obviously there are so many online compilations which collect all of these credentials and whatever data that was leaked during the data breaches. Examples are LeakSource, SourceBase. There are a lot of websites like this which we subscribe to, and of course we have our own reconnaissance tools that have purchased these APIs and integrated all of that, so that the moment we enter our domain, we get the hits on whatever accounts are leaked for employees. But getting leaked credentials is just a very small thing. More importantly is to enumerate where all these credentials will actually work. So that is where identifying the third-party services where employees might have their accounts. So obviously the first thing, obviously, if it's a LinkedIn breach, then of course you try the password on LinkedIn. But a lot of times with breaches like Collection 1, 2, 3, etc., Adobe and all of these leaks, they you do not exactly have a guaranteed a sure shot location where you can try the credentials. And that's why we generally target social media, of course, Facebook, Instagram, LinkedIn. And then, of course, while we are doing the reconnaissance, web reconnaissance and attack surface assessment, at that point, of course, you generally find login panels, internal employee panels, some CMS, some attendance management system, stuff like that. A lot of these things we discover during the recon, especially when the organization is big. So that is what we try these credentials on. Then a very interesting place to try these credentials are dev portals, of course. So GitHub, Slack, Kubernetes, AWS, all of these things where developers are working. The moment you hit an account that is working in these, then you really have a big lottery on your hands, because it gives you so much information, so much insider stuff, credentials, internal IPs, endpoints, everything. So that's there. Of course, you have the email clients like Gmail, O365, and all of these. If you're able to log into them, then it's a good thing. 2FA can be bypassed when you log into Gmail. Of course, we'll come to that later on. But one more thing that you should try is unlikely services. Food delivery, travel, shopping, dating. Yes, we have had cases wherein people use their official accounts to actually register on such services. For example, an HR might register on a travel website for booking the tickets of their employees. So things like these are very helpful. Of course, if you are able to find the personal email addresses of these professional email IDs, work IDs, then that is an even plus, because then you can get into their personal GitHub, their personal accounts, and that would lead out to a lot of things. So again, you can refer to Awesome OSINT. It's a good repo for doing all of this. Now, for us, this gave us the outcome. 2 of the credentials worked and on our business management portal. So as you can see, we had to redact a lot of screenshots, even in further slides, and we were able to log into this. A quick tip is how we discovered this business management portal is during a vhost subdomain enumeration. So another common trick that you might know is you attach localhost in your host header while doing your FUF or div search or whatever. You attach that, and that helps you to discover internal domains, internal IP addresses, internal assets, and things like that. So this is how we got the business management portal. And another a place where we were able to log in, not able to log in, but we knew the credentials are working, is the central employee panel. So this is where the people come in, give out their attendance and all that, anything related to their internal stuff. It comes in to this page. They log into this application. But if you notice, it had 2FA. Now 2FA says OTP is required when accessing the website outside the secured network. So this is where we hit a roadblock. Now at this point, we had a lot of stuff. So we had employee accounts hacked. We had RCs on internal servers due to various misconfigurations. We had partial access to Quark network because of these RCs. And of course, we had tons of customer data with us during the IDORs and web application assessment and all that. And of course, we had access to mobile devices of some employees. Now, the challenge was to get inside the internal network completely. And we had to prove ourselves to get the big project. Because it's $1 billion company, and obviously, we had to make a good business out of it. So we took an extra step. And what we had to do is to gain access to the secure network that this internal employee panel was talking about. Because if we are able to get inside that, it will be a really good thing. So how do we do this? So secure network, we decided to do war driving. So I know this is like, it's only digital perimeter, but we bended the words, and we decided that we'll check the physical, not exactly the physical, but the wireless part of this, and see what we can get while war driving. So we are talking about a 1,000-acre campus of this organization with strict policies. You cannot even a food delivery guy cannot enter the campus. The person has to come outside and take the food. So getting inside, a big issue without a proper ID. And this, you can see, this is me, Himanshu, and a couple of other hackers sitting inside a car parked outside. You can see the bonnet, the dash is lifted up, showing that our car has broken down because it's 3 a.m. at night, and we are sitting over here with our laptops and 9mm 9-meter alpha card antennas, and we decided to basically see what all signals we can get. Of course, with the bigger antenna, we are able to capture signals that are
Radius,
inside.
yes.
Yeah. So what we saw is at the gate, we had Wi-Fi signals. Mostly they were WPA2 enterprise. Some guest networks were also there, but they were DMZ'd, of course. So we decided to park our car, and our next objective was to militarize this DMZ. So we parked our vehicle, and we did some recon while connected to the guest network, and we realized that the switch was a Cisco IOS 2811. Now, this obviously had a public RCE, which gave us root access to the switch. And from that, it's game over, right? You can permit our host to get in, bypass the DMZ, and we were in the network. And from here, the moment we were inside the network, we run our responder, PowerShell, and Cobalt Strike to gain access to multiple systems inside. And then we use our C3, got access to the internal servers, and it was, most importantly, we gained access to the secure network. And with secure network, you know what it's coming? No OTP, right? So now we were able to finally log in inside the central employee panel. And at this point, we're like, okay, now we have done our part. Now we can tell the CISO that, okay, now you know what we can do. And at this point, the CISO was pretty impressed, and he gave us the full-blown internal red team project, and moving on to phase 2. So that's where the internal assessment now starts, where we are there, Himanshu, I, and a couple of others inside the campus with basic access, trying to attack from the inside out. So yeah.
Yes. So keep in mind that it's a huge company with a huge campus, multiple buildings. They had a lot of networks. Like every different building you go to had like five networks, and their network security team was really good. Like when we met them, all these guys were really good. They knew what they were talking about, and they had a lot of devices set up. They were firewalls, DLPs, everything. Plus, even like as Aman already told you that they had strict compliances. We couldn't even walk anywhere on the road. Like they were strictly
If
marked.
you're walking on the left side and the policy is to walk on the right side, a security guard would come and tell you, sir, that's against the policy. Please walk on the correct
Yes,
side.
so that was the strict.
What kind of policies we are talking about in this campus?
So we started off with initial rules of the engagement, which is pretty standard for red team activity. And in the meeting, we usually ask for the critical assets in the network, right? So that would have been our entire objective of the activity, like not to focus on number of the vulnerabilities, but to focus on the main objective. It was a goal-based activity. So we were told about the industrial control systems, the SCADAs, the data management system. They also had some medicine databases. They had medical sensors. They had packaging systems, because obviously they manufacture it. They do their research on medicines. Everything was there on there in the campus. Now the first things first, right? We had a guest room there, and it was very restricted, and yeah, so we basically had very minimal access, and everything was whitelisted. But we actually, they gave us the list of critical VLANs, like, okay, this is what you have access to, but this is what we want you to attack or get access to. They also gave us a couple of Wi-Fi networks, like these are pretty much important. These are the servers which are important, and the most important part is that what to stay away from, because we don't want to be touching something like which is really live and can do accidental damage. So we had a strict no-go zone, that if you see something like this or this IP, you stop there immediately. Moving ahead, this was our approach. Basically, we did external recon, we did external compromise, we established a foothold, and then the point was there to basically escalate as much as possible to get access to maximum privileges, or maximum privilege we could get to, right? Then once we are inside, and then it began the internal recon. So we started the entire process of recon again. What all systems are there, what kind of devices are there, what what kind of IPs or what kind of ports are running, what kind of services they use,
Just like any other organization, we had different segments of the network. So we were there in a very minimalistic network, very restricted. Then of course there was a central network that every employee connects to. Then we have dev networks, we have account networks. There are just like any other organization, these AD policies are properly implemented. And of course, we only had a LAN access to our laptops. So yeah, first things
We
first.
had to, yeah, we had to open our Facebooks and play PUBGs, Counter Strike. So we just basically created a LAN based hotspot to
Yeah,
complete that
yeah.
objective.
Yeah. So from this point, we started doing trying to gain access, pivot, escalate, and all of that process. Standard approach that goes into this is, of course, network recon, port scanning, VLAN testing, sniffing. Responder comes in very handy where, in such situations for sniffing out NTLM hashes from the network. AD enumeration, super important with Bloodhound and Death Star, very helpful. And of course, internal phishing and ACL enumeration, getting an idea of what network to go to, how to, what would be the proper workstation that we'll have to exploit in order to get outside the restricted network to the main network, to the dev network, to the medicine databases, to the scientific data management systems, to electronic lab notebooks where scientists are keeping their notes and all of that stuff.
So
So
keeping in mind that because it's a restricted environment, it's possible that we have to be very careful. For example, if you try to execute a PowerShell script on a HR network, the actual SOC team would get suspicious that why does an HR need to execute a PowerShell in their systems. So we had to be very careful according as per that. So this is the
yeah,
compromise flow one.
blending in is the most important aspect of doing that. So yeah, so outcome is this.
This was the initial compromise flow, one of the flows which we managed to achieve to get access to the employed database system. Now, what we noticed was because pharmaceutical companies, there were a lot of industrial control devices. These devices are actually, limited to. They have a lot of dependencies, like they have OS-based dependencies, they have software-based dependencies. One such software we found was basically HP Data Protect, which is used basically to manage the automatic backup and recovery of all the data which is there in the connected to the system.
Yeah,
Now,
so
HP Data Protect had a
irony,
standard
data protection software compromises the data because it had an RCE.
IRT. Yeah, so we were, and plus it obviously HP Data Protect requires to be run as root to be able to back up all the data. So we had an RCE, we achieved the anti-authority system straight away. And the next step is everybody, I'm sure, can guess. Mimikatz came to the rescue. We were able to dump the hashes. We were able to also extract some of the even the credentials in plain text because it was a frequently logged in system. So we had credentials stored in the memory. We were lucky enough. Now comes the
Yeah.
interesting part.
Yeah, so this HP Data Protect is obviously a widely used software because it has multiple instances in the network, and of course it is like it's being used and it is vulnerable, and we already had one RC. So of course we found all instances of HP Data Protect and ran an RC, got anti-Android system. That was a pretty easy cakewalk, of course. And once we got out of our minimal network, we started recon inside that more elaborate network. And one of my interesting, like one of my go-to tactics is, of course, to search for internal web apps that generally are less restricted, a lot of times running on HTTP. So that makes it easier for sniffing and all of that stuff. Easier to find vulnerabilities. XSS is again used for internal phishing. Very interestingly, there have been cases where we have been able to use XSS to inject JavaScript that steals the login credentials. And there are a lot of benefits of reconning internal applications. And this was one application. This was an LMS inside this main network, employee network, where all the employees are redirected to carry out their internal learnings and whatever. So this LMS has Adminer installed on it, and you can see the version is slightly older. And this version, of course, had an SSRF vulnerability. Now, in this case, what happened was while checking for SSRF, I was not getting any connection back. So I thought it's possibly port blocking. Firewall rules have been implemented so that outgoing connections are not allowed, which makes sense. But in this case, a lot of times, and this is again has worked a lot of time, people always allow, server admins allow port 53 because of internal DNS and requirements. they allowed 53, but the correct way to do it is allow 53 with UDP, but they allow 53 in general. That allows us to create TCP connections. And from here on, I was able to create my MySQL server. I used pre-routing with the IP tables, and I redirected all my 53 traffic to 3306. And I allowed the remote access on my MySQL. You have to enable that by default. The root access from remote IP is not allowed. So I created that instance, and I used and I bypassed the firewall with port 53. And from there on, I was able to exploit the SSRF. Now, AdMiner has this vulnerability wherein you can read local files and project them into a remote database, and that's what I did. I ran this load data local in file and read the etc password into my database, and as you can see in my database, the entire password file was printed. It was from here on, it was more recon, find interesting files, and that's what I did. I was able to identify that it was using WordPress WP config file enumerated, which gave us database username and password, and I was able to log in into the database and then log in into WordPress, then upload a shell and all of that. Obviously, this is a standard go through where you compromise a WordPress instance. And what was interesting at this point was, from this point, we were, because this was an LMS, this was actually also part of the dev network. So this is, again, all of this recon has been done initially when we are running our Death Star and planning our attacks, Bloodhound, to see exactly what path should we follow. And this machine was actually part of the dev network, which opened us the dev network for us. And the moment we did recon in the dev network, we were able to find some RMI services, and we created a custom bean with SJet. And the moment we used that exploit with Jython, we were able to gain again an RC on that server inside the dev network. So there was that. And that server, of course, again, the moment we gained access to that server, we started digging in for log files, source code, anything, because again, this is an LMS. So inside, if it is a dev network, there could be source code and things that are interesting for us. And that's what happened. We extracted Oracle credentials from the source code, and we were able to log in inside the employee panel, where to which the LMS was connecting to. And that led us to O365 credentials, because people were using the same credentials on their LMS and O365. So that gave us access to more employees' O365 accounts, giving us a lot of information. You can, any day you can go in, if you are able to access a company's email account, just search for SSH, just search for password, keys, things like that. People share these on email without any thought, and because obviously they assume nobody's going to get inside there.
Yeah,
So
not in GDPR though. Like, it doesn't work in. You should not do it in GDPR.
yeah, this is all pre-GDPR, non-GDPR areas where we are allowed to actually read email of employees. That's just our legislation system for you. Obviously, in GDPR governed areas, this cannot be done because it severely breaches the privacy. So at this point, we had a lot of things we had access, but some critical crown jewels were still left. SDMS, ELN. ELN is electronic lab notebooks. SDM is a scientific data management system, and the SCADA devices, medical sensors. They had factories for labeling, bottling the medicines, and all of that stuff. So that was there. And in comes compromise flow number 2. So
this only just gets interesting from here. Like, this was also the interesting part, but we also hated this part because, it involved reading a lot of product manuals. We were dealing with things we were not aware about. Obviously, we had done SCADA-based testing in the past, but we first had to figure out what softwares they were using, what vendors they used to get those softwares from. So we basically started with reading product manuals. It took us hours and hours of going through product manuals, understanding the functionality, and maybe then trying to figure out, okay, this is where the logic might break, or this is where a bug might exist. And
yeah,
because it was a live system, we actually did not have the permission to go ahead and try something which might crash the system. Or so we had to be very, very careful doing this.
Yeah, and even understanding how an ELN works, because where is the data stored? Is it stored in a database? Is it stored in the same server? And so all of that comes from the product manuals and the tireless 1 hour long YouTube videos and tutorials that these guys made. So there was that. Yeah.
Yeah, so this is how we started, and this is what we found. We basically started looking for weak default pass. That was our main goal, that which could get us access, straight away access. We had default password, we had databases running with was there databases. The question was, if they were running a database, was it required with the admin privilege? They had some open ports, but was there a telnet running on it? And then how do they work? What are SDLM? So we had long hours of sleepless nights going through YouTube videos, digging around what manufacturers they had, what model numbers exactly were there. So if you go to the previous, this slide, we will actually, this is where we actually figured that things started falling apart. These softwares are actually installed, a lot of softwares are actually installed by third party vendors on behalf of, to be used by all these scientists and people in the company. Now these softwares have dependencies. Old versions of OS, as we have told before, they had service based dependencies, because, and plus updating would take a lot of time. If there's a new update on Windows, and you'd have to actually do the entire update and manage it in the software system
And
compatibility as
these
well.
guys, server admin guys, which are very good, these guys were not even allowed to touch these servers because these were managed by third parties. So there was a clear instruction as to, so that means no hot fixes, no updates, nothing like that. So obviously that gave us a thing that we have not included in this is, again, inside the network we were able to find backdoors created by ransomwares and things like that. Obviously, they didn't work because of the restricted architecture. Some due to some reason, the ransomware was never activated, but it left loopholes inside. It left backdoors inside that also allowed us to traverse into these devices, because these are again third-party vendor controlled, and the organization does not have a lot of freedom to update these and keep them secure. So that's how it
There's
began.
a very interesting documentation showing that with what we found of the software. Once we found the name of the software, we started looking at the docs, and this is a very classic example that default username and password. We were able to get these some of them, and we had access to electronic lab notebooks. Now electronic lab notebooks are basically considered as keeping a digital notes for scientists. You are writing some formula, you are taking down some notes based on experiments, and everything you can actually do it digitally and store it on these systems with historically all of the things mapped. So these had entire formulation histories, the entire experiments, everything, every research here mapped in it.
Yeah.
So
And it was extremely important to get into the software of the ELN, not the database, because in future, as I will tell you, when we were able to get inside the databases, there was no readable data. Of course, it was all encrypted, and
yes.
without these credentials, we wouldn't have been able to. Without the login of these softwares, even if we had access to the database, it didn't help. So that's where this was important. So
Meanwhile, we already had our responders, running since then. Basically every new network we had access to, the first step was we started running responder and see where it goes. We left it right there. So this was a major breakthrough where we, discovered basically a developer
developer
workstation.
workstation.
And you can see that if you notice that it already has Internet Explorer icon there. And this is where interesting part comes in. We actually tried the browser pivot. So basically we did a man in the browser attack where proxy pivot is created, and whatever the user actually does on his own Internet Explorer, we are able to basically refresh and use the same session on our own browsers, keeping the
Yeah,
desktop.
if you remember the concepts of Zeus botnet and the those things, this is again pre-integrated into Cobalt Strike, and you can actually inject proxies on the go inside Internet Explorer, and of course that gives you access to all sessions and passwords of the developer that is working on that workstation. And so what we did was, of course, this developer was logging into the Oracle Enterprise Manager, and the moment he logged in, we waited for 2 days, and of course, the moment he logged into the Oracle Enterprise Manager, which is controlling all their databases, that was a big win. And
Luckiest day of our life.
yeah, so that helped us access to internal databases. Of course, they had encrypted data for a lot of things, But yeah, from that point, I decided, okay, I have access to their Oracle database. So wrote this quick script in Oracle to get an RCE from the server. This is again, you cannot, while doing SQL injection, you cannot execute these kind of scripts to gain RCE from Oracle. But if you have the access to the Oracle console, of course, then you can use the DBMS scheduler servlet in Oracle that allows you to create jobs, which obviously you can use to get reverse shells and execute your command. So this is how we got RCE on the Oracle server. And the moment we got RCE on the Oracle server, I started digging into that Oracle server and started reading their files, log files and things like that. Inside the log files, obviously, we were able to get passwords for electronic lab notebooks, more electronic lab notebook passwords, and most importantly, the SDMS. Now, this is Mpower, that is the name of the service provider, the software provider. And SDMS is again scientific data management system. This contains all of their formulas, medicine formulas, and not only that, we could see the formulas for the medicines they were developing. We could actually edit it. And at this moment, we realized that we could convert this 100-acre campus into allowing to change the formulas for basic medicines like Combiflam and Crocin and convert it into happy pills. If you might say, and mint out literally, because not only we were able to control the formulas, as you will see later on, we were able to access other things also that allowed us to start minting out different formula medicines out of their factories. So this was like disaster, but we were still not into the SCADA systems and all of that. So there is that is left. But we had read-write access to lab notes. We had access to formulas. We could change that. We could, as I would show you in the future, we even gained access to the SCADA systems that were doing printing, packaging, bottling, labeling of all the medicines. So it's like complete game over from that point. And these secret formulas could, again, by a malicious attacker, be sold to competitors for hundreds of thousands of dollars. Or imagine if I just simply delete these things, or because I have access to data protector, I have access to the database, I have access to the backup management system. So today, if I short their stock, because obviously it's a public listed company, and then delete all of this data, I'm making millions of dollars. So this is like disaster for them, because we were able to access this much. And in comes the final flow, that was compromised flow number 3, that led us to the SCADA devices and the entire Active Directory for us. It was game over from here. This was
So we basically had we were continuing our recon process in the backend, and where we came across a inventory management system, which is initially which we figured that okay, this is what system admins use to push updates, manage systems, take remote control for support, technical support, reinstallation, installations, enforce policies, etc. So we started credential spraying as usual, and then we actually logged in using one of the passwords collected, and what we discovered was basically we saw that okay, we found we started digging around, and we basically discovered an SQL injection and the password
management system, which again is its purpose is to manage and execute scripts on the devices in the network. So
imagine a system connected to everything and anything which is system, and then you have an SQL injection there, and you are able to log in as an admin. So basically, as you can see in the screenshot, we had access to all the labs and every network on their campus through one single portal. And this gets better. This actually, we started reading the documentation, and we found that this software actually allowed to create a custom execution script, which would, and then we could actually select in which network and what computer we want to run this script on. And obviously it would have been run as an system with system privileges, because it was an agent based. So the agent running there was running with privileged user, as a privileged user. So we basically
came from a 0-day in the IMS, which is again not reported anywhere, and we found during our other exercises a 0-day in this IMS. And the the worst part was that this SQL injection was accessible without any authentication. So
Yes,
yeah, so without any credentials, we were able to get inside admin access of this IMS, which led us to the AD. And from AD, it was game over. So from AD, we were able to get inside the SCADA systems and obviously get the printing, packaging, bottling, labeling system, which was working on SCADA. The name of that was Retrack, which controlled carbon printing, case packaging, pharmaceutical bottling, labeling, all of that things. It was
conveyor
covered.
belts, everything.
Yeah. So it was really crazy at this point where I remembered the scene from the movie Hackers where they are fighting with their DVD stacking systems. So that's what we could actually do. We could change which bottle goes where in that factory and all of that. It was crazy at this point. And that was mission accomplished. We gained access to the formulas, we gained access to the SCADA systems, all the notes with read, write, edit, delete access. So yeah, that was
And
mission
of course, guys, we must tell you that okay, everything was, we had a point in contact SOC from their team. We were actually real time informing all the bugs we discovered. We had CISOs pre-approve us and give us the permission before we went and ahead and do anything. So imagine we had access to this. We actually had to take permissions of the CISO that okay, sir, we have got this. This is a possibility. Would you give us, a go to go ahead? And the CISO was, he was, I guess he was on our side, and he wanted to see, the extent, because obviously he wanted the in the end, the end goal was for the CISO was to, make sure this doesn't happen from a malicious intent. Nobody from outside is ever able to, achieve or gain access to this much data anywhere possible. So please, the key point here was basically you once you do all of this, you have to basically ensure that everything and anything you find must be reported immediately, because when you when you go around digging with SCADA systems, it's actually very critical.
Yeah, and why it is even more important is why these SOC teams and they have to be aware of the things that we are doing. Is that if somebody is actually attacking, carrying out a real attack, then the SOC team and the blue team should be able to differentiate between red team attacks and real attacks if they are happening. So it's very, very important.
Yes,
So
using our pattern fingerprinting, they should be able to catch, like, have such incidents in the past or in the future.
Yeah. So quickly coming to key takeaways, key things that we keep in mind while doing external recon is, of course, subdomain enumeration on cron. That means constant subdomain enumeration is very, very helpful and much more powerful than just running a subdomain scan once. So obviously we have automated recon. We even provide it as a service. It's called Security Risk Monitor. It's a tool for attack surface management and third-party risk assessment. We use it for our recon also. So we keep on scanning subdomains, changes in the domains, changes in the output, so that the moment a new application or internal application comes up, we are able to attack it right away. Of course, reverse whois, full port scans, Google, Shodan, Census, Binary Edge. Again, very, very helpful. Shodan filters and Census filters are super, super important and very useful. You might have heard about the recent attacks going on while attackers are searching on Shodan using the favicons because Shodan provides that, and discovering softwares with known vulnerabilities using that in your organization. Of course, a big part of web analysis comes from JS analysis. There have been so many cases. Every day I am struck with some JS file which has some internal path or credentials, API keys. So analyzing JS files is super important. Of course, parameter brute forcing, header brute forcing, getting URLs and internal endpoints, not only from active scanning, but from passive scans like you might have heard about GAU, GAU, Web Archive, things like these. And of course, Google cached things. Then GitHub Secret Finder, again, so many times these internal developers, they host source code of their organization from their personal email account, again, on public GitHub repositories that contains, a lot of time contains API keys. Even yesterday, a day before, I extracted SMTP credentials of one of the accounts, a watchdog service of a client of mine, wherein basically it reported alerts and errors in their servers. Now this developer hosted their code on GitHub, and the private account of that company that had access. So it was again game over from that point. Cloud assets, S3, Docker servers, Azure servers, AWS. Again, accessing these are super important. Getting a root AWS access to a company's account is very helpful for you as a penetration tester or red teamer. Employee OS int, again, we have shown you how, obviously, trying to understand the hierarchy inside the organization, which person does who. These things are very helpful while carrying out phishing attacks. Leak credentials, and of course, reading the API and product documentations, because a lot of time you will come across products that you are not aware of. You have no idea how they are working, and they could be very sophisticated products. So reading the API and product documentation allows you to find a lot more logical and privileged escalation vulnerabilities as to just approaching it and running standard tools on that. So yeah, with the internal recon, again, you get inside the network, you run your full port scans, you run your basic automated vulnerability detection softwares like Nessus, Insight VM, Cobalt Strike, Core Impact, if you have that.
But guys, keep in mind that if you're doing a red team and you want to avoid detection, you should not stick to tools because they make a lot of noise, and you should do as much as manual recon as possible, and then maybe you should customize your own scripts, which we often prefer while doing a recon. And then yes, so we have responders for internal recon. We do sniffing, we do Wireshark, we actually test for VLANs, we actually see what other VLANs can we hop off, are there any misconfigurations, whether a switch we compromise, we are able to,
L2 testing, layer 2 testing with VLANs. Again, we have not included it in this presentation, but the same client, we were able to hop VLANs using L2 testing, because these had layer 2 vulnerabilities, these switches. So that was really helpful. Coming to footholds and exploitations, of course, we have so many ways to run exploits, but more important is customizing our exploits, because running the same old payloads, public payloads, first, they might not work. Second, they raise the red flags. So it's always better to look at the exploit, read the exploit, customize it, put better payloads with more obfuscation. That will help you. Phishing is a very big thing that people ignore. Humans are the weakest link in the entire security ecosystem, and if you do not exploit that, then you're missing out on a very massive aspect. So of course, not all red team exercises the client allows phishing, but red team exercise without phishing is a bit derailed. So yeah, default accounts, a very good way that helps us in finding zero-day exploits and things like that. Public exploits that are the exploit exact vulnerability is not public, is of course comparing patches on Git or using diff to compare the binaries and to find out what exactly changed, what did they patch. So if they applied a patch on this, then if the older code was there, what could be the vulnerability? And again, build a exploit on top of that. I think we did that with Drupal, Himanshu, if you might remember.
Yes, we had to customize our exploits.
Reverse engineering the patches to find Drupal exploits, make Drupal exploits. And again, reverse engineering the mobile and desktop applications is very helpful. Gives you access to a lot of internal endpoints and API keys and things like that. And of course, our C2s, most important, C2 and C3. Cobalt Strike is one of the best, of course. Coedic, very helpful. If you've not checked out Coedic, go right now and check it out. It's very amazing. Empire, and of course, PowerShell Empire. Armitage Teams is very helpful. If you don't have access to Cobalt Strike, does a similar job, but again, nothing beats Cobalt Strike at red teaming. So there are these. Coming to AV evasions, of course, there are so many techniques that you can use. Some of the most helpful ones that we have seen during our red team processes is in-memory injection, encrypting the payloads, and of course, one of the best ways is the malleable C2 provided by Cobalt Strike, wherein you can customize your Cobalt Strike beacons, which gives you a lot more flexibility to bypass modern antiviruses with behavioral detection. Of course, you can bypass the static and dynamic uh, malwares detection with properly encrypting the payload and packing it with things like iExpress. Creating signed EXEs, again, a very, very important aspect of bypassing the smart screen in Windows and things like that. So there is that. But malleable C2 again is a big helper when we are talking about AV evasions.
Yeah,
Yeah.
we have different frameworks for post exploitation. Like you're already in the network, what to do next? We have PowerShell based power up. We have Nishang framework, which again has different set of modules, and which are again PowerShell based. Then we have Responder, obviously, which might ease your way into the network. You might be able to get a lot of NTLM hashes and authentication. Then if you have a Windows system, you are able to run Mimikatz, is well and good. Then we have Mimikittens. For Linux systems, we have Mimipenguin doing the same job, extracting the credentials for us. Then you have browser harvesting, where you are able to achieve a credential, where you actually look for pre-stored credentials in the browser or pre-stored configs. Like a lot of time, like we know, like I myself, sometimes prefer storing credentials in the browser itself, because ease of use. I don't have to go to the hassle of typing the password again and again. Then
Yeah.
yeah.
Himanshu, you just need to have access to his Google Chrome.
Yeah. Okay, I shouldn't have told that. Okay, then you have, the most important key part is that if you are doing a web application, you have gained access to the network or simply the application part, you should go through the source code, guys. You should read. We have had cases where, we basically we were not able to get inside a production environment, but we were able to get into the dev environment and reading the source code. We started reading the source code initially, and we actually were able to discover a couple of vulnerabilities within the source code itself, and we were able to replicate it on the environment itself, on the production environment.
Yeah. Quickly wrapping it up with pivoting, of course, we have browser pivoting. Then, of course, you have TCP tunnels over HTTP, which you can encrypt with SSL. You have SOCAT, and so many ways. You should always encrypt your tunnels and your reverse shells so that DLPs and things like that do not detect your traffic. We'll cover that quickly in the staying under the radar. Again, SSH tunnels should be encrypted. Things like that. Port forwarding,
Cat,
multi-level.
SOCAT. Yeah, there are a lot of tools out there already. Then we have meter port forward, then multi-level pivot, where actually when you are jumping from one network to another using a system as a pivot point. Then yeah, so
And most importantly, the moment you take over, let's say, a web application, you create your own admin account. Again, a very straightforward and obvious thing to do is to create users that look similar to the actual users, and that is very important because it helps you to cover your tracks, and the system admin won't should not be able to just look at a username and tell it's a password. So if you hack inside an organization and create a user with 1337 XOR, obviously the system admin will detect it. So staying
don't
in
do that,
the
guys.
yeah. So staying under the radar, of course, while exfiltration, you can use the OneDrive and Dropbox C2s. Then, of course, you have ngrok and custom. So a lot of times in our red team assessments, we buy homoglyph domains. We buy HTTPS certificates, signed certificates with their name, and then create our C2 and C3s so that all of this traffic, when a network administrator is looking at it, it just seems like their own internal traffic. So that is the most, because if today I tell you to identify a malware in your system, you will open your task manager and try to look at a process that is unusual or you are not aware of. So that is what staying under the radar helps you with, is you create traffic, you create noise that is possibly the inside noise, and the blue teams and the system admins are not able to detect. In
Yes, in
memory,
our case, it was very helpful. OneDrive C2s. We basically, what it did was, our agent, the Empire agent, was actually going through OneDrive first and then giving us back the response. So if I, being the SOC team member, was monitoring the traffic, all I would see is that some employees trying to go to OneDrive.com. which is okay because my employees use Office 365 network, right? So I use Outlook and Office 365. Yeah.
Yeah, so I think that wraps it up. Exfiltration, I think we're running out of time, so I'll quickly go through it. Obviously, you have Cloakify Factory for doing text-in-text steganography. Obviously, everybody has heard about text in image, text in MP3, text in blah, blah, blah. Cloakify allows you to do text-in-text steganography. So a paragraph about random things, two people having a conversation, and there is actual text hidden in that. If you haven't, check it out. Very, very useful while doing exfiltration. Of course, encrypt all your traffic while exfiltrating. Create all your tunnels, bind shells over HTTP, because TCP tunnels are not TCP based shells are not stable. HTTP shells are very stable thanks to the stay alive header. DNS exfil, ICMP exfil, again very, very helpful. Empire has a very good exfiltration option with Dropbox. Again, helps you keep under the radar and exfiltrate large amounts of files. We have exfiltrated like 20 GB, 50 GB databases using Dropbox. So again, stays under the radar, obviously because it's Dropbox. System admins tend to ignore that. And I think that wraps it up, concludes our interesting journey of this pharmaceutical. I hope everybody took out something from this talk. Of course, you can reach out to us on Twitter, Facebook, LinkedIn, wherever you feel like, for questions. If we have, we would take some questions right now, or you can send it to us later. Yeah, I think that concludes it
Yes,
from
that's
our side.
about. We are on time. Yes.
Yes, you are pretty much
Yeah.
against the deadline, but there are a couple of questions, and the talk after this one is pre-recorded, so I'm just going to whack it in because I think it's important to have questions when questions are asked that we ask them. I got quite a few of them are blue team related. So first question is, when you are on a target network, what are some of the observations that give you a vibe that the blue team is really strong and that they know what they're doing?
So, see, the most obvious way is that your payloads stop getting executed. Like you're trying a payload multiple times, you execute it, but nothing comes back. So, and then yeah, that's the like major flag that okay, someone out there is watching, or you have a connection, it suddenly disappears. It keeps
Yeah,
dropping. Yeah.
deleted accounts, some unusual activity that you're not doing. Those things are there. Some your payloads, your servers getting blocked, and these things are standard pointers. New rules in firewall suddenly, VLAN policies and AD policies, things like that. Because these things do not update generally in an organization. Does not happen that just right out of the blue some policy changes unless somebody knows that something wrong is going on. That's where these things will happen.
I think we had the case in that add minor scenario. We actually tried some different posts initially, a port number for connection, and then suddenly, it got blocked.
Yeah.
That's where Aman got spooked, and we thought, why not try just port 53 instead. So that's a couple of red flags which actually we get.
Okay, awesome. Yeah, I'm going to do one more. Final one. In your adventures, what technologies have most detected your activity, if any?
What technology? In terms of, if you're asking about, in terms of technologies that we hack into, I think, of course, Windows servers, Oracle servers, and things like that are the direct vulnerable points. If there is a Windows AD during a red team exercise, we are more confident because of responder and because of so many AD flaws and pass the hash and all of these techniques. Of course, with Linux, you have to have things. If there are Linux servers, then big point goes to exploiting services inside the network running on that Linux box.
I think the question was also around the idea that what technologies caught us. So do we have? Yeah, in some cases, I think in majority of the cases, it was only when the SOC team was actually monitoring the traffic data
Yes,
live, and they were able to pick up our scans, the nmap
manual
ones.
manual SOC analysis is what has caught us a couple of times. It's not very common because not very common with us, but yes, when it happens, it is because of the SOC team manually assessing me. Because DLPs and AVs and all of these, we are already very used to bypassing these technologies. So most of the times, what comes in handy is a SOC with a proper, manual network analysis tool that they are able to pick us manually, looking at what activity is going on.
Yeah, exactly. So basically, it's more like, if you won't be able to find us if you actually don't know what you're looking for. So a person with experience who actually knows, this kind of traffic means like there's an nmap running, or this kind of traffic means there's somebody trying to, brute force credential spray, or this credential has been used too many times across all the portals. Why? Or like an example we gave, like, why is a HR trying to execute a PowerShell on script on their system? So this is the kind of case which usually,
so
yes.
any tool that is doing anomaly detection, I think, is one of the best tools that will be able to break through these infiltration exercises. Anomaly detection is a very big part right now for detecting attacks, because that's the closest you get to automated anomaly detection. So of course, those tools are bringing up. We'll see in the future some more easy to gain access to tools like these.
Okay, I guess I'm sorry. We are over now by 2 minutes. We really have to wrap it up here. But thank you ever so much for your talk. It was great feedback, as also we're getting from just the fact that you get so many questions. Great talk, guys. Thank you very, very much. Our next speaker is going to be Arnau Gamez Montolio, who will be giving a talk, a review of modern code deobfuscation techniques. I will play that in 2 seconds. Please don't go anywhere. And as promised, we have the next talk here, which is by Arnau Gamez Montolio, a review of modern deobfuscation techniques. This talk has been pre-recorded, but I believe he is in the Discord channel, so if you have any questions about the topic, by all means ask them in there.
Hi, and welcome to my talk, a review of modern code deobfuscation techniques. My name is Arnau Gamez Montolio. I am graduated in Maths and Computer Engineering. I am also the president of Hacking Libre, a non-profit organization around ethical hacking and social aspects of it. I am also an organizer for the R2 Congress, the Congress about the reverse engineering framework, RADAR2. First of all, a bit of a warning. This presentation may contain traces of assembly and also a little bit of formal maths, although it won't be required for you to follow those more formal aspects, as I will explain them very, very straightforward for everyone to understand and to get it. So the contents of the talk will be, first of all, introducing what is code deobfuscation and some basic techniques that we usually encounter. Then I will present you a brief theoretical-ish approach to mixed Boolean arithmetic expressions and how can we use them in order to obfuscate mathematical expressions and, at the end, arbitrary code. Then I will present you what is program synthesis and how can we leverage this technique or these approaches in order to deobfuscate code, some existing work and recent research in this area. And finally, I will show you R2Cynthia, which is a tool I developed that integrates a program synthesis tool known as Cynthia into the framework, and the reversing framework rather too. And we'll see a little bit of some demos. Finally, just showing you the conclusion, some future work, and a bit of references in case you're interested, just to be able to follow with the topic. So let's begin. When we talk about code deobfuscation, we have to place the context in the area of technical protections against the mate attacks, which are those attacks where the attacker or the analyst has a complete instance of the program and controls the environment where it is executed. As you can see in this diagram, obfuscation lays below the technical aspect of the protections, where we also have legal protections as well. So what is code obfuscation? In a nutshell, we call code obfuscation a transformation from a program, an input program P, into another program P prime, which is functionally equivalent, but which is harder to analyze and harder to extract information than from the original program P. Who uses code obfuscation? So I differentiate basically to different actors. And first of all, related to software protection, and then also for malware, it's used in malware threats. And why? So the main reason is just to prevent, although in reality it's usually just complicating the process of reverse engineering. In the case of software protection, this is motivated due to intellectual property and digital rights management. And in the case of malware threats, we have an intention of avoiding automatic signature detection, and also if slowing down the analysis, which leads to more time uncovered and more money, usually, that malware actors are able to generate from that. And how is basically applied those transformations? So usually the idea is to complicate the program's control flow and the data flow at different abstraction levels. We can see source code, the compiled binary, or even an intermediate representation, and those transformations affecting different target units. We can have, for example, the whole program, a function, a basic block, or even a single instruction. Just as a side note, a remark that many weak techniques that we can encounter, that from them used alone, could be not as hard to break, but usually we can combine a lot of them arbitrarily to create hard obfuscation transformations. So here we have a table from one of the references I will give you afterwards that presents basically most of the known obfuscation transformations to today. So I will start presenting you a few examples. Let's start with control flow obfuscation techniques. The first one would be opaque predicates, which are very classic obfuscation transformation. An opaque predicate is basically a specially crafted Boolean expression P, a predicate P, that always evaluates to either true or false. That is, at obfuscation time, the one who is doing the obfuscation, the transformation of obfuscation, knows the value of P, and it knows to be always true or false. That way, we can get some snippet of code and just branch it into two different paths, one of which will be the rest of code, the valid code that will always be taken, and the other one will be just junk code that will never be taken. This path will never be taken. Another usual technique for control flow obfuscation we find would be the control flow flattening, in which we basically change the structure of the function's control flow graph, and we replace all the control structures with a central and unique dispatcher. You have to think of a massive switch statement. In this case, we have this code with its corresponding control flow graph. As you can see, you observe that the green arrows point to the nodes that represent the true, the branches that will be taken when the conditions are evaluated to true, and we have this control flow graph. So if we flatten this control flow, we will get something like that, in which we introduce a new variable, which will be, in this case, the next, that will be used for the switch. And each case for the switch, will get us to a different place of the code. Okay, so at every time we go to one of the nodes that represent one case of the switch, we get back to the switch and go to the next one, depending on the result put in the next variable in each of these. Let's see a bit of data flow obfuscation techniques. First case, here I have dead code insertion, where this is a technique where we deliberately insert instructions into our code that do not have any effect in the computation's outcome. As you can see in this, both in those snippets, in the C snippet and the assembly snippet, the remark instructions, in this case x equals 1 and z equals 3, and also in the assembly listing, the move EAX1 and move ECX3 that are marked, those instructions do not have any effect in the outcome of the computation. So we call this dead code insertion, because basically this code that it's dead is useless. We can also find another data flow obfuscation technique known as encodings, which they are used to prevent a specific value to appear in clear at any given point of the program execution. And the basic idea is we can compose a pair of functions, f and g, for example, in which when we want to apply an encoding function, this will be the case when we are interested in hiding this value. So here we see that instruction sub EAX x1, 2, 3, 4. We apply the f function, which will be the encoding function. We push that value to the stack. We do whatever we need with them. And when we need to retrieve that value, the original value, we just have to apply the decoding function, in this case g, and this instruction remarked in the assembly listing in blue. Finally, for data flow obfuscation techniques, I will present you pattern substitution, which is a technique in which we can transform one or more adjacent instructions into a new sequence of instructions that is more complicated, usually involving more instructions, but it preserves the semantic behavior, which means the outcome is essentially the same. In this case, we have in the first two columns of the assembly listing, we see that the blue marked instructions are semantically equivalent. We have used just a pattern substitution in this case. And then the first instruction of the second column has also been substituted with another 4 instructions in the third column, as you can see, both marked in blue, which are, again, more complicated new sequence of instruction that preserves the semantic behavior of the original one. So, as you might expect, this process can be used iteratively until any number of iterations that the person or doing the obfuscation would like. So with that in mind, with that context about code obfuscation, we would like to define code deobfuscation as the transformation process that gets as input an obfuscated program P prime or a piece of that program P prime, and converts it into another program, another piece of program, P double prime, which will be easier to analyze and easier to extract information than from P prime, which is the obfuscated part. However, although ideally we would like that P double prime is basically similar, equalish to the P, the original program P, which has been used for the obfuscation, this is very, very difficult to guarantee. In first place, because the analyst or the attacker does not have access to the original program P to compare. Otherwise, it would be a waste of time trying to deobfuscate if you have access to the non-obfuscated version of the program you're analyzing. Then, also, the point is that usually the analyst or the attacker is only interested in some specific parts of the program being analyzed rather than the whole program, and it's usually interested not in reconstructing a functional program, but more on understanding what is doing on some part of it. So usually we don't need to reconstruct a valid program when we are dealing with obfuscation. We just want to know what's going on in there. So let's see a bit of what are mixed Boolean arithmetic expressions and how can we use them for code obfuscation and why are they important. Let's define them informally as an expression, a mixed Boolean arithmetic expression, would be a mathematical expression that is composed of mixing of operators among the integer arithmetic operators and also bitwise operators, as you can see here. If you want to get a little bit more formal, you could get this definition we have here in pretty LaTeX form. I won't go over it, but I just wanted to leave it here in case you are getting mathier and want to get a little bit more formal definition, which encompasses what we just said in a formal way of a mixing of operators in the expression. So you can see here just in bold, we have differentiated what are polynomial mixed Boolean arithmetic expressions and linear mixed Boolean arithmetic expressions. These won't be really important for this talk, but if you want to get a little bit into the theory of that, it's quite interesting, the difference and what kind of things can we do with such restrictions as linears, for example. We have more tools to deal with them. But anyway, this is just for the people more interested in going into it more formally or studying the mixed Boolean arithmetic expressions from a theoretical standpoint, which I will give you references to that if you're interested. So here you have a couple of examples. It's for polynomial expression and a linear one. And essentially, as you can see here, they are just expressions that mix operators from bitwise or Boolean world and the integer arithmetic of integers world. So how can we obfuscate with that? First of all, let's take into account that mixed Boolean arithmetic expressions are provides us a mathematical background to deal with the kinds of expressions we could obtain from a set of instructions for any computer architecture. So when we talk about obfuscating with this kind of expressions, we are talking of essentially being able to perform obfuscation in the terms of instruction, actual computer instructions. So with that in mind, let's talk a bit of what we call MBA rewriting, which is essentially getting an operator and rewrite it in an equivalent expressions, but more complicated. Let's say just rewrite and give an operator with another expression that is equivalent to the initial one, but it's more complicated. Okay, and the outcome of this process generates what we call the rewriting rules, and we have some of them in different references, and we have also some methods to generate them. I won't go really deep into that, but I will leave you the references if you're interested in that. Then another common technique for obfuscating with mixed Boolean arithmetic expressions would be what is known as the insertion of identities, when we just compose two different functions that are inverse, modulus, some number of bytes, essentially modulus 2 to the n, where n is usually 8, 16, 32, or 64. And for understanding better that both the MBA rewriting and insertion of identities, let's see just an example to obfuscate a very, very simple expression. So consider the expression x plus y and the following functions f and f minus 1, which are inverse, working on 8 bits. So first of all, if you apply the rewriting rule that we have seen just before to the original expression, we would get this one, the e minus sub 1 expression. Remember, we are just using this rewriting rule. Then we can use the insertion of identities that is produced by those functions that we have just defined. First of all, we apply f to the expressions that we obtain from the rewriting rule, and then we apply f minus 1 to such expression obtained before. So we just get the final expression, which is this one that we see here, expanded. And as you can see, it's far more complicated than the original one that was only x plus y. So we have essentially obfuscated our expression. How can we deal with measuring the complexity of such an obfuscation transformation, or more general, the complexity of a mixed Boolean arithmetic expression. So essentially, we can represent such expressions are directed acyclic graphs, which will identify commons of expressions. That is why we consider that if an expression has commons of expressions, this does not increase the complexity of the overall expression. So based on that, we find a few metrics that can give us some idea of the complexity of such an expression. First of all is the number of nodes of this graph representation. Then the MBA alternation, that is basically the number of times we change the type of operator we have in the expression from integral arithmetics to Boolean ones, and also the average bit vector size of each operator and operand, which is basically the bit vector size in which it is operating. So what are the theoretical simplification approaches that we can take in order to basically simplify such expressions, such mixed Boolean arithmetic expressions? And in the first place, we find what we call the bit blasting approach, which the basic idea is to find a canonical, that is a unique representation for such MBA expressions. The idea is representing the MBA expressions as Boolean expressions that are obtained by computing the effect of each operation on each bit of the resulting value. So we are getting Boolean expressions for each bit of the resulting value. We leverage for that the algebraic normal form that guarantees unicity, which is basically we express all the Boolean expressions we get will contain only XOR and AND operators. And the advantages that this approach has are basically that we are transforming the problem of the MBA simplification into the problem of simply Boolean expression simplification. Although we find a few drawbacks as well. And in the first place, we have that the process of canonicalization can be very, very expensive, both in memory and in time. And also identifying the word level expressions once we get Boolean expressions on each bit of the resulting value is far, far from trivial. There is still a ton of work to do, theoretically talking, in that aspect. And finally, we find that it's really, really hard to scale for this approach when we get to a larger number of bits. Think of anything that is bigger than 8 bits will be extremely hard to deal with that. Then we find another usually simplification approach that is usually taken, which will be what we call the symbolic approach, with the idea being just finding an equivalent expression, but in a simpler form. Basically, we want to use the existing techniques for simplification that we know for arithmetic simplification and for Boolean simplification for those parts of the expression that contain only one type of operator, and then we can use a term rewriting approach to create the missing link between those sub-expressions that alternate different types of operators. The basic idea is that we can generate rewriting rules for the obfuscation the same way we did for the rewriting rules used for obfuscation, just inverting the direction of the rule. As you can see here in this example, we just inverted the direction of the rewriting rule we used before for obfuscation, and we just get a rule for the obfuscation. The main advantages that this approach presents is that the simplification is not impeded by an increasing number of bytes. We are working on the word level, and also the representation of the expressions is far, far smaller than the representation in a bit blasting approach. Although we also find some drawbacks. In the first place, this approach is very sensitive to the size of the obfuscated expression, the total size and number of nodes in the graph representation, if you want to think that way. And it's also highly dependent on the chosen set of rewriting rules for the obfuscation. If we lack a rule that will be used for the deobfuscation, that its inverse was used for obfuscation, we won't be able to go as far as if we had that rule. So it's really, really dependent on the set of rewriting rules for the obfuscation that we have for this approach. So let's go now right into the program synthesis part, and I will start with a motivating example. So consider the following function, which represents an obfuscated MBA expression, and we are interested in its behavior. So we are just going to treat that function as a black box, throw some inputs, and observe the output. Let's just observe how it behaves, but without paying attention to the internal details that define it. Okay. So we treat it as a black box. We throw some inputs. We get the outputs. This is shown here. So essentially, in program synthesis, we are interested in learning or synthesizing a simpler function that exposes the same input-output behavior. In this case, such a function would be this one, h, which is just the sum of the three input values. In order to define program synthesis, we could say, a little bit informally, but it will be enough for now. It's just the process of constructing programs in an automatic manner that satisfy a given specification. And when we talk about the specification, what we mean is we want somehow telling the computer what to do, but letting the implementation details to be carried by the synthesizer. Okay. What kinds of specifications can we find for such approaches? In the first place, we can find formal specification approaches, which will be just specifying the way, the behavior of the program in some logic, for example, in first order logic. In this case, we just have here define a program that for any input on 64-bit values, we just add 7 to that input. Then we can also define a specification as a set of input-output pairs that just describe the program behavior, as we have seen before. In this case, we just have the set of pairs. And another way of specifying or giving a specification is having a reference implementation that we call an oracle. Even if that seems quite strange, this will let us to generate pairs of input-outputs that describe exactly the behavior that we want to synthesize. So essentially, our approach for our problem, that is basically code deobfuscation, its nature leads to a kind of inductive and oracle-guided program synthesis style, which uses the obfuscated code that we have as an input-output oracle. That essentially means that we will want to generate a set of input-output pairs from the obfuscated code, the oracle, and then determine the best candidate program that matches the observed input-output behavior. So, some practical considerations before going on. When we talk about constructing candidate programs, what we are essentially doing in real world is we are defining a context-free grammar that will encompass all the primitive components, the terminals that will be essentially which variables are we using to create our expressions, and also the ways in which we combine them, the production rules of the context-free grammar. Then we usually need to set some boundaries that will delimit the task of program synthesis, let it be the number of input-output pairs, the number of terminals and derivations of the context-free grammar to construct the candidate programs, and we would need to ensure that that task of program synthesis terminates. So basically, we need to put a maximum number of iterations or a timeout for each task. And finally, we usually need to decide when we consider that a synthesized candidate is valid enough, okay? And whether we want to introduce some kind of equivalence checking and in which way. So, what is the existing work in this kind of program synthesis approaches towards code deobfuscation? And in the first place, I would like to mention Cynthia, which is from 2017, that uses a stochastic, Monte Carlo research-based stochastic program synthesis approach, in which essentially we convert the problem of finding a candidate program into a stochastic optimization problem. That essentially means that we are generating intermediate results at digit iterations that will evolve towards a global optima that will be our best candidate program, and this evolution will be guided by a cost function that will just compute the somehow similarity between what the code we are trying to synthesize and how it's behaving, and the behavior that we are getting by those intermediate results. We'll see a little bit of that afterwards. So we are really lucky that we have a public and open source implementation of Cynthia, and this indeed will be some of the basis for our work on R2 Cynthia, as you might have guessed already. We will talk a bit more about it in a second when we present R2 Cynthia. Another really interesting work that came up just a few months ago is what's called QSynth, which is the title of a paper presented a few months ago, as I said. And it presents an offline enumerative program synthesis approach for also towards code deobfuscation and treating mixed Boolean arithmetic expressions as well. And the basic idea is having a context-free grammar. We want to generate all the programs up to a certain number of derivation of that grammars, and then we just create offline lookup tables that map each candidate program into its input-output behavior given some set of inputs. And just we perform an exhaustive search for the candidate programs, the mapping of candidate programs with each behavior, to find which one presents the same input-output behavior as the oracle we used to generate the input-output pairs, that is essentially the obfuscated code. In my opinion, the most significant contribution of this work is not, even if it's interesting that they use that approach of not using a stochastic approach, but an offline enumerative one. My opinion, the most significant contribution is that they presented an algorithm, a process that lets to split an obfuscated expression into smaller sub-expressions, then being able to synthesize those sub-expressions individually and finally reconstructing the total simplified expression. So this opens the door for a really scaling the process of synthesis, even if we want to use some other approach, not necessarily offline enumerative. But the idea and the process that they present for splitting the obfuscated expression into smaller sub-expressions that can be synthesized by their own, and being able to reconstruct the total simplified expression, this, in my opinion, the most interesting contribution that they did. So the bad news is that we have no public implementation available, and I don't expect that they release any of that, because in their paper they already say that it's integrated in some internal tool. So let's see what goes on in this direction, but certainly I'm pretty sure that there will be people, and I will try myself as well, to implement something that integrates that idea of splitting the obfuscated expressions into smaller ones. So let's see how this goes on. What are the limitations of those approaches of program synthesis, especially Oracle-guided approaches that we have seen? First of all, dealing with code or expressions that are on their own very complex semantically speaking. So think of cryptographic expressions. We want to derive cryptographic primitives, for example. If we want to derive a program or an expression that gives us the behavior of an already complex expression, just from its input-output behavior, this will be extremely difficult, because we won't be synthesizing something simple, but something that is already complex semantically speaking. Then, of course, dealing with some source of non-determinism in the code will be basically impossible to synthesize such a thing, because if we are relying on the input-output behavior, but we cannot actually rely on it because it has some non-determinism inside, it will be really complicated to synthesize such programs, such code. And finally, what we call the point functions, which are those functions that they give us the same output value for all inputs except one specific input that gives a different output. So if we try to synthesize such expressions just from randomly sampling the input space, it will be actually very difficult to get anything meaningful. So now we'll present you R2 Cynthia, which is the tool I have developed. And it's essentially based on the following component. First part, RADAR2, which is the fully fledged reverse engineering framework. Then ISIL, which is the Radar2 emulation engine, which is integrated, and also Cynthia, which is, as you might have guessed, a program synthesis-based framework for the obfuscation that will be synthesizing the behavior of the obfuscated code given its input-output behavior, observable behavior. The basic integration of that will be that from an active R2 shell, where we are performing some analysis of binary that contains obfuscated code, we just call R2 Cynthia script, okay? So then from R2 Cynthia, we will leverage ESIL, communicating with the R2 shell, to generate the pairs of input-output values for the specified variables that will be essentially the registers and memory locations that we are using for input and output. Once we have that, we just invoke Cynthia from R2 Cynthia with the generated input-output pairs and also some configuration variables. And essentially, the result of that will be that we will be able to synthesize the code semantics of the output variable, that is a register or memory location, with respect to the input variables, again, registers or memory locations. So let's just go into a guided example that will serve as an illustration of the process and what are we actually talking about. We start with some piece of non-obfuscated C code. In this case, we have the function EF49A, which essentially the only thing that it does is returns the value obtained by multiplying the second parameter times the fourth parameter. And then the target function, which the only thing that it does is calling the previous function. We will see in a second why we have such a construct. So when we have that, we want to obfuscate the functions. In this case, we used the Tigres version 2.2, which is an academic obfuscator, using the following techniques. In the first place, encode arithmetic, which will replace the original expression with an equivalent and more complicated mixed Boolean arithmetic expression. And then we will use encode data, which essentially will encode the integer arguments before calling the function, decoding them at return, which is using the encodings technique that we have seen before. So now we have this phase from the non-obfuscated C into obfuscated C using Tigres, and the code looks like that. This is the F function where we just replace the multiplication of the second parameter and the fourth parameter with this large mixed Boolean arithmetic expression that is equivalent. And also for the target one, what we are doing is essentially encoding the parameters before calling the actual function. That this will be decoded at return value when we return from this function. Okay. So once we have that, we just compile that C code and we obtain an obfuscated assembly counterpart. So let's explore a little bit of such an assembly. So I'm opening the obfuscated file. I will analyze code to obtain flags for the functions. And if we just print this assembly of the function target for an 8. Okay. Here you see this function. This is the C function target that we have seen, getting those values as the inputs, and then essentially this encoding with the values we have seen, all the inputs, and once the inputs are encoded, it's just the only thing that it does is calling the function f that we have just seen. So let's now take a look at this function. And this assembly listing that I'm not expecting you to read, but I only want to show you how long is it with respect to the target. For example, it essentially contains just the multiplication between the second and fourth parameter, but obfuscated. So it is code that computes multiplication between second parameter and fourth parameter, but obfuscated in the way that we have seen in the C code. So basically, this is all the obfuscated assembly instructions that perform such an operation. Okay. So if we want to address the task of deobfuscating such code, through, for example, a symbolic execution approach. What we will obtain would be an expression that represents the return value, in this case, what will be in the register EAX at the end of this snippet of code, the call to target function. So we would obtain an expression for such a value with respect to the input variable, okay? The input variables in this case are the 5 first registers for the calling convention on 64 bits. Sorry, I said output value will be EX. In this case will be RAX because we are in 64 bits, but anyway. So let's observe the resulting obfuscated MBA expressions that we obtain if we run a symbolic execution engine through this obfuscated code in order to get the expression for the return value with respect to the input variables. So essentially, this is the way that looks such an expression. So here we have RSI and RCX as variables, which are the second and fourth inputs, and this is essentially the expression that gives us the result that will be in the RAX register after we call the function, essentially its return value. So as you can see from here, the syntactic complexity of this expression makes it totally unapproachable and I would say useless for us to derive any understanding from it. So basically, we have obtained an expression for a return value that is useless because it's too complex on the syntactic level. But remember that its semantic behavior, its semantic complexity, if you want, is, I would say, trivial. It's just multiplying second input times 4 input. So we will leverage R2Cynthia to just extract the actual code semantics. We will synthesize the code semantics just based on the input-output behavior and not being limited by the syntactic complexity of the expression itself, of the instructions that are defining this obfuscated code. So let's take a look at that. Let's print this assembly of the function target again, which will give us the boundaries of the obfuscated code. In this case, we will start just in this instruction, and then we will end at the end of the function, which will include all the call to the function f that we have seen before. So let's take a look at that here. So here, as you can see, we are calling R2Cynthia. We first of all indicate the bit size we are working with, then the initial offset, the starting offset for the obfuscated code in the file we are analyzing. As you can see, this is essentially the offset where the target function begins, then the finish offset, which is essentially the last offset of the memory direction where the last instruction of the function is, and then we pass as input variables those registers, which are essentially the registers for the inputs, and finally we pass the output variable that will contain the output of the operations. So if we run that, it will output a lot of verbose information that I put out for you, and I will go over it a little bit. So here we have, let's let it finish and then we will comment about it. Okay, that's it. Let's comment a bit about it. So essentially, first of all, it just prints the information that we pass to it, the bit size, the start offset, the finish offset, the inputs variables and the output. Then what we do is we are generating the input-output pairs, and essentially we are using ESIL, the emulation with ESIL, to give values to the input variables, in this case, those registers. So basically, those values that you see here in the input-output pairs are hard-coded to the registers at each pass of the emulation. So we just give those values to the input registers. We emulate all the code until the finish address, and we observe what value lays in the output variable, which in this case the Reyes register. We do that a bunch of times, and we collect those pairs of inputs and outputs. Then once we have that, we can create the context-free grammar that we will use, that Cynthia will use in this case, to generate the candidate programs. So essentially, we start with a non-terminal variable that we call just U64, and we have the following terminals for the grammar. We have all the input variables, in this case the registers, and also those operators. So essentially, with that, we can apply those different production rules iteratively. Here you have in reverse police notation, which is actually how it is implemented internally, but here you have the nfix representation just to take a look at it, feel more readable. Okay. And finally, we just said that the starting variable for the context-free grammar will be the only non-terminal that we have. So applying those derivation rules, we can generate candidate programs, candidate expressions to meet the input-output behavior that we have observed. So essentially, we just now call we call Cynthia from R to Cynthia, and it starts doing some iterations of the Monte Carlo tree search, generating intermediate candidate programs until we find a reward of 1, in which case we will obtain essentially an expression that gives us exactly the same semantic behavior. And as you can see here, the final expression found with reward 1 is essentially RCX times RSI, which is, as we know, second parameter times fourth parameter, which is essentially the semantic behavior of the code that we had initially, that we obfuscated at the C level, then we compiled to get an obfuscated assembly counterpart. And as we have seen before, if we extract its expression with a symbolic execution engine, we obtain a massive expression that is useless for us because we cannot derive any information from it. But if we synthesize its behavior, just observing its input and output, we can call Cynthia in this case to learn a function to construct a candidate program that matches this behavior, this input-output behavior. In this case, as you have seen, in less than half a second, we obtain essentially the semantics of the obfuscated code. So basically, that's it. And if you're wondering when will be this published, it's already published. So you can go play with it to that GitHub repository. Please note that it's on early stage and it's on alpha stage, I would say, but it works, and you can use as variables for inputs and for output both registers and memory locations. You have some examples in there. I'm planning to extend it, or maybe to transform it into a native Product2 plugin that will give us some more space for configurations and other stuff that will be much easier to handle than just having a single script file. But anyways, you can already go there and play with it and report issues, bugs, or whatever. Extend it for anything you would like with it. It's there for you. So let's see a bit of the conclusions of the talk and my work in here. First of all, a few takeaways. Mixed Boolean arithmetic expressions can be leveraged to obfuscate data flow of a program. This has been demonstrated before. We can use MBA rewritings and the insertion of identities, and we've seen, for example, Tigres that is using the encode arithmetic transformation that essentially does a replacement of an expression with a more complicated mixed Boolean arithmetic expression. Also, that current deobfuscation techniques that are mainly based on symbolic execution and some variations, even if they are super useful for a ton of cases, and when they address simplification of this kind of data flow obfuscation, usually they are very limited because they are strongly tied to the syntactic complexity of the code that they are analyzing. So this gives some limitations, some clear limitations to those approaches alone by themselves. And finally, we have that there exists, and we already have some implementations of program synthesis approaches that are quite novel, that allows us to reason about the semantics of the obfuscated code and being limited only by its semantic complexity, but not for the syntax complexity. For future work, I would say that there is a ton of work to be done on the theoretical aspect of mixed Boolean arithmetic, expressions treatment. There is really a lot of work to be done here yet, and more mature theoretical development can lead to better approaches for simplification, both on a theoretical aspect and also to improve even more some techniques, for example, from program synthesis or other approaches that we could take. And from a more practical standpoint and more immediate, we can have just improving Cartosynthia, which is already a work in progress. I'm working on that just right now, as I told you. I'm working on doing it, a native R2 plugin, and introducing some improvements to that. Also, I would really like to implement an open source solution for that approach presented by the QSynth paper for synthesis of sub-expressions and further reconstruction of the original obfuscated expression. And also, it makes sense to detect patterns and to somehow memorize synthesized tasks to not repeat them. So somehow have an offline database of already synthesized tasks that we can reuse them for free. Because usually some operators appear many times as different obfuscation transformation. So that would make a lot of sense as well, to have some offline memorized component to reuse those for free. For references, here you have a few of them. First of all, chapter 5 on obfuscation of the Practical Reverse Engineering book. Also, the tutorial on software obfuscation, which is a quite long document by Banescu et al., which is the one where we extracted the table I showed you before on obfuscation techniques. Then the book of surreptitious software by Christian Kolbert, which is also the creator and I guess maintainer as well of the Tigres obfuscator. Then there is a recently uploaded course on GitHub about advanced binary deobfuscation, which is quite interesting and really useful. If you are a little bit more hard into theoretical aspects, dealing with mixed Boolean arithmetic, and so more from a theoretical standpoint, as I said, you need to read the PhD thesis by Ninon Ayrols, the obfuscation with mixed Boolean arithmetic expressions, reconstruction, analysis, and simplification tools. Then also, if you're interested in the program synthesis approaches I described, you certainly need to take a look at the paper on Cynthia, synthesizing the semantics of obfuscated code by Tim Blasetko and others. And you also have a couple talks on CCC and Black Hat from 2017 and 2018, where they present their research, and they gave also some examples with that. And the other paper of QSynth that you have here, it's also really interesting, where they present all their work on the offline enumerative program synthesis approach for code deobfuscation, and they introduced that idea of synthesizing sub-expressions and reconstructing the original deobfuscated expression afterwards. So that will be all. Thank you for your attention. If you have any question, any comment, anything, you can always reach me on Twitter, as you have here, and also in that mail address. That would be it, and hope you enjoyed it. Thank you very much.
And that was Arnau. Now, Arnau is also currently available for questions on our Discord service. So please, I noticed a couple of questions were asked on Slido. Thank you for that, but please direct them to him in the Discord channel. I made a screenshot of the Slido page, and I will ask him those questions via Twitter. Follow him on Twitter. His Twitter is literally just Arnau Gamez. And ask questions. I'm sure he will love answering them. We will continue here in about 5 minutes with Nimrod Stoller, hacking the DevOps Butler, from nothing to admin. Don't go anywhere. And it is time for our next talk. This is another pre-recorded talk. This one is by Nimrod Stoller, Hacking the DevOps Butler from Nothing to RCE. Sorry, to Admin. I always keep getting that wrong. Hacking the DevOps Butler from Nothing to Admin by Nimrod Stoller.
Hello, ladies and gentlemen, and welcome to this Hack in the Box Lockdown number 2 session titled Hacking the DevOps Butler, the Road from Nothing to Admin. In this talk, we will describe in detail the code analysis process that led us to discover the vulnerabilities that allowed us to hack into Jenkins and how we managed to exploit them to trip the Jenkins security switch off and gain control over the entire Jenkins infrastructure. Jenkins, for those of you who are not familiar with it, is an open source automation server used to accelerate the software delivery process. It is now widely considered the de facto standard in open source continuous integration tools. For many organizations, Jenkins effectively acts as the DevOps engine, addressing everything from source code management to delivering code to production. Okay, my name is Nimrod Stoller, and I work for CyberArk Labs in Israel. In the past, I have been researching and developing embedded products. I was researching and developing for FPGAs. I was doing some web applications, some in-depth research on Linux containers. I'm also a licensed lawyer in Israel, and again, working for CyberArk. So now we're going to start with this slide about an example DevOps pipeline. So I'm going to switch to the laser pointer here. Here on the left side, we have the dev part, and on the right is the ops. The general scheme here is the following. Developers located here are pushing code to the code repository, which is in turn notifying Jenkins about the new code using a webhook. Jenkins is brought to life and starts building the code here, testing it over there, and eventually pushing the code, in our example, as an image into the Docker Hub here. If the dev side compilation and tests are successful, Jenkins will be prompted to continue with the ops side. This here, on the ops side, Jenkins starts another process which instructs the Kubernetes cluster here on the right to fetch the Docker Hub image previously saved here in this stage and deploy it across multiple customer-facing AWS instances. Enterprise DevOps teams today have the ability to deliver high-quality products and services to market faster and more efficiently than ever before. That's in part made possible through the use of DevOps methodologies and tools such as Jenkins. And this was the main drive initially for this research. So we're going to start with a brief introduction to Jenkins. Here in front of us is a Shodan scan. Shodan is a search engine for internet-connected devices and is an extremely important tool for cyber attackers. So this scan shows that almost 80,000 Jenkins servers are accessible online. You can see it's the number here on the left. This is a large number of servers, and of course does not count all the Jenkins servers and infrastructure which is located inside closed networks. We know attackers are constantly trying to obtain access to those Jenkins servers in order to take advantage of the unique blend of credentials and code execution available to Jenkins. Over the past months, we at CyberArk Labs have been extensively researching Jenkins as part of our ongoing DevOps research. Our research has now evolved into 6 CVEs and 5 blog posts on the subject. You are more than invited to read those research blog posts at CyberArk Labs Threat Research blog. Today, we're going to talk extensively about 2 of those vulnerabilities and what was the research process that we used to discover them. Now, Jenkins, as we said, is the de facto standard in open source continuous integration tools, with more than 220,000 active installations around the world. We've seen that almost 80,000 of those are accessible online. Jenkins servers execute more than 200 million jobs on average per month, a staggering number indeed. Jenkins to date offers over 1,600 plugins. All of them are open source code and available for download from the Jenkins plugins website for almost every tool and customization around. Jenkins is used at the heart of the development stack of very large companies we all know, such as SpaceX, Facebook, ENC Square, eBay, NASA, Sony, Netflix, LinkedIn, Michelin, GitHub, Atmel, and even Nintendo. We all know Jenkins is a wonderful tool. It literally is the engine that drives the DevOps train uphill. We all love it when one tool solves all or almost all our problems. And Jenkins does just that. It clones the code right out of the GitHub the minute we make a change in our code, and does everything needed to build, test, release, and even deploy to our customers, all while interfacing seamlessly with your favorite DevOps tools and applications. Jenkins is great at integrations too. Here we can see just some of the major plugin integrations Jenkins offers. From Git and Visual Studio source control repositories to Maven Art, Gradle, and Docker in the build and config part, Cucumber, JUnit, and Sonar in scanners and automatic testers, all the way to deploying artifacts to Docker Hub, AWS Cloud, and Kubernetes. Well, Jenkins has it all. It is therefore not surprising that Jenkins needs a lot of access, the secrets, to do its job. From usernames and passwords to GitHub, through access tokens to AWS and Kubernetes, SSH keys to access infrastructure, Jenkins holds them all, and so becomes a lucrative target for attackers, both from outside and inside the organization, seeking to take advantage of the unique blend of code execution and credentials, all available in Jenkins. It is these secrets that are increasingly sought after by attackers to carry out cybersecurity attacks, attacks which may result in complete takeover of an enterprise network. We will cover some of these attacks next. We will start with this case reported here, which is a high severity issue rated with a CVSS of 8.8. We'll explain how this vulnerability was identified using actual code samples. This vulnerability can be exploited when totally unauthenticated attackers manage to remove files from the Jenkins master file system, causing Jenkins to trip its main security switch, and in some cases, completely abandon all security safeguards, including those that are meant to protect the Jenkins infrastructure from data breaches. All of this allowing unauthenticated users admin access to Jenkins, as simple as that. This allows anyone to log into Jenkins as admin in what we called from nothing to admin. And although these issues were fixed a while ago, thousands of Jenkins servers are still vulnerable. Good, so now we begin our preliminary probing. I work at the labs of a privileged access management security software company, CyberArk. And part of our research is always geared towards looking into other software's privileged access. So we always begin our research on new software with looking into users' databases. For example, local databases, LDAP, Active Directory, and so on. And while doing this, we categorize all security measures the software under test is utilizing. Well, here in Jenkins, I actually don't mean to be disrespectful to Jenkins developers, but when we found this, we really laughed. Can any of you see what I mean here? Quite at the beginning of the probing phase of our research, we found, to our surprise, that Jenkins has this funny switch called Enable Security, which can be flipped on or off by the Jenkins admin. Well, it is only the admin that can do that, and the Jenkins admin is almost omnipotent. So this shouldn't be a problem, right? Well, as you can imagine, our goal from now on was one, to find a way to flip this switch and disable security for the entire Jenkins infrastructure, allowing any user on the network full admin access to the entire infrastructure. Let's see a short demo of that. So access to the global security configurations are allowed to Jenkins admins only. Here it is. Configure global security. But what happens on the Jenkins master when some admin decides to disable security? Let's have a look. Any sign of a login page simply vanishes, and we have complete access to all Jenkins pages and resources. Our next step in our probing was to find where this magical security switch is located on the file system. We hypothesized that Jenkins would be saving this valuable information somewhere inside the Jenkins home directory. Well, surprisingly, the first file on the Jenkins home folder is config.xml. Well, this might be it. But you can already see that there are a number of XML files in this folder. For example, Jenkins CLI XML and Node Monitors XML. Let's have a close look at what's inside the config.xml file. So this is a printout of the config.xml file, the Jenkins main config.xml file. And as you can see here, on line 11, we have this switch, which is called use security. Well, our goal now is clear. We want to change this flag on the config.xml file from true to false. That's all. If we can accomplish that, we can launch the ultimate attack. An unauthenticated actor on the network would then gain admin access to the entire Jenkins infrastructure. That is going to be just great. But again, working for CyberArk, we are always interested in the user's database of any research project we have in front of us. And Jenkins was no exception. Looking at the Jenkins Global Security Configuration page, we can also choose the Jenkins Security Realm. This defines how Jenkins is treating its users and where their information is generally stored. In our case, we use the Jenkins own user database. Every new user of Jenkins, whether it is a user of Jenkins' own user database or of other user databases, such as Active Directory, is welcomed with special gifts. A new directory is created for the username, and a new config XML file is written there with information regarding the new user, such as an encrypted API token, the user's email address, and its full name. The encrypted API token is a randomly generated token that may be used to make scripted clients, such as bots, impersonate the new user and invoke operations that require Jenkins authorizations, such as scheduling a build or changing a job script. For every new user, Jenkins prepares room on the disk to save the details of the new user. The term database is a bit misleading, as Jenkins saves the new user's information in that special directory called users, as we can see here. This is the users directory of our Jenkins. And we can see we have 4 users, 1 admin and user 1, 2, and 3. Every username is given a directory under Jenkins home users. And inside each directory, we will find a single config XML file. If Jenkins is set to use its own users database, this config XML file contains the hashed user's password, its encrypted API token, full name, email address, and more. Well, if we dive deeper into the admin directory, for example, we'll find the config XML of the admin. So we have a config XML file for each user under users username directory. Okay, this here in front of us is an example of a user's config XML file. We can see some of the information recorded here. Maybe the user's full name here, the API token, which is encrypted. This is the API token. The password hash here, its email address, and other information. Here, we have the Jenkins code that reads a config XML file into the Java code. So line 2 defines CFG as an XML file container, which is later, on line 10, being directly unmarshaled here into a Jenkins class. So the file itself defines and builds the entire Java class. Unmarshalling, in this case, is loosely synonymous to deserialization in Java. Another nice feature Jenkins has is this script console. This fantastic console allows the admin of Jenkins to run code written in the Groovy programming language on any of Jenkins' agents and the Jenkins master itself, and also interfaces directly to the Jenkins Java code. This way, the admin can execute calls to functions within the Jenkins Java code, for example, for debug, or to run actual code inside the Jenkins source code. This is a very nice feature, and we'll be exploiting it soon. We're going back to Shodan for this slide here. Internet scanners are an important part of any probing activity. In many cases, the Jenkins people webpage is available for read-only users. So we had a chance during the probing to look into some of the Jenkins installation accessible on the internet. The people's page includes all the users which have access to this Jenkins installation or infrastructure. Well, here on this people's page, we can already see something suspicious. Some of the usernames look misplaced, as in this example that we see here. Root is not generally a Jenkins username. So this makes you wonder. We'll get back to this point later on. So right now we've finished our probing stage, and this is to summarize it. Well, point number one, we've seen how XML files are loaded directly from disk into Java classes in an unmarshalling fashion. So the XML file is read in its entirety and becomes a Java class. We've also learned that config XML files are used in multiple places across the Jenkins file system. These XML files are used to configure Jenkins Java classes. The main config XML file, and this is an important point, contains the security on-off switch of the entire Jenkins infrastructure under the use security tag. We've seen that. 4. Each new user gets a new folder under a special username directory. And number 5, we've also encountered funny people behavior seen on our Shodan search, which we don't yet know how to exploit. Good. So now we're going back to some brief explanation about Jenkins logins. Every Jenkins user can log in using their username and password, and we've seen how that in one of the demos that we saw. And we can see it in this slide also. You have a place to type in your username and password. Another way of logging in is by using a machine consumable remote access API to almost all Jenkins functionalities. We're doing this by using a HTTP basic authentication with a user's API token. We came across the API token when we looked into the user's config XML file. The fact that every Jenkins user can authenticate using their password or by using an API token makes the authentication processes a little complicated and naturally requires a dual authentication mechanism. This dual authentication mechanism is implemented in a filter, a Java filter called Basic Authentication Filter. Why dual? Again, Jenkins supports two types of authentication. One is HTTP basic authentication, and the other is form-based authentication. The HTTP basic authentication is reserved for scripted clients. For example, as we said, bots impersonating human users to run scripts on Jenkins. While the form-based authentication is for humans to log in with their usernames and password, and this is done using the web user interface. Using the HTTP basic authentication, a client authenticates to the Jenkins master with a username and password or API token combination. In this basic authentication, the client's username and password or API token should be concatenated, base64 encoded, and passed in the authorization HTTP header as we can see in front of us. The Jenkins master authenticates the user against a user's database in case of a username password combination, or by comparing tokens with the local user's API token, stored in the user's config XML file in case of username API token authentication. So basically, we can issue an authorization request by using this curl CURL with authorization basic and this base64 username and password, and of course, the IP address of our Jenkins master. Okay, well, the next part is going to be a deep dive into the code. So again, this is our static code analysis, and we run this code that we see here by calling this curl, this CURL, this HTTP GET request. And again, just remember that we are not authenticated in any way, and we actually don't even know the password. So in the code, we've reached this basic authentication filter. And here, this basic authentication filter calls doFilter. As we can see here. And this authorization string is being filled up by the header authorization basic. This next command here that we see here, the descramble, takes the base64 that we see here and descrambles it or decodes it. And then we're looking for the colon, which separates the username and the password. And then we have the string username and another string for the password. Good. Now, the next stage here in the code is a call to get by ID or user get by ID. As we can see, only after get by ID returns, Jenkins calls to get the API token parameter here and checks if it matches the password that we supplied from our get HTTP request, from our CURL. So whatever happens before this compare here is completely pre-authenticated. Okay, so again, we call user get by ID with our username and another second parameter, which is true. This true parameter is quite interesting, and we'll return to it shortly. So, get by ID is called and continues by calling get or create. You can now notice that our interesting true parameter is now called create here. So get or create calls another get or create function. And here it adds another interesting parameter, return from get unsanitized legacy config file for the ID, which is the username. This is where everything gets really interesting. It seems that there was some Jenkins legacy file system that was used to populate the user's database. Digging in, we found two sister functions relating to this legacy database. So we have this get unsanitized legacy config file 4, which calls legacy file name of, and this legacy file name of simply returns the ID. Again, the ID is the username in lowercase. So whatever username we supplied via our curl, our CURL, this simply returns as lowercase. No sanitation at all. Good. So this would return Jenkins home and users and whatever username we have in lowercase. And it is appended by config XML. Let's have a look at our get or create. So here we are getting config file now for the ID. The ID is the username. This would return the sanitized version of our username. Again, it would be Jenkins home users sanitized username config XML. Let's have a look at what this sanitization is. So here we can see that if we supplied a username which has con, prn, aux, or a null, then this function would replace those with something less dangerous.
Okay, back to get or create. Now this gets a little tricky here. So we now reach the get or create sister function with the last parameter being the unsanitized config file. This is where things get really interesting. When an unsanitized legacy file exists and the legacy configuration file is not equal to the sanitized configuration file, we move inside this if clause. The next if statement states that when the sanitized configuration file does not exist on disk, Jenkins goes further to create a new sanitized directory for the user, and the unsanitized legacy config file is moved into the newly created directory. Moving the file explicitly means that the file is copied into a new directory and then deleted from the original directory. Again, this looks like some kind of user directory migration procedure that is executed before any kind of user authentication has been performed. This sounds pretty dangerous. Can we exploit this logic? Knowing that we have a config XML file in the Jenkins home directory that contains the Jenkins main security switch, we set out to check the code and see if we can somehow convince Jenkins to remove the main configuration file from disk. All right. Let's look into this flowchart and then analyze the code. We begin as an unauthenticated actor on the network and send an HTTP GET with simple authorization header with username, password. Our first checkpoint is testing whether the unsanitized config file exists. If there is no unsanitized config file on disk, then we simply do nothing. However, if an unsanitized config file does exist on disk, we move to the second checkpoint. Here, Jenkins compares the unsanitized config file class to the sanitized one. If they are not the same, that is, not having the same file name, then we move to the third checkpoint, over here. Here, Jenkins simply checks if the sanitized config file exists or not. If it does not exist, then Jenkins will perform the migration procedure we saw earlier, which will move the unsanitized config file to a new sanitized location. Let us check the flowchart with the username ... To do that, we prepare a base64 string in the format username colon password that contains the username ... and any password we would like. Next, we send it using CURL. So again, we use authorization basic as a header. Jenkins code will compute the unsanitized config file to be Jenkins home users ... config.xml, which is actually equivalent to Jenkins home config.xml. We know this file exists, as this is the Jenkins main configuration file we discussed earlier. So we've successfully passed checkpoint number 1. Jenkins does not allow the sanitized config file to have a ... in the username due to path traversal issues. So Jenkins replaces each dot with a string $002E. Therefore, the sanitized configuration file is computed as Jenkins home users $002E twice / config.xml. Obviously, the sanitized configuration file is not equal to the unsanitized one. We just passed checkpoint number 2. The third and last checkpoint checks if the sanitized file exists. Well, I don't suppose some Jenkins installation will have a user by the name of $002E, $002E. Well, we just passed test number 3. At this point, the Jenkins main configuration file, config.xml, the one that contains statements about the main security switch, has been removed by Jenkins itself from the Jenkins home directory. Note that Jenkins did not require us to authenticate to get to this point. This means that any unauthenticated actor with access to the Jenkins master can delete the Jenkins main configuration file and eventually, as we'll see next, gain admin access to Jenkins resources, secrets, and infrastructure. Well, I guess now is the right time for a demo. So we're first going to check and see if security is enabled or not. So logging in and clicking Manage Jenkins and then Configure Global Security, and great. The security is enabled. Good, we're now going to log out of our admin user and jump over to a bash shell. Here we are. Jenkins 121 is our Jenkins home directory. So we're changing into there, and the first file appears to be the main config XML file. Well, this is great. Next, we prepare the username password pair in base64 for the HTTP GET request. So we're going to use ... and, well, any password, of course. In base64, ... is the username, and don't have a password is the password. And next we're going to curl it with authorization basic header all the way to the Jenkins master. Now remember, we are not logged in any way. We're going to add the username password, base64, and the IP of our Jenkins master. Okay, that's it. Once we press enter here, a GET request would be sent to the Jenkins master, and the process we've just shown would be executed. As we can see, we've got an error. Funny enough, this is rather a good sign. Good, let's go back to the Jenkins home directory and check there. As you can see, the config XML file just vanished. But where did it go? So we can check the users directory, which holds all Jenkins users. And it seems that we have a new user called this funny $002e, $002e directory. And we want to look inside. So we're changing into the directory, and inside we have a config XML, which is, quite interestingly, the original Jenkins home config XML with the use security switch inside. But at this point, the Jenkins main configuration file has been removed from the Jenkins home directory by an unauthenticated user. All right. If you recall, the user module function getById we saw before was called with username as a parameter and another including parameter, which was set to true. That parameter we later found was called create, and it seemed like we could create new users in Jenkins Java cache, even though we were not authenticated to Jenkins. As we saw, the actual authentication check is performed a few lines afterwards. We also remember the funny usernames in our showdown scan, the root username that we saw before. Here, we see the getById function called with create set to true, which in turn calls get or create here, which eventually reaches this line here, and this line checks if either create is true or config file exists, and if, as in our case, the create parameter is true, the code would simply create a new user with the ID we supplied, again, before the caller is authenticated. Let's now see another demo. Okay, we are now preparing a new base64 basic authentication string with username attacker. And now sending that base64 string, again, there's no need for a password because we pre-authenticated, to the Jenkins master using curl. Right here. Good. So, although we get an error here of invalid password, the user attacker somehow got himself into the users list of Jenkins, the people's list. as we're going to see now. We're going to click the people's list here, and we'll see our attacker user that we just used, although pre-authenticated, now inside the users list of Jenkins. Now each user takes a certain amount of space in the Java virtual machine memory, and if the users have long names, the amount of space may be increased. By using the same curl command with very long usernames, we were able to crash the Java virtual machine due to low memory and force the Jenkins admin to restart the Jenkins server upon our will. Now, we've seen how the Jenkins main config XML file, a file containing the most important Jenkins security configurations, was moved from the Jenkins home directory to a new directory, effectively removing it, and how we were able to crash the Java virtual machine by filling up its memory with new users. So when Jenkins is restarted, it will be running in security disabled mode. This mode requires no authentication and considers any actor with simply access to the Jenkins master as an administrator. At this point, a sophisticated attacker can further exploit this situation to become stealthier. By reading the config file from the Jenkins home users $002E, $002E directory and making necessary changes to the files on the Jenkins file system, such as adding a new admin user or reading and decrypting the admin's API token, our attacker can copy the previously moved config XML file back to its original place. By doing that quickly enough and at the right time, the Jenkins master would be returned to its original security configurations, and nobody would notice the fact that the Jenkins master reverted to its legacy default, that is, security disabled, for a short while. This would be extremely dangerous for an organization, as it would make the entire attack on the network virtually undetectable. Good. So we are logging in as admin at first to see all the registered usernames in the people's page. Notice that there is no attacker username anywhere here. Now logging out. So this is the Jenkins master's IP, ends with 142. Let's see all the XML files under the Jenkins home directory. The first file here is the Jenkins config XML file, the main configuration file. Here is a small application we wrote to perform the systematic exploitation of the two CVEs we discussed earlier. So after we input the Jenkins IP and press the inject button on our little app, the application would send the .username curl to remove the config XML file, and then start bombarding the Jenkins master with new users, all until Jenkins collapses. Here, we're looking into to see if we have a config XML file in the Jenkins directory. Naturally, we don't at this point. So we are now bombarding Jenkins with new users at this point. And we are waiting for the master to crash, for the Jenkins master. So at this point, you can see that Jenkins seems to be down, Okay, it's not responding anymore, and actually waits for the admin to restart it. So our little app now says that the server looks down, and it is waiting for the admin to restart it. Let's have a look at the Jenkins log file. It seems that the reason for Jenkins to be down is an out-of-memory error. This looks okay. So the admin now restarts the Jenkins process. And Jenkins now says that it is getting ready to work. Now our little app notices that. And during this time, our app will inject a new admin user called attacker into Jenkins, since it is running in security disabled mode. And that's it. A new admin user is introduced, and the Jenkins master security switch is on again. So nobody would ever notice that we inserted our new user, admin user, into the system. Well, that's it. Thank you very much for being part of our journey.
And that concludes Nimrod's talk. We will be back in about 5 minutes with PayDay, Jackpotting Fortune 500 treasuries by Martin Doyhenard and Gaston Traberg. Don't go anywhere. And we are moving on to the last talk of this block. We will have 4 more after the hour break. The talk coming up now is PayDay, Jackpotting Fortune 500 Treasuries by Morton, Doyhenard and Gaston Traberg.
Hi, my name is Gaston Traberg. I'm going to be presenting this talk with Morton Doyhenard. We are security researchers in an Apsys company. We are part of the security research team. We used to work looking for vulnerabilities in Oracle, in SAP products. We used to contribute in some blog posts, in some online publications. We have made some trainings in some other conferences or present in some other conference too. So I don't know, if you want to know a little more about what we do in Apsys, you can visit on Apsys website. This talk will be divided in 6 different parts. In the first one, we will be talking about what an ERP is, what financial applications works, and then Morton will be presenting CCF vulnerability, the vulnerability he found, and Morton will be using that vulnerability to make a wire transfer, okay? Then I will be presenting the EBS payment vulnerability I found. I'm gonna use that vulnerability to make a check printing attack, okay? And then we will be presenting a conclusion of all this research. So what was what was we looking for when we start this research? When we start this research, we were looking for profit, but a lot of profit. And the first thing we thought when we start thinking about this, or the way we can get profit, was, I don't know, rob a bank, governments, casinos, retail, juries, any institution or company or whatever that can handle a lot of money. But the problem with all of these targets is that you can end in jail or death. Okay, so those were not a really good ideas. So when we continue thinking about this, we say, okay, why we don't just take one of those ERPs we used to research and try to go far, okay? Because ERPs are responsible to handle a lot of money in companies. So we used to look for vulnerabilities there, but that's all. We don't used to go far and look how you can exploit that vulnerabilities and take profit from there. So we start researching, basically thinking about that. But first, what's an ERP? When we talk about an ERP, what we're talking about? Well, what an ERP means Enterprise Resource Planning. What that means is basically an ERP is an application that a company uses to handle the resources, okay? But when we talk about resources, okay, we are talking about employers, clients, partners, products, right? But we are talking about money too. We are talking about financials of the company too. And when we talk about financials, we are talking about cash, okay? So ERPs are responsible to manage cash in big companies. And this is the interesting thing about ERPs. ERPs have special modules that are called financial modules. Those financial modules are able to, for example, make wire transfers, make check generations, or make prints of some checks, are able to handle bank accounts and a lot of things. They are able to do that because they have to be able to pay a supplier, a vendors, manage payment orders, and that stuff. So, because the ERP have to do that, ERP have to be able, the financial model have to be able to make that kind of bank operations, okay? So that's the interesting part of all this on what we are looking for. But what could one expect about those systems? Because are really critical. If they are handling thousands of millions of dollars of a company, they should be probably in a bunker inside, behind a lot of walls, under the ground, I don't know, in a really restricted place. But that's not really true. They are restricted, but in general, many of those systems are really exposed. If you, for example, make a request, make some queries looking for ERP systems in Shodan, you will find that there is a lot of systems there. So ERP systems are not just systems that you can access. They are vulnerable and they are really, really exposed to many of you, to any of you. Another interesting thing about ERPs is that the ERP systems that are in production are not always patched. Why? Because it's really dangerous to patch a system, ERP systems. ERP systems are systems that could be working for years. And when you have vulnerability patches, security patches, those patches doesn't guarantee that the ERP will continue working after the patch will be applied. So, it's not rare that companies prefer to leave the ERP working against to apply the security patches. So, that means that if you find an ERP, it's not rare that the ERP is vulnerable to all vulnerabilities that someone could report 1 or 2 years ago, maybe. Okay, so they are exposed to you because many of them are exposed to internet and they are vulnerable to. And it's not a misconfiguration that they appear in internet, because many of them appear in internet because they need to be connected to other ERPs that exist, for example, in other countries. For example, if you have a company that exists in US and you have another office of the same company that is in Europe, and that company have to make some ERP requests to the other, they have to be exposed to internet. Or those companies that have a lot of customers, or I don't know, there are many situations where ERPs have to be open, okay, to internet, because they could receive connection from anywhere. So that is why it's not a misconfiguration that ERPs exist open like this. Okay, but what happened with that open ERPs? Nobody hacked them? Well, that's not true. Some of them have been hacked, but the problem with that cases were that when hackers attack those systems and they gain access to those systems, they don't know what can do with those systems. And what they do, in general, they used to do the same that they do with any other common system. For example, mine cryptocurrencies, install ransomware, make that system part of a botnet, or make it as some kind of extortion. So, I'm pretty sure that they don't know how much money those systems are handling. And probably they get, I don't know, $1,000 of dollars, mining Monero, but they don't know that probably that system is handling hundreds of millions of dollars. Okay. So, and here is where we are interesting for. What we can do? Well, the idea of this research is to mix the security knowledge we have about how to attack an ERP, how to gain access to an ERP, and how can we go further and make a post exploitation of that systems. So the idea is to make not just attack the system and gain access, else try to make a post exploitation and take a lot of profit of that system using what we know about ERPs. So, okay, Martin will continue, and he will be presenting you what a little more details about Oracle EBS, because it's something we have to know.
Hello everyone, my name is Martin Doyhenard, and as Gaston already introduced us, I'm not going to do it again. Instead, I'm going to start talking about Oracle eBusiness Suite, which is the ERP we chose for our research. So a quick introduction to EBS. It's Oracle's main ERP software. It's entirely written in Java Enterprise Edition using Java Server Pages, servlets, and applets. It runs on a WebLogic server, which is nothing more than a web application server for Java. For storage, it uses an Oracle database, which is a well-known relational database. And to fix vulnerabilities, Oracle releases every 3 months a critical patch update, which is a collection of security patches for all Oracle products. And we chose EBS because it's one of the most used ERPs in the world, and also it contains all the financial applications and modules that we will be using in our post-exploitations. And before I show the vulnerabilities I found, I'm going to introduce you to the Thin Client framework, which is the API in where the vulnerabilities are present. So as I said, the TCF, it's an API provided to developers to build server-based applications by reducing the amount of processing at client-side. This is done by defining client-side and client and server classes that are similar to remote method invocation because they will share the same skeleton, and they must implement the TCF interface called proxy, which provides some methods that can be called by a remote client. So in an example, we can see that the TCF client object will call the read-sync method, and the framework will actually execute it at the TCF server object, which is the twin class, and returning the results back to the client. And all this communication goes with a TCF communication protocol, which is encapsulated in HTTP, using the TCF servlet as an entry point or as a port, like a network port. But before the client can use any of the TCF objects that we just mentioned, he must first establish a communication. And this is done by using a class called dispatcher. So the client will first create a client dispatcher with the information about the server, like IP address and the URL path of the TCF servlet. And this client dispatcher will perform a handshake through HTTP to the TCF servlet. And if this handshake is successful, the server will create a server dispatcher that will be binded directly to the client dispatcher. So the dispatcher can be seen as a socket, but it also stores information like the database configuration and the TCF object that will be used by the client. So let's see how the handshake looks like. It's a post request, as I said, everything goes encapsulated in HTTP, and it has the TCF servlet path, which is called APPS TCF server. It has a TCF session ID, which is an alphanumeric string that is chosen by the client and go through an header called TCF start. One important thing is that the EBS session cookie is also sent, which means that only authenticated users are allowed to access the TCF servlet. And finally, a hard-coded string, which is the handshake string that we found by reversing the EBS Java application. If the handshake is successful, the server will respond with a JSession ID, which is a Java session cookie that will be used in following request and will be used to store the server dispatcher just created. The most important class in Thin Client framework is the proxy interface. As I said, it's a Java interface that must be implemented at both client and servers. And it will be implementing 3 different methods. The getPureType method, which is the one that says which is the twin class. So for the client TCF client object, it will just say the name of the TCF server object. The readItem method, which is used for initialization. And this is because the server classes will be instantiated with reflection, so no constructor will be called. And by using the readItem method, you can emulate the constructor. And finally, a readSync method, which is a general brute post method that can be used for processing any kind of information. As an example, when a client wants to create a new proxy, he will just create the myClient proxy, which is the class implementing the proxy. And the client dispatcher will retrieve the name of the twin class by using the getPureType method. This will be sent directly to the server dispatcher, and the server dispatcher will create the myServer proxy, which is the twin class of the myClient proxy. And this will be stored as an object inside the dispatcher. So next, whenever the client desires to execute a method from myClient proxy, like readItem or readSync, the client dispatcher will recognize this and will ask the server dispatcher to execute this method and return the results. So now I'm going to start explaining the vulnerabilities I found in this framework. But the first thing that is important to notice is that, as I said, only authenticated users are allowed to use this framework. So it will be useful to find a way to bypass this authentication. As an attacker, we probably won't have an EBS session. If we send a handshake without the cookie, without the EBS cookie, the server will respond with an error saying that only authenticated users are allowed to use the TCF. And to bypass this, we had to look at the source code in the Java application. This is a pseudocode of the handshake that will be helpful for understanding how to bypass it. First, whenever a handshake request is received by the server, the TCF servlet will create a JSession ID, which is a Java session, that will be used for storage, actually for storing the server dispatcher that also will storing the TCF servlet objects, the TCF objects, sorry. Next, the TCF start header will be retrieved and a connection key will be created using this string. Now, the important thing is that the TCF start header doesn't need to be present, because if the get header TCF start method returns null, it will be just used as if it were an empty string. So it's the same to send the TCF start header with an empty string that don't sending it at all. Next, the read handshake method will be executed, which is just comparing the hard-coded string with the one that's been sent by the client. And if this is successful, then the servlet will create a new dispatcher, which is the server dispatcher, with the IP address of the client. And this will be stored, as I said, at the at the Java session ID. And finally, it will check that if the TCF start header contains the closed string or if the user is not authenticated. If any of this happens, then the session is deleted and an error response is sent back to the client, as we already saw. But what is really interesting is that, as I said, the TCF star header doesn't need to be present, and if it's not there, then the TCF star will be, or its TCF session ID will be considered as an empty string. But the problem is that when the TCF star header is compared with a string close, and if the TCF star header was null, this will produce an exception, because we are calling an equal method with a null object. And when this happens, the servlet will not raise an exception and will not delete the session, but it will continue because it's not being handled properly. So, as I said, if we send the handshake without either the EBS cookie and the TCF star header, the Java exception is raised, but we're still receiving the successful response with the JSession ID cookie. So this means that we have been able to create a new server dispatcher, and we have a TCF session that we can use to create TCF objects. Okay, so as I said, the important class is proxy, because this is the classes that we'll be using to execute methods in the server with the remote method invocation. And as we already have been able to bypass the authentication, now the attacker is able to create any of these classes and call any of the methods read item or read sync. So the idea was to look for the default classes that are already implementing proxy in the Oracle eBusiness Suite, and look for interesting actions such as command execution, database manipulation, or files manipulation, which would allow us to perform to look for vulnerabilities that allow the attacker to take over the system. And we did find many interesting classes, but we are going to focus in a particular one, which is called Server Postmaster. So the Server Postmaster, of course, implements the proxy interface and the read sync method. And it's one of the fewest class, or maybe the only class, that actually receives an array of bytes and operates with it. So most of the other classes will receive integers or strings or any other type of classes, but not byte arrays. So it was interesting to look why this is happening. And after reversing and understanding how this class works, we understood that actually an object is being serialized and then is being compressed using a zip method, and is sent back to the server, and is sent to the server. So when the server receives this byte array, it will decompress it and convert it into an object input stream. And this object input stream will then call the read object method to deserialize and obtain the new object, which in this case will be cast to a message class. By now we are able to deserialize any object we want. So the idea is to create a gadget, which is a chain of objects that, when deserialized, end up executing any interesting actions we already mentioned. To do so, we will send a byte array to the server postmaster, which will be decompressed into an input stream. The input stream will then call the read object method to retrieve the object sent by the client. And if the client sends a message class object, then the server postmaster will be able to cast it and call the root message method. And before I continue, I will explain what are messages in the server postmaster. The idea is pretty simple. Messages are objects that contain two attributes. One is service ID, which is an opcode, and a body, which is an object implementing the request interface. The request interface contains just one attribute, which is the service name, and when deserialized, the request will create a service using the service name and reflection. And this service will contain different methods that can be accessed through server postmaster and through the thin-client framework. And the method that will be executed in the service will depend on the service ID, which is an opcode. So if I send the opcode equal to 1, then it will create a request, which will create a service, which will execute the method 1. This means that we can execute almost any method inside a service or inside a class implementing service. So we started looking for interesting methods, meaning interesting actions inside those methods. And we found one, which is the static method respond from the single response service. And what makes interesting this method is that there is a concatenation, there is a SQL statement creation with a concatenation of the select statement and a variable called language. So if we could control the language variable, then we could exploit a SQL injection vulnerability, which is great. But the problem is that the single response service does not allow to initialize this variable. This is actually obtained from a session configurator, which is a session context. And also, we didn't find any request that is associated with this service. So we weren't able to call this respond method. So we start looking for different services that could call this respond method from the single response service. And we did find one, which is the FND message request and service. So when the message calls the root message method, it will deserialize the request of the body. And if the request is an FND message request, it will create by reflection an FND message service when it's deserialized. This FND message service can execute the method execute by sending the service ID equal to 10. And when the execute finish, it will call the respond method from the single response service. So by this, we are able to access this vulnerable code, and we might be able to exploit this vulnerability. But the problem is still we need to find a way to set this language session or this language from this session configurator. And so we start looking for different different services and requests that could be used to initialize this variable. And we did find one, which is the service called Context Bootstrap Service, which is created through the Context Bootstrap request. And it's a service for initializing the context and any other configuration from the server postmaster. So by sending a Context Bootstrap request, we can create a Context Bootstrap service through reflection. And the Context Bootstrap service will create a session using creating the display language or setting the display language. If we send a session configuration object inside the Context Bootstrap request, it will be used to create this session. And so we will be able to set the display language using this session configuration object. And by doing this, we can inject a SQL statement that can be used to exploit the vulnerability we previously mentioned. So this is a second order SQL injection. First, we will inject the string or the code. And this is done by creating a Bootstrap request, which will create a Bootstrap service that will create a session. And this session will be created with a session configurator, which can contain the display language. And after, we will use the FND message request to create an FND message service that will call the respond method that will execute the SQL statement. And by using some well-known techniques from the Oracle database, we can declare an autonomous transaction to execute any query we want. So, as we saw, this language was concatenated with a select statement, but by using the declare pragma autonomous transaction, we can execute any kind of query like an insertion or a deletion or anything that modifies a database table. So now we are going to see a demo of how we can exploit this to modify the password of the admin user. As I said, using these vulnerabilities, we are going to modify the sysadmin user password, which is the most privileged user in Oracle Business Suite. And first, we are going to try to log in using the password hacking the box Singapore 2020. Of course, this login failed because this is not the password. So we will start by sending a handshake without the TCF star header. this will produce an exception, but it will not be handled correctly, so we will receive the JSession ID cookie. And using this cookie, we will create the server postmaster object, which is the class that implements proxy. And now we are going to create the objects that will be deserialized by the server that will cause the SQL injection. First, the object generator jar will ask us for the username password for the username, and then the new password that we want to set, and the file name that we will save these objects. And now, with a Python script, we are going to send these objects to the server so that they get deserialized, and we can change the password of the sysadmin user. The Python script asks us for the victim host, which is paydayvs.com, the object file name that we just created, and the JSession cookie that we obtained from the handshake. And now, when we try to log in, we see that we successfully log in with the sysadmin user. Using these vulnerabilities, an authenticated attacker will be able to obtain full control of the Oracle eBusiness Suite applications as well as the Oracle EBS database. But the question now is, if phase 1 is hacking EBS and phase 3 is obtaining profit, then what is phase 2? Meaning, if an attacker is able to control an ERP, how can he make real profit out of it? And to understand this, we are going to present the ERP payment modules. These modules, which are present, for example, in Oracle Business Suite, provide create, read, update, and delete operations on vendors, invoices, and payment orders, which organizations will use to pay to suppliers. They also store financial information such as the bank account data, the payment methods supported by the organization, and finally, configurations to make the payments effective. So the way they work is, whenever an organization needs to pay to a supplier, he will first create this supplier in the Oracle eBusiness Suite application by providing bank data, such as the bank account number and the bank name. Then an invoice will be created for this supplier, which will contain information about how much money is going to be paid to this supplier and why this money is going to be paid for. Next, a payment order will be created for this invoice, which will tell how this money is going to be sent to the supplier. So, for example, the payment method can be an electronic fund transfer. And finally, a payment document will be created from this payment order that will actually move the money from the organization to the supplier. So, in most companies, there is a payment day every once in a week or once in a month. So, when this day comes, the responsible person will create a payment close request to the EBS server, and the EBS server will generate an EFT file with all the information about the transaction that must be performed by the bank to send the money from the organization to the different suppliers. The EBS server will then send this EFT file through a payment transmission protocol or using any batch process to the bank. And the bank will make effective all the payments by moving the money from the bank account of the organization, of the company, to the different suppliers and vendors. This is how an EFT file looks like. It contains a lot of data, but we only care about some of the fields. First, we can see that there is a payment amount. The last two digits are just for cents, so in this case, it will be sending $1,086 to the bank account number that is described at the right, and the destination bank account name. And finally, we have the branch name of the destination account that can be obtained just by calling the bank and asking which is the number of the branch. So, after seeing this file, we need to know how to modify this file in order to create a new file that can be used by the bank to send money to wherever the attacker desires. So again, if phase 1 was hacking EBS and phase 3 was obtaining profit, then phase 2 is of course modifying the payment data in the database. Again, using the vulnerabilities we already described, the attacker can send a TCF payload to the EBS database and modify all the information about payments, about invoices, and about suppliers. Now, when the payment day comes, the responsible person in the company will send the payment close request to the EBS server. And the EBS server will generate the EFT file, but instead of using the real information of the suppliers and the payment orders, it will use the information that the attacker has injected in the database. So now the attacker is able to control the EFT file, and when the EFT file is sent to the bank, this bank will make all the transactions that the attacker wants, so he can send any money from the company to his bank account. So we are going to use a Python script to exploit the vulnerabilities we already found, and by doing so, we are going to modify the payment orders that had already been approved, so that when the EFT file is generated in the PayDay, the attacker can control all the transfers that are being performed by the bank. So the exploit is called EFT exploit, and as argument it expects the EBS target. So in this case it's PayDay EBS. And it will first verify if the target is vulnerable, and if so, it will offer us to modify the information from these payments. So first, it will retrieve all the payment orders that had already been approved. And remember, these payments that we are going to see had been approved by many actors in the organization. So when the payment day arrives, nobody will double check them because they are considered to be alright. Nobody should be able to modify them. We are going to modify the Hacking the Box Singapore vendor, or the payment for this vendor. And so all the information from this payment will be retrieved, and the script will ask us if we want to modify it to obtain profit. We will say yes. And so it will ask us the new bank account number. Let's provide one. A new bank name, which is attacker bank. A new bank address. This is just for in some cases, the ERP will check if the bank address corresponds with the bank name. And finally, a bank branch number, which in this case will be 111. Now, when we provide all this information and we enter to press enter to start the exploit, all this information will be modified in the payment order, so that all the payment that's going to go to the Hacking the Box Singapore vendor will actually go to our account. So in this case, it will be $213,800. Finally, it will ask us if we want to erase all the logs from the audit tables. And of course, we will say yes. This is because we have when we exploit the vulnerabilities in the thin client framework, we are actually exploiting them with the APPS user, which is a really highly privileged user in the database. And finally, it will ask us if we want to create a trigger in the database so that when the PayDay arrives and the EFT file is generated, all the information from this payment is changed again to the original one, so that no one can know what happens. It will create this trigger, and the attack has been successfully completed. So we created a batch process in the EBS server that will move all the EFT files from the EBS server to the bank server. The bank server has an FTP server which holds all these EFT files. So let's log into it. We will be logging using the EBS user. And let's look for the EFT files. We see that there is just one. Let's retrieve it. And let's look at the EFT file that was generated and sent to the bank. And as we can see, the payment for Hacking the Box Singapore now has the bank account that we provided, which is 0123456789. still the same amount of money. It's going to be sent to the attacker bank, which is at 007 PayDay Street. And the bank branch number is 111 as we provided. So this means that when the EFT file gets to the bank, all this money is going to be sent to the attacker account and nobody will ever know how this ever happens.
Okay, so let's talk about an e-business suite payment module. The e-business suite payment module basically is a module responsible to make the interaction between the EVLs and the banks. Okay, for that, this module handle many protocols like FTP, HTTP, AS2, that is a proprietary protocol, and this module is responsible for handle requests from provider, customers, and that stuff. All that from using HTTP for that. Okay. And for example, when a provider wants to make or a customer wants to make a payment to the company, he make a request, okay? And this module is responsible to take that request and make a transaction with the bank. The fact that this vulnerability we will be talking about exists in the payment module doesn't mean we have extra credit for the impact, okay? We don't have extra impact because the vulnerability is in the payment module. It's just coincidence that we are talking about how to attack the financial system, and the vulnerability exists in the payment module. That doesn't mean that if the vulnerability was, I don't know, in a human resources module, that vulnerability doesn't work for this. It could be the same. So how we interact, how can we do, or what a user of this module interact with this module? The first and easy way to do that is make a request, an HTTP request to that module. Those HTTP requests have a really simple format. Those requests have to be a post request to the resource you are looking there, the IVA transmit servlet, okay? There you have the post request divided in 3 different parts. In the first part, the blue one, you have 2 headers we are interested on. The first one, OAPF, del, and len, this crazy name for a header, that header will contain the length of the green part of the request. And the second header will contain content length, that is the content length, the traditional one, that will contain the full length of the post request, okay? What the green part of the request mean and what the orange one part means. The green part of the request will contain an XML file that is modeling a method call inside a class we will specify and the parameters we want to call, okay? I will be back over this later, so don't worry. So, but basically we have a call function inside the server. We have to model using that XML. It's like SOAP for those guys that know what SOAP is. It's like SOAP, okay? You are modeling as a call to a method, a call to a method of a class. And the orange part of the request will contain an extra payload that we will be sending to this method we are calling. So let's analyze the XML we are sending. The XML that we are sending have to have this form, okay? We have 3 different parts we are interested on. The first one is that the first 2 ones, the blue ones, are the code package, that is the name of the class we are interested on, and the second one is the entry point, that is the method we will be invoking of that previous class. In this case, it's like we are calling method to call of the class to use, okay? The third tag we are interested on are parameters. Parameters, you can find a lot of them that depend the method you are calling, and basically you have the parameter name and the parameter value that are the parameters you are trying to pass to the method. But it's not that you pass them like the traditional way, okay? Because you don't have remote command execution, code execution in here, because what the servlet is doing is call the method you are invoking, but using the parameters, passing the parameters as a dictionary, okay? And the input stream that is the second parameter you will be sending to that method will contain the green part that we have sent with the request. You remember the orange part, the orange part of the request. So we will be basically with that XML, we will be executing the method to execute method of the class to execute, and passing as the first parameter a dictionary containing all the parameters we have listed in the different lines with the tag parameter, key and value, and in the input stream will be referencing all the orange part of the post request, okay? So, what classes we could use here to make transactions, to make those invocations? The interesting one, or the class we will be looking for is file dump function, okay? This class is responsible to dump files inside the EBS system. For this one, I will be calling the transmit method that is responsible to transmit a file to the EBS server. The parameters I have to pass to that transmit method in the dictionary are filedir, file name, and transmit ref. The filedir is the absolute path we will be using, we will be working on. The file name is the file name of the file we will be using and where we will be writing the content of the extra payload. And transmit ref is the relative path relative to the filedir path that we will be using. So the full path where we will be writing the servlet, we will be writing the file in the EBS server is composed like in the bottom of the slide, like filedir plus the transmit reference plus the file name, okay? So what I did to exploit this basically was use the class. For class, I use file dump, it's the same, method was transmit, that's okay. And for parameters, for filedir, I use the root file system, okay? For file name, I don't care, I just put an empty string. And for transmit reference, I put the full path of the file I want to write, but without the slash of the root file system. And that's all. You can write files inside the EBS system anywhere, even you don't need to make a path transversal or similar. It's just there you have a vulnerability. All you need to write files inside the EBS systems. So you can see how simple could be some vulnerabilities there. Okay, so we are able to write files in EBS, but we need command execution there. So what we can do? What could we convert this in a command execution? The first thing you can do, or you can try to do, is create a web shell, okay? Write a file someplace. But it's not really easy to write files in EBS or in other ERPs, because they used to compile them, all the resources. When they start, they used to compile the resources and present all the resources already compiled. So when you when you modify one of those resources, you have to restart the systems to make that change reflect into the website, okay? So that is not a really good option. What I found is a CGA file in EBS that I don't know, I'm pretty sure what that Perl script do. That is there, I don't know, that doesn't matter. But when you overwrite it, the changes are reflected in the website. So I decided to use that Perl script to write my web shell. So the problem was that it was a long time until the last time I wrote something in Perl, so I had to custom my archaeologic custom, and I have to address my archaeologic custom and start writing some Perl web shells. So with that web shell in Perl ready and working, I was able to make a post request to upload it and overwrite this Perl script, right? And well, the request I had to do was basically like that. A post request to the IB transmit resource with the OAP headers and that stuff. An XML, the green part of your request, an XML referencing the class we were talking about, but this time referencing this Perl script, okay? Referencing this Perl script, the absolute path of this Perl script. And in the orange part of the request, I append my Perl script, right? And just make this request. With that request, with that authentication, I upload a web shell that I can request and I can execute, just making the request at the right side of the slide. Just make a request to that Perl script with the CMD parameter and the ID command and execute the ID command. So let's look the demo to show you how this works. Okay, so now we are here with DBS. We want to upload the web shell, the Perl web shell. This is the script we want to override, okay? There's a common error. This is the login we are not gonna use, but this is the same script. We are gonna use verb because it's easy to make this attack. And here's the attack we want to do. As you see, here's the class. This is the class we want to call. This is the method of the class, the values, and here is the full path without the root path at the beginning, the full path of the file we want to override. And at the end of the body of the request, we have the web shell script we want to send. So we execute the request. You see, we have no session tokens and nothing that mean an authentication. We have no authentication there. So if we go back to the script, the Perl script, and we run it again, we will see no error. If we try to execute a command like ls, we will see the name of the script there. The result is in the headers because WebLogic is appending more headers after the script execution. And if we run, for example, ID, we will get the ID of the Oracle EBS user, okay? So we have the web shell really already working, and now we are going to explain how the check printing attack works. The check system is really simple, and EBS to compose checks use two steps. In the first one, EBS take a template that will be used to compose the check using the database information, and then in the second step, EBS already have a file that will be with the check file that will be sent to a printed queue, and that's all. In general, EBS don't use it's a really simple process, as you see, and it's really common that EBS don't have the printer installed in the same place as where the system of the EBS system is, okay? For example, you can have an EBS in US and a printer in China, for example. It's really common that. So what we need to print a check, right? First, we need the template, the template of the check we want to print. For this, it's more useful it's more easy for us to take an already existing check in the system. In EBS, there is a cache for the already generated checks where we are going to use to take an already completed check and modify it. This is because complete a check is not a really easy process. There is some information which we have to take from the database, and that's not easy. In the second step, we have to recognize the printer we have to use for checks. And this is not a problem too, because in general, EBS, the printers that will be used for checks printing, have a really common name containing like something like, I don't know, check printing or something similar, because are really specified, are printers that are used just for that. So, that's not a problem too. So we have the two things, we need to print a check. An already completed check looks like this. As you see, it's a really simple format. It's a just text format. You have all the information the check needs, but the problem in general is the layout. We need to respect that layout to make up a correct printing, okay, and print a valid check. And that is what we are interested on. This is a real example of that. So let's make the demo, okay? Okay, so we already have a web shell running in EBS, and what we want to do now is the post-exploitation. We want to recognize a file, recognize a check file, download it, modify it, upload it, and send it to the printing queue. So let's do. I upload a really simple script to receive connections from my desktop, because it's easy to execute commands this way and not using the web shell. The web shell is like really hard to use. So netcat to the PayDay server, EBS server. Sorry, netcat PayDay EBS.com port 1337. Okay. If I check, I am in. There is a lot of files because this is we are working in the reports directory that have a lot of files, not just checks. So the first thing we have to do is recognize one already generated check. I already did it because it could take too much time. So I rename it to check that out. Another thing that I am doing is using a plain text check. This is not the common format. The common format used to be PDF or RTF, that are the EBS formats that EBS used to use. But because this is the most easy to edit file, kind of file, I choose this one. So to export this file, I'm gonna use base 64 command and the name of the file. I'm using this. Some of you maybe are asking the questions why I don't just edit it in the server, right? Why I don't just use BI and edit it? But well, that's because I want to respect the full process. If in this case, I'm editing a text file, but if I have to edit a PDF file, probably I have to download it and edit it with a more complex tool and then upload it back. So I want to respect that process. So base 64 to decode it, and I'm gonna redirect the output to test that out. This is the output. Control D. So here we have two files. The other file, Gaston.out, is the same file that test. If we check test.out, we're gonna see that is the file that we have in the EBS, the check file. If we use the same with Gaston.out, we're gonna see that it's the same file but modified using my information. So Gaston is the file we are going to upload now. Gaston.out. And I'm gonna dump this file to the EBS server using the same command I used before. down to set that out. And Control V, Control D. Okay. Here I disconnect because my shell implementation is .com, but that is not a problem. Okay, we are back. So we have the already modified file. So the only thing we have to do now is send it to the printing queue. And to do this, we just have to do LP and the name file that we want to print. That is the check. Okay. Before do that, I'm going to say that in this EBS server, we have just one printing queue configured. That is a Linux machine I have in the next room. This EBS is in Amazon. So basically, when I run the command, this printing process will start from Amazon, but will end in my next room. In the next room, you will see in the other square of the slides, that there is a printer, and you will see the check going out from there. So let's start. I'm gonna start the command, and I will go to the next room to continue the presentation there. I don't see if you. There you have. That's the result. That's a real check. So conclusions. We have 4 conclusions for this talk. In the first one, companies fully trust in their ERPs. If companies don't really trust in ERPs and they don't ask questions about if the information that ERP is generating is true or false, or if really is real or not, okay? In second, when critical software is compromised, functional controls are useless. This is because, well, you are controlling all the system and functional controls will not do a lot. And all software with new vulnerabilities, deserialization everywhere. This is true because, well, ERPs in general are really old software. They have really common vulnerabilities, but the new ones are really hard, okay? New kind of vulnerabilities that deserializations are a problem in these systems because those are things that they were not thinking about when they developed those systems, so are really critical in general when you found some of that kind of vulnerability. At the end, if hackers improve their post-exploitation, the end is near. And that's true because until today, hackers don't know how to make a post-exploitation of the systems. And that is good for companies, but how much more time will pass until they start learning how to make a really good post-exploitation of those systems? So thanks, Guy. There you have our emails. Any questions you have for us, you can write us. And thanks to Look this talk. Bye.
And that concludes the talk. We are going on a 1-hour break now, and after that we will return with the Fragile Art of Edge Computing Walk Through Access Control Systems by Philippe Lin and Roel Reyes. We hope to see you then. Okay, it is 7 o'clock in Singapore, and we hope you have enjoyed your dinner break. We are continuing here with our next live talk by Philippe and Roel Reyes, the fragile art of edge computing, walk-through access control systems. Keep in mind this is a live call, so if you have any questions for Q&A, put them on Slido or ask them in the Discord channel, and at the end of the talk I will be able to relay them to Roel and to Philippe. Roel and Philippe, take it away.
Thank you. Thank you, Cooper. Yep. So welcome to the session of the fragile art of edge computing, walkthrough access control systems. My name is Philippe. I'm presenting along with Roel Reyes. This research is delivered by our colleagues, JunWei Costoya, Vincenzo, Ciancaglini, and Dr. Morton Swimmer. All of us work in forward-looking threat research team in Chen Micro. So feel free to drop us questions on HITB Discord channels. My colleagues and myself are answering the questions here. Okay, so edge computing does not come out of blue. The arrow above illustrates the history before edge computing. And for example, we had standalone nodes were later connected with LAN, local area network, and they were gradually connected to the internet, the cloud, and then back to the powerful on-premise nodes, that is edge computing. And you could say edge computing is the history repeating itself because the edge nodes are now responsible for protecting your data, just like 2 decades ago. And vendors chose different types of edge computing models. For example, industrial control systems has improved the cellular routers to edge gateways, and the fleets shop floor control uses edge gateways, and for facial recognition systems that needs higher bandwidth and faster processing speed, they chose edge servers. And if you are using a very powerful tablet, then that's a powerful IoT lens per se. And using edge computing nodes means there are several advantages. For example, that's on-premises data acquisition, which means that the data is collected on the edge and it doesn't leave the premise. For the applications such as smart healthcare, the data should not leave the hospital in order to comply with HIPAA. That's why edge computing kicks in. And it provides some sort of resiliency. For example, you want the system to be still running, even if the network is temporarily not accessible. And resiliency means that the edge node gateway servers are autonomous to some extent. They have lower latencies since the data are processed on the edge, and since there's no more traffic back and forth to the data center, that means less traffic and faster network traffic. So here's also where we want to exploit, because some sort of resiliency means that you have to trust the edge nodes to some extent. And this page gives you an overview of the edge computing architecture. We have copied it from a white paper. The link is given at the bottom of the slide. So on a normal scaled system, you might find a 3-layered model just like the one on the left. And on a larger scaled system with more nodes, that will be a 4-layered model, just like the models on the right. And you see like smart assets, smart sensors, smart controllers, actuators at the very bottom. And the data they have collected is sent to a smart gateway or edge computing node in the middle. And the matrices are some control data, some audition data, logs are sent to the data center. That's on the very top. And 3-layer model or 4-layer model, they are not pretty much different because it's just like a horizontal expansion of the system, just to handle this a little bit complexity introduced to by more nodes. So So what has motivated us to look at access control system? So shortest answer is that our company was testing such a system in our offices. So you see, it's easier to acquire the devices. Somebody has bought them for us, and we don't have to pay extra. And so before COVID-19, people were only testing the edge computing system for the future. But since the breakout of COVID-19, body temperature sensing is more and more important, and it's advertised even as safeguarding the city. Just like the screenshot you see above, it shows a facial recognition system that's used in Beijing metro system. It does some sort of facial recognition as well as measures the body temperature on the fly. And a little bit disclaimer is that we did not test this product. This picture is there just for a very good example.
Hi everyone, this is Roel. From this research, we tested 4 devices and compared its security and communication protocol. So the first device that we had our hands on was the ZK-Teco. So that's the Face Depot 7B. We have this in our Manila office, basically. So ZK-Teco is one of the biggest Chinese vendor that supplies access control devices. It's basically sold 3.8 million just for the fingerprint reader alone for last 2015. It's an Android-based camera as well. It uses MACD algorithm and can store up to 10,000 images, basically. It also has the feature of checking liveliness, and it can communicate with different I/O relay like the Wagon RS-232 and RS-485. During our research, we were surprised that the only face image are stored and not the actual metadata for the facial recognition thing. The next device that we had access was the Hikvision. It's a DS-K1T606MF. So it's a combination of facial recognition, fingerprint, and RFID checker. So Hikvision is one of the biggest vendor in the world that supplies camera and access control as well. It uses a customized Linux operating system. So basically, we managed to like check the device, access the communication in between. But since we are still doing some decoding for the actual binary data, so we were not going to talk about this device on this presentation.
Okay, and this one is a Telpo TPS 980. Actually, we bought it for fun. So Telpo TPS 980 is Telpo is a partner of Alibaba. They provide a facial recognition service for a point of sale terminal of Alibaba shopping centers, and it uses ArcSoft facial recognition algorithm. It's a very common algorithm used by many devices. It's Android-based camera, and actually that's a standalone camera itself with an optional cloud service for $10 per device per year. And by standalone, it means that this camera has this tablet has a camera attached, and when it does the facial recognition, it matches the database stored in the tablet. And when it matches one face, it opens the door by shorting the digital output and input pin. So for bigger businesses, there's also an SDK only version sold to the customer. So for this algorithm, one has only to pay $38 and it has LTE and the vegan and the digital I/O interfaces. So this one's really cool. And then we have a product from vendor A. So this product is bought by a very big Chinese company. It's actually one of the top 3 facial recognition companies in China. It's marketed as a residential access control system. So the use case is to deploy it in the basement of several apartment complexes. And it has a very high throughput. And when someone passes by, it takes a snapshot and send it back to the edge server for audition. That's why it needs an edge server instead of just do everything on the tablet itself. We have bought the on-premise version, which means we have paid more money, and the on-premise version has brought us some really good advantage of having HTTP instead HTTPS connection. And it works with network relays. So it's network relays that you can buy on the market.
Okay, so let us talk about ZK-Techo, our findings with the devices. So ZK-Techo device is based on Android OS. Basically, it's Android 5.x Lollipop. So there's a USB port on the lower part of the device. Basically, it's used for importing and exporting records. You could also do ADB connection on the USB, but unfortunately, we didn't do more testing on the ADB connection, but we concentrated more on the communication protocol. In this slide, it shows us a general infrastructure setup of ZK-Techo. So user register from the device updates or sync its information on the server, and then the server syncs the information across all the other devices. So information like password, PIN code, crop images, facial biometrics, and door access are synced on those devices. From our test point of view, we just used the user registration device and the server itself. So what are the things that we've done? So in the initial test, what we did was capture communication protocol or packets from the device and server. So first, we used MITP proxy since we assumed that the communication was HTTPS, but unfortunately, it's not. It's just using HTTP, and it's in plain text. So second, we use Packet Squirrel to monitor a data traffic. So we embedded the packet sniffer on the server, on the device, which communicates on the server. Okay. So lastly, we perform Wireshark on the test environment we have. So from the collected packets, we analyze the protocol and data or the payload. To our surprise, things are not encrypted. So everything is in plain text. So what's next? So the important part there is you have to first identify the serial number of the device. So on the communication or on the Wireshark or on the packet itself, you could identify that. Looking at the image on the slide, you have their SN with the serial number on it, and a token, which is used by the communication from the device and the server. But unfortunately, you could just use or reuse the same token. And we've identified two communication: server going to the device, and then device going to the server using port 8088. So let's try to check the findings that we have by using or presenting some demos. Okay. So on this first demo, let us try to add a new user with normal permission using a simple curl command. Okay. So looking at the payload, it contains table UI, UID, card number, PIN, password, group, start time, end time, name, privilege, disable, and verify. So those information, you could actually put anything on the UID with the just numbers on it. PIN is something like the ID identifier for the user. Password is in plain text, so I just put there 1, 2, 3, 4, 5. Group 1 is the default. Start time, end time, 0 is the default. Disable and verify is 0 as the default. Privilege 7 value means it's a normal user. Okay, it's a normal role basically. So let's look at the demo. So here on the demo, if you look at the UI, there's one personnel, Angel, And then when I execute the curl command, then go back to the UI and then refresh, then there you go. You have 1111 bogus name with a role of ordinary user. Okay. So from there, you could actually create any user with any name, or if you identified some legit name, then you put that there. Well, anyway, you were able to like create the user, but it's just a regular user. Can we create an admin? Yeah, we can. So adding an admin or modifying a existing user with an admin privilege, all you have to do is just change the privilege to 14, and then do the same execution, curl command. Let's look at the demo. On this demo, I've just created a new user basically. So same payload except for the privilege, it's 14. It means it's administration role. And then try refreshing the UI, and then there you go. Checking the operation role, it's administrator. So that's easy, right? Now we've created a user with an admin account or admin role. So still it's look like a bogus account. So we can actually insert a user profile. How do we do that? So by changing the query parameter from user to user pick and replacing the payload information. So here's the payload information. So there's the table name, user pick, pin, which is the pin number that we used a while ago when creating the user. Size is the actual size of the binary file or image. Content is the base64 conversion of the image. So you might ask if there's a resolution or size limit on the image. To answer that, frankly, I haven't really tested that. All I did was use the one I've seen on the packet sniffer. It's 720 by 1284. That's the size. So let's try this. So looking at the bogus profile, that's the avatar, my avatar. So let's try changing it into a more realistic user profile. So here's the curl command with the payload. After executing, let's try to refresh the user UI and then look at the new user profile. So that's it. It's a user profile of one of our colleagues. It's Vincenzo. So we have the profile, the account, the password. So can we use this on the device? Well, yes, we can. If the server actually finish the sync up of the information from the server to the device. But we don't have the facial recognition information. So how do we insert that information? So from here, we could change the bio photo. Well, bio photo means that the facial recognition schematics or the information. Like what we said, we're really surprised that it's not storing the actual schematics, but it's storing the image itself and then perform the algorithm. So here, we use the bio photo table name, okay? And then here's the payload. We change the table name to bio photo, use the same pin. File name is the pin with the .jpg. Type is 4, which means it's a JPEG. Size is the actual size of the binary file. Content is the base64 content of the image file. So I've tried testing a couple of images while I'm doing this research. So I've tested the Totoro image, a sculpture image, and Jollibee. So out of 3, the only image worked was the one in the middle, the sculpture face. How come? So it's actually checking the eye formation, the cheek here, and the side of the nose, and this part. So it's trying to check that if it's a real person or not. Well, while I was doing that, I printed out this image and then tried it out. It didn't work. So basically, the liveliness algorithm of the device is working. So let's see a demo. So here, let's check on bogus account. So we have we don't have any facial picture registered, right? So let's try executing the same curl, just replacing the payload and the table name. So there, and then let's wait for the server to actually updates its information. Well, you could actually see there that there's none yet. Okay, so there's one. So it's a little, that particular icon there. So let's try accessing it and view the face picture. Okay, so I did that, right? So it's the same. So what's next after this, right? So we could actually use this and then update the device, and then you could use your image and then enter any room in a company or in an office. Oops. Okay, so there are other findings that we stumbled while doing this research or doing the packet analysis. So we were able to like get some harvesting of the user information, user photos basically. So just using the URL provided on this slide. So the server and the IP of the port of the server, and then upload pers, user face, and then pin. Just replace the pin with the ID that you could, or just a random number, and then you can actually download the actual file or the actual image. So let's look at the demo here. So let's try, I was accessing the server UI, and then check how many users I have, like 2. So I have the Angel and Bogus. So I'll try to access the pin for Angel. And there you go. So you could actually create a bash script that will scrape all this information. So what else? You could also do user data exfiltration. It happens when the server or the device sync up on each on the client or the server itself. So here's the packet example. So you can see there that there's the pin information, the base64 content or the image, the bio photo that's used, and the authorization. Okay, so you can actually get the name, pin, user image, and facial biometric image. So we've done the device client to server vulnerability or exploit. So here we'll be doing server to device. So what we did, we've created 2 scripts which performs the following. One is it creates ARP poison to acquire the server IP. Second, it replicates the communication of the server to the device. So basically, it sends commands to create user, make it an admin, change the biometric, facial recognition, schematics, and that stuff. So here's a very nice demo about it. So here, you can actually see that I've created a demo account, an admin, without the facial recognition. So looking at it, I've just added the PIN code so that I could access the device. So that's the user management. So only have like 1 account here. So that's my alias. Okay, now I'll be assuming that we already gained the server IP by executing ARP poison, since I'm doing isolated network test here with static IP. So from this script, I've executed the zktecho.py, created an ID 97601 and name, which is I'm just using my name here, and then execute. So it's started to like replicate or create a flash server using port 8088. Since the device is broadcasting the communication on the server itself, so everything starts to communicate. So it triggers the communication the device, and it creates all the necessary information or all the user information required for the device. So looking at here, we can identify that it was successful by looking at the return code 00 and the command. That's delete, update, update, and update. Okay, so after doing that, I was trying to check if it worked. So let's try. Okay, it was successful. I was able to create my own account. So am I an admin here? Let's try. Okay, trying it again. All right, there you go. I was able to access the actual device and created my account with super administration role. Okay, so it's that easy basically. So let's try if the password was also working. So just enter the PIN number. That's 1, and then password is 1, 2, 3, 4, 5. All right, so it worked, right? So you could use the PIN number or the password, or even the registered facial recognition image. So to cut it short, our findings, we can add user from server side and device side as well. We could change user privilege, we could change user facial recognition data, and we could obtain user information. And also we assume that this kind of vulnerability exists in other vendors similar to ZKTecho.
All right, thanks, Roel. So the next one we have on the list is the Telpo TPS 980. So actually, you can find this product on AliExpress for something around $600. And in this section, we are talking about the optional cloud service that is licensed for $10, $10 per device per year. And without the cloud service, users can buy a $38 algorithm license to write their own Android application. But it's cheaper for a big company to write their own applications, while small and medium businesses tend to buy cloud service. And this one is the back of the device, and we see a slot of SIM card here and a bunch of cables, cable with like power, digital I/O, vegans, and you may have not noticed it, but the key to everything is actually printed on a label. So let's zoom in. The label. Okay, so that is the serial number. And with the serial number, you can access everything on the cloud service, just like add a user, delete a user, change admin password, change pictures, make fake attendance logs, dump the user DB, and download the pictures. And however, we want to express our appreciation that actually on the device, the HTTPS is on and the server certificate is checked. Therefore, we have once tried to use man-in-the-middle proxy to do a man-in-the-middle attack, and we have failed miserably. Without adding a fake CA for man-in-the-middle proxy, and that's not easy since Android 7. It's not possible to do such an attack. So we think this is a good practice delivered by the vendor. And apart from the HTTPS secured by Novate library, actually the vendor have used the ProGuard to obfuscate the APK. So it brought a little bit difficulty for us while we're doing the reverse engineering. The only thing they forgot to turn off is that everything is logged in great detail, just like the picture, the slide that you see here. For example, when someone draws near, you see the log that someone comes and with its names. And it shows the serial number, the group ID, the access token, everything you need to play back or do a replay attack. And it even shows the HTTP post URI so that you can try to think about it, and maybe we can pretend we can forge the client itself and hack the server. So actually, this gave us a very good idea so that if we cannot forge the server, we just forge the client and dump everything. And again, let's recap it. This is the access token on the back. Sorry, this is a serial number printed on the back, and with the serial number, you can get the access token. And with the access token, you can just log into the server and do everything. We have noticed that the client secret is always the same, but the access token changes every time. The expiry time is about 1 hour. We cannot impersonate the server, but we can impersonate the client. And if a guest is registered in the system, we can actually get the guest's QR code and use a QR code generator. You're able to print yourself a badge and just print the badge and log in. And the faces are downloadable with HTTPS GET. So it's a kind of security by obscurity. Let's see a demo. So here we have obtained the serial number from the back of the device. Then we just call the API and get a secret and the device password. And you see here, you get the client ID, client secret, which doesn't change anyhow. And you use the client secret to get access token. The access token is here, and it will expire in 1 hour. So once it expires, just come and grab it again. Then with this token, you can tell the backend server that the device is going back online. And you see the code 100, which means it's okay, it's online. Then here you dump the guest users. You get the name, you get the expiry time, the mobile number. So I'm pretty sure it violates the GDPR here. And the QR code. This QR code, just dump it to QR code generator, and you can print yourself a badge. And here you see how to list deleted users. Even if the user is deleted, you can still retrieve it back from the database and get the, for example, get the faces, get the mobile number, get the names. And even though there is a hash that prevents you from brute forcing, you can just download it, download the face. And with this command, you can add a fake attendance record. And take a note that the date that we have presented here is June 22nd. We will see it in a bit. And with the command, you can simply list all the employees in the database. We have 13 employees, and we can even add a user so that when I present in front of your factory, in front of the door of your factory, I can just walk in. Okay, so let's log into the backend, and actually, this password is not the password that you have obtained anywhere else. And you see the June 22nd. This is the fake attendance record that we have just added. And all right. Next slide. Yep. So for the convenience and for sake of to make everyone happy, we have written a retrieve employee pictures.py that logs automatically for you and dumps the get a token for you and download all the pictures. And of course, the pictures are generated by this person does not exist.com. So we did everything we can to not violate any regulations. So here is the vendor's response. Luckily, we have contacted with the vendor, and the vendor said that they are going to release a GDPR compliance update in August. And this one is from vendor A. Our apologies that we have kind of miscalculated the disclosure time. So in order to make a responsible disclosure, we are not able to disclose the name, and we're not able to talk about the technical details of the vendor A. And however, we still want to talk about it because it introduced a very, very special network topology that we can see. Next slide. So actually, this is a very special network topology among all the face recognition devices that we have seen. And this represents sort of weaknesses or weak points that you can find in other edge computing devices, not limited to access control devices. So on the left-hand side, you see a terminal that's Samsung Galaxy Tablet A. So Samsung Galaxy Tab A is a very high-end tablet running Android 8.1. And however, it's only served here as a terminal and a camera. All the computational power is not used in this case. And in the vendor's original document, we see that the terminal can be a one high-resolution webcam and one TV. So it's not limited to Samsung Galaxy tablet. And the edge server is actually a Dell Precision 3430. That's a very high-end server, workstation. And it does all the detection, recognition, and recording audition in that server. And the thing we have noticed is that it communicates with third-party APIs with an open API interface, and it has a network relay with this device management thing. That's pretty interesting because when you see the network relay, you may think, okay, so how to trigger the network relay to make it open the door for us? And that's exactly how what we have done. And I wanted to emphasize that we have purchased a standalone model instead of a cloud model, so that everything is in HTTP. This has brought us quite a few advantages when we did this analysis. However, you still have to deploy a network relay in your local access network, which means they are still exploitable even if you're using the cloud model. So this is the network access relay introduced by the product's user manual. There are only two types of access relays supported. The one on the left-hand side, the HT Net 2D, and the one on the right-hand side is a very common access relay that does. So it takes an Ethernet input. So with RJ45, you can just send commands over UDP port 5000. And with one single command like ON1, the output 1 is turned on, so it's shorted, and then you can access, you can open the door. And actually, this is what we have deployed in our office. So you see this wooden board with a very big hole, and you see the very friendly USB-C cable here. It's connected to the Samsung Galaxy tablet. It provides power to charge the tablet itself, as well as providing a network access, which means the tablet is not you accessing the network via Wi-Fi, but via this actually wired network access. So the thing that I have done is to just plug that USB-C cable to my MacBook and try. Then I get what I want, the local access, local area network, and I am in the local area network. And then what I've done is to use ping to try to probe what's in the net, and then I found some interesting IP with port 5000. So let's see. With one single command on1 to UDP port 5000. The doors opened. The interesting thing is that I cannot close the door. And I didn't wear a uniform, and I was standing there asking a colleague of mine to take the video for me, and nobody has asked me any questions. So yeah, the next one. Luckily, we have contacted with the vendor in this case, and the vendor's response is that they have a manual workaround that their technical support personnel can help the customers to deal with. And this series is no longer there. It's end of line already. And in the new series, they have introduced security measurements to prevent this kind of open the door. And they have already published a public advisory to customers. At least I have seen the Chinese version. Maybe there will be English version pretty soon. And the vendor has promised us to fix it and gradually deploy the fix to all other models within 1 month. So applauses to them. Well, it's a very good reaction of this vendor. So let's do a very quick summary.
All right, so I'll be doing a very quick summary here. So although we were attacking access control devices throughout this talk, some cybersecurity must do are shared by all edge computing devices. So here we managed to identify 3 particular types of attack. So one is the implicit trust of devices, communication between server and devices, and actuator. So looking at the table here, ZK is the most unsecured, but they've recently updated their firmware, which is now using HTTPS. That's a good thing, but still, I was able to execute my script using HTTPS, and I was able to create my own user again.
Okay, so this is the matrices of the responsible disclosure. Our apologies again that we have miscalculated this vendor A's close date, so that actually in 3 days we're able to disclose everything. And if you download the slide in 3 days, you will have all the details that we have promised. And even though ZK Tackle has responded to our inquiries, they did not respond to our follow-ups, and they didn't tell us if they have fixed anything. So we have no choice but to open it as a 0 day. I mean, to disclose it as a 0 day. And for telco, even though we have contacted with telco people, unluckily, they did not work with ZDI, and we have no other choice but to disclose it as a 0 day as well. And for vendor A, thanks for this cooperation, and we will disclose it in 3 days.
All right, thanks for that, Phil. Well, for some notable snafus, so we have 4 devices, right? One of our findings is that devices and servers should always communicate using HTTPS or any secure communication protocol, like TLS or anything with the certificate. Additional authentication layer and not just serial number should be used to harden the communication authentication. Okay, communication between server and devices should always be encrypted. So looking at the 4 devices, well, it's there, right? Okay.
Okay, so takeaways. Maybe you can notice that these vulnerabilities are actually not new. And in fact, they have been documented for years. And for example, if you just check the OWASP top 10 vulnerabilities, you see many of them are applicable in our examples. So first, for example, the lack of encryption by default. We have seen HTTP instead of HTTPS in many devices. And second, encryption disabled at server side. Yeah. And third, broken authentication and session management. For example, in Telpo, it's a broken authentication. We can just use the serial number printed on a label to get access to everything. And then vulnerable components. So actually, the edge computing devices has brought a very powerful computational power and give us a very good, very convenient, very resilient devices in the deployment. And however, a greater caution is needed to deploy such devices in a secure way. And last but not least, I want to say that for particularly for edge computing, the upper layer must not blindly trust a middle layer, just like the examples that we have shown in this presentation. And at least if anything is hackable, you have to make the access logs auditable so that in the end of the day, you know who has hacked you. So thank you for attending this talk, and Roel and myself are on the live stream questions. Just go to Hack in the Box Discord channel. We'll be there answering your questions. Thank you, and have a good evening.
Thank you, guys.
Cool, thank you. Yeah, there aren't any questions on Slido, so I'm guessing they're keeping them for you at the Discord channel. One question I do have for you guys. Is it your opinion that things are at least improving with these sorts of devices, that the security implementations provided by them, at least they're getting better?
Well,
Hard to say right now, actually, since we have this pandemic issue, so we haven't had access on different access control. But probably looking at the transformation of access control from fingerprint biometrics to facial recognition with the additional of temperature control. Well, the functionality of the device is kind of okay, but security-wise, communication, still a lot of things to check on that actually. So it's too early to actually say to say that it's really okay right now or not.
Okay, I'm mentioning it because I've seen recently you see a bit of an uptick on like, let's call it generically IoT devices that some legislation is also getting in the way of them reaching the market now. Like a device has to be properly securable. I was hoping that potentially these devices would similarly get some attention and some love by their vendor. Okay, so guys, thank you very much for your talk. We will be back in, in about 10 minutes with the talk Quark Engine, an Obfuscation-Neglect Android malware scoring system by JunWei, KunYu Chen, and AyokJin. That will be a pre-recorded talk. They will be here in about 10 minutes. Don't go anywhere. And we continue with the last pre-recorded talk of the day. That is Quark engine, an obfuscation-neglect Android malware scoring system. Sorry, it's a very long name. It will be presented by Vincenzo, KunYu Chen, and AikyoJin. And here they are.
Hey guys, welcome to join our live sharing talk. Today, we will be demonstrating our engine, Quark. It is an obfuscation-neglect Android malware scoring system. And if you have any question, please feel free to ask in Discord. Thank you. So, my name is KunYu Chen. I'm a security researcher and the founder of Quark Engine. And we also have another speaker, JunWei. He's the co-founder of Quark Engine, and he gave talks in security conferences like HITB and DEF CON. So this is the outline. Number one, we will introduce our malware scoring system. And number two, we will show you how we designed the Delvik bytecode loader. And number three, we will go through two cases of real malware analysis using Quark Engine. And number four, we will share our strategy of generating the detection rules. And the last thing, yes, the future works, because we still have a lot of things to do. All right, so let's introduce the malware scoring system. As we know, when developing a malware analysis engine, it is important to have a scoring system. However, those systems are either business secrets or too complicated. Therefore, we decided to create a simple but solid one and take that as a challenge. And since we wanted to design a novel scoring system, we stopped reading and decoding what other people do in the field of cybersecurity, because we don't want our ideas to be subjected to the existing systems. So we started to find ideas in the field other than cybersecurity. And luckily, we found one. Yes, the best practice we found is the criminal law. So, when sentenced a penalty for a criminal, the judge weighs the penalties based on the criminal law. And after decoding the law, we find principles behind it. And we developed a scoring system for Android malware. There are only 8 principles decoded from the criminal law, and I'll go through it in the following slide. Now let's see principle number 1. A malware crime consists of action and targets. In the criminal law, the definition of a crime consists of action and targets. For example, steal money and kill people. So, with this principle in mind, we developed the definition of a crime for Android malware. And the definition is: the malware crime consists of the same action and targets. For example, steal photos or steal your banking account password. Now, let's see principle number 2. We consider that the loss of fame is greater than the loss of wealth. In a criminal law, physical body injury is more serious than psychological injury. So the principle we decoded here is when things are hard to recover, we consider it a felony. So with this principle in mind, we developed our second principle. We consider the loss of fame is greater than the loss of wealth, because it's easier to make the money back than rebuild your reputation. Okay, now let's see principle number 3. Arithmetic sequence. In a criminal law, when a murderer is sentenced 20 years in prison, and a robber is sentenced 7 years in prison for his crime, have you ever think about why 20 and 7 years? Why the number? We found no obvious principle in a criminal law. So, we use arithmetic sequence to weight the penalty of each crime. For example, the penalty of Y1, which is steal banking account password, the penalty weight is 10, and Y2, which is steal photos, the penalty weight is 20, and Y3, 30, etc. So, now let's see the most important part of the scoring system. We create an order theory. And the other theory consists of 3 principles. There are principle number 4, 5, and number 6. So let's first look at principle number 4. The later the stage, the more we are sure that the crime is practiced. So, as mentioned in Chapter 4 of Taiwan criminal law, each crime consists of a sequence of behaviors, and those behaviors can be categorized in a specific order. Well, let's take murder, for example. Determined in stage 1, determined. It means somebody decide to kill someone. And in stage 2, conspiracy. It means he or she started to make a plan for the murder. And in stage 3, preparation. It means buying stuffs, for example, buying weapons, or arranging services for the murder plan. And in stage 4, start. It means when things are all set, the murderer takes action and is on the way to kill someone. The last stage, stage 5. Practice. It means the murderer does pull the trigger and shoot someone. So, as we can see here, the later the stage, the more we are sure that the crime is practiced. So, with this principle in mind, we developed Android malware crime order theory. And in this theory, we also have 5 stages for the crime. For example, if a malware tries to send out your location data by using SMS, in stage 1, we will check if related permission is requested by the malware. And then we will check if the key native API is called. And in stage 3, we will see if certain combination of API exist. And then we will check if the APIs are called in a specific order. The last stage, finally, we check if the APIs are handling the same register. Okay, so now you can see from this picture. This is a 2-dimensional map for Android malware crime. For the crimes, we put them in y-axis. And for each crime, we use x-axis to see the evidence we caught for this crime. So, x5, y1, it means in crime number 1, we have found native APIs that are called in the correct sequence and are handling the same register. And x3, y5 means in crime number 5, we have found certain combination of native APIs that are used in this APK. So now, let's look at principle number 5. The more evidence we caught, the more penalty weight we give. So we give stage 2 more weight than stage 1. And stage 3 more weight than stage 2, etc. Okay, principle number 6. proportional sequence. As we decode it from the criminal law, the later the stage, the more we are sure that the crime is practiced. So we consider proportional sequence, for example, 2 to the power of n, to present such principle in our scoring system. All right, principle number 7. Crimes are independent events. For simplicity, we assume crimes are independent events, and penalty weight can be added up directly. So, this is an example of adding up 2 crimes. In the malware, we find 2 crimes. There are stealing photos and stealing your banking account password. So the calculation of the total penalty weight is quite simple. For each crime, we use penalty weight of crime to multiply the proportion of caught evidence and add up the result of the 2. The last principle, principle number 8, threshold generate system. After calculating the total penalty weight for the malware, we need to have threat level threshold so that we can tell which threat level does the malware fit in. Unfortunately, we can't find them in a criminal law. But we know we need to design a threshold generate system for that, not just give any number by intuition. So, we decide that threshold for each threat level is the sum of the same proportion of caught evidence multiplies penalty weight of crimes. We know it's not a perfect one, but we're sure that we build a foundation for future optimization. All right, now let's talk about the design logic of Delphic bytecode loader and my partner, JunWei. He will take care of this part.
Hello everyone, my name is JunWei, and I will take care of this part. So now, let's talk about the design logic of Delphi bytecode loader. So our Delphi bytecode loader is actually the implementation of the Android malware crime order theory. We implement every stage of the theory. There are 5 stages. The first 3 stages are easy. We simply use APIs in another open source tool, Android Guard, to implement the first 3 stages. As I just mentioned, the implementation of the first 3 stages are easy. But in stage 4, we need to do a little bit more. So, before the implementation, we need to know what does stage 4 do. In stage 4, we find the calling sequence of native APIs and check if they are called in a specific order. For example, if a malware sends out your location data by SNS, then first it will call native API get cell location to get your location data. And then it will call native API send text message to send your location data by SNS. Normally, native APIs are wrapped in functions, so we trace back to see which function is cross-referenced from the native APIs. And we call those functions the parent function. And we will keep tracing back until we find the mutual parent function for both the native APIs. Here is the example. Send text message is called by send SNS, which is the parent function of send text message. And get cell location is called by get location, which is the parent function of get cell location. And if we keep tracing back, we will see that both send SNS and get location shares the same parent function, which is send message. And after we find the mutual parent function, we will scan through a small line code of the mutual parent function and check which function is called first. So this is the smiley-like code of send message. We can see that get location is called first to get location data of the cell phone. And the send SNS is called to send out the location data. And in stage 4, we found out that our design can also overcome the obfuscation techniques used by the malware. When applying obfuscation techniques, functions except native APIs are renamed. This has made the decompiled source code hard to read for humans. The machines can still run the code because the logic of the code remains the same. Here is the example. When applying obfuscation techniques, native API send text message is called by function K, and function K is called by function F. The alternative API, get cell location, is called by function E, and both function E and F shares the same parent function, which is A. So you see, if you start reading the decompiled source code of A, it will be hard to figure out what is going on there. And by the way, since our goal is to find the mutual parent function, so it doesn't matter how many layers the wrappers are. Now, let's see the implementation of stage 5. Yes, this is the most important part. In stage 5, we need to confirm that if the native APIs are handling the same register. Let's use the same example. Send out your location data by using SNS. So when native API get cell location is called, it will return the location data of the cell phone. And what we do in stage 5 is to check if the older native API send text message sends out the location data return from Gaston location. So in stage 5, we simulate the CPU operation, and we will read line by line of the Smalley-like source code and operate like CPU to get two things. First, the value of every register. Second, the information like functions who have operated the same register. To make this happen, we create a self-defined data type. We call it register object. In each register object, we store three kinds of the information. Number 1, the register name. And number 2, the value of the register. And number 3, the function who use this register. Let's see the example. So the register name is V7, and the value of the register is a string. And the string appends the value of string 1 and the result of function 1. And then we can see that the register is used as the input source of the function 2. And by the way, when filling in the value of used by which function in the register object, we expand every register by cross-referencing other register object in the table. So, for example, by cross-referencing, we know that V8 is a string, which is user location, and V3 is a function called getLocation. As you can see in the lower right corner, the result of getLocation is appended to the string, which is user location. And the new string is sent out by using function send SNS. In other words, the value of register V7 is generated by using function getLocation, which has native API 1 in it, and the value is used as an input for function send SNS, which has native API 2 in it. So now, we prove that by using the register objects, we can check if the APIs are handling the same register. So, after we scan through the source code, we will produce lots of register objects. And those registered objects will be organized with a two-dimensional Python list. It is a similar idea like hash table. We will use it to boost up the read and write of the list. So now, let's see the table. As you can see here, register v4 has 3 registered objects. That means in the source code we scan, v4 was used 3 times. And every time when it was used, we store the present value of the register and the function who use it if there is one. So basically, the whole table is the history of the registers. So when we finish constructing this table, which is the hash table we built, we then scan through all registered objects in the table to check if the native APIs are handling the same register. So now, let's see how to use Quark engine to analyze the malware. And now, let's get back to KunYu.
So, in this section, we prepared 2 malware. One is non-obfuscated, and the other one is obfuscated. And for each malware, we will show how we detect the behavior of the malware with the detection rule. Now, let's look at the first malware. This is a non-obfuscated one. We will use the rule in Quark engine to detect whether if the malware send out cell phone's location data by using SMS. So this is the detailed report of Quark engine. In this report, the engine shows the detection results of one single malware behavior. Or you can say one single malware crime. So, for example, we try to find if the malware sends out your location data by using SMS. So in this report, we list out the evidence we found in each stage of the Android malware crime order theory. And this report shows we find evidence in every stage, which means we have 100% of confidence that the malware has this behavior. So let's see. In stage 1, permissions like send SMS, access course location, and find location are requested. And in the second stage, key native APIs like get cell location and send text message are used. And in stage 3, we found certain combination of native API exist. And in stage 4, we found out that in functions like send message and do byte, the APIs are called in the right sequence. And in stage 5, in function send message, we found out that those APIs are handling the same register. So now, let's think. If you're analyzing this malware and you want to trace the decompiled source code to see the evidence, how do you do it? Our suggestion is, if you're reading this detailed report, generated by Quark engine, you start reading backwards. That means you start from stage 5. So, for example, in stage 5, we know that inside the function of send message, it has 2 functions that contains the 2 native APIs respectively. And they're handling the same register. So, you start to locate function send message in the decompiled source code. And in stage 4, we know that those 2 functions are called in the right sequence. So we can start to find functions that contains the native APIs and check if they are really called in the right sequence. And the information of the 2 functions and the sequence will be shown in the next version of Quark engine. So now let's look at a real example. As we just mentioned in a detailed report, we need to locate the function of send message. And we found out that 2 functions that contains the 2 native APIs respectively. There are send SMS and get location. And if we dive into the function, dive into the source code of this function, get location, we will see that it contains native API get cell location. And if we dive into the source code of function send SMS, we will see that it contains native API send text message. So, the decompiled source code here, it means the APK or the malware will first collect your cell phone location data and send it out through SMS. So now let's dive into the source code of function get location. As you can see in the source code, it tries to call native API get cell location and return this information at the end of the code. And now, let's dive into the source code of send SMS. Native API send text message is used to send out the location info. Well, it's quite simple, isn't it? And now, let's look at the second malware. This is an obfuscated one. We will use the rule in Quark engine to find whether if the malware detect Wi-Fi hotspot by gathering information like active network info and cell phone location. Okay, so as a malware analyst, we read the report backwards. So as you can see, in stage 5, there are functions like p.a, @view.c, and af.run. And those functions, they have 2 functions that contains the native APIs respectively, and they're handling the same register. And in stage 4, these 2 functions are also called in the right sequence in functions like p.a, @view.c, and af.run. So, according to this report, we can say that the malware has the behavior of Wi-Fi hotspot detection in 3 parts of the source code. We can pick any part for further analysis. So we just pick function p.a. So now let's see the source code. Let's locate the function p.a. And we found out that 2 functions that contains the 2 native APIs respectively. They are ap.a and f.f. And if we dive into the function of ap.a, we will see that it contains native API get active network info. And if we dive into the function of f.f, we will see that it contains native API get cell location. So the code here means after collecting information from function ap.a and f.f, they send the information as an input for function am.a. So now let's dive into the source code of function ap.a. As you can see in the source code, it tries to call native API get active network info and return the related information at some point. And now let's dive into the source code of f.f. Native API get cell location is used to get the cell phone location data. And this information is processed with some other strings. And at the end of this function, it returns the strings with the information. As I mentioned earlier, after collecting information from function ap.a and f.f, they use the information as an input for function am.a. And we noticed one thing, that function am.a use byte array output string as one of its input parameter. And we know when seeing byte array output string, it means the function is probably trying to write the data into a file. Well, this is amazing, isn't it? So with Quark engine, malware analysts can really boost up their productivity. Okay, so now I will introduce our detection rule generate strategy. So, why do we need to develop the detection rules generate strategy? The reason is quite simple. Because to make our engine practical and easy to use for malware analysis, we need to have more detection rules. However, the speed of rule generated by human is quite slow. And a human-generated rule is subjected to his or her experiences of malware analysis. So, we decide to develop a rule-generate strategy to boost up the production of detection rules. Since our goal is to find all kinds of behaviors in the malware, So if we use permissions and native APIs to generate all possible rules, we will have an amazing amount of rules, which is 1.26252E plus 13. Amazing number. So, and after, if we really take time and a disk volume to generate such amounts of rules, we then use Quark engine to find the intersection between those amazing amounts of rules and the malware we prepared. We prepared a lot of malwares. So, in other words, we find rules that matched the malware behaviors. However, this is not a good way to generate detection rules because it's very obvious. It's time and resource consuming. So, we developed a 7-step rule generate strategy. In step 1, we crawl down all native API information on Android official API reference. For example, this is the native API information of send text message. You can see the input parameter, the return value, and the description of this API. We pro all of them down into our computers. Okay, step 2. So we did a little bit modification to our engine. We ignored the permission checks in stage 1 of the Android malware crime order theory. And in step 3, we find all kinds of API combination and generate rules without permission information. In stage 4, we use the modified Quark engine to find the intersection of the rules and the malware. We call rules in the intersection, this part, the first stage verified rules. In other words, these rules, they still need to be verified again. And since we don't need to generate rules with permissions, and we don't need to verify the permission in Quark engine, the whole process of rule production really speeds up. And in stage 5, we try to generate rules with permissions. So inside this intersection, we have first stage verified rules matched with malwares. We then use the first stage rule and the permission in the matched malware to generate rules with permission, which is the second stage rule. And in step 6, we then use the Quark engine, the full function version, to find again the intersection of the second stage rule, which has the permission information in, and the malwares we prepare. We find the intersection of those two. After that, for each rule, we label the number of matched malware. So, as you can see, the rule number 1, it can be found. The behavior of rule number 1 can be found in 100 malware. And the behavior of rule number 3 It can be found in AD malware, etc. We label such information in somewhere. And in step 7, after labeling the rules, we then sort the rules by numbers of matched malware. And we will review the rules from the highest matched one. That's our strategy for the production of rules. All right, the last part, future works. As I mentioned earlier, we still have lots of things to do. For example, we need to have more detection rules. And we also need to deal with the .so files and the packed APKs. And we want to have more features of the Dalvik bytecode loader. For example, we want to have features like the downloader. And we also want to apply the scoring system to other binary formats. Yes, it is in our to-do list. And also, we noticed one thing. We noticed that the API changes in different version of Android. And every year, it has a different version, it has a newer version. So, we'll also take care of this problem in the next version of Quark. And the last thing, we probably will change the core library since AndroGuard is quite inactive recently. And there is one nugget that I would like to share. We work at the limits of our tools. When new tools come along, new things are possible. Okay, that's all for today. And if you have any question, please feel free to ask in Discord. Thank you.
And there you have it. In about 10 minutes, we will be back with the next talk, which is PECidious, create mutated evasive malware using artificial intelligence. This will be presented by Chandni Vaya and Berang Seng. Please don't go anywhere. It is 9 o'clock in Singapore, and that means that we are up for the last talk of Hack in the Box Singapore 2020, aka Lockdown number 2. The last talk is by JunWei Via and by Bedang Chen. They are here via Zoom call, so entirely live. That means that if you have any questions, please chuck them in Slido and I will ask them on your behalf. We have JunWei and Bedang talking about PE-Sidious, create mutated malware using artificial intelligence. Take it away.
Hello, a very good morning, good afternoon, and good evening. Thank you for joining us today for the last talk of the evening for PE-Sidious, creating mutative evasive malware using artificial intelligence. Now, before I kick off this talk, I thought it'd be very fun to really explain what the word PE-Sidious means. I know I've had a number of questions pop up around this in the past, so I thought it'd be best to kind of get this out of the way in the very beginning this time. Now, for those of you who are Star Wars fans in the audience, you might have already figured this out, but for the rest, here's what it is. PE-Sidious is a portmanteau of two words, PE, which is the Windows PE executable, the primary data that we're working on for this project, and Sidious, who is .Sidious. Now, for those of you who don't know, .Sidious was the Dark Lord of the Sith, and he very successfully infiltrated the Galactic Republic as posing as a benign senator while truly being the malicious Dark Lord. And that is exactly what we aim to do with our project. Another very interesting fact I thought I'd introduce in the beginning of this talk is how PE-Sidious was in fact a solution that came out of a Hack in the Box challenge last year. So this was the HITB AI challenge, and that's really when Johnny and I got together and we developed this tool for that particular competition. And we were actually fortunate enough to win first prize for it. So when we heard there was a Hack in the Box conference, we were more than excited to present in this conference and share this with the broader HITB community. So before we get started, just wanted to give a huge shout out of gratitude to Dylan and the rest of the HITB group and crew for having us here for this talk. Right, so that being said, just a little bit of housekeeping before we get started. Now, we know that a lot of the stock is very heavy on the AI. So what Tony and I have decided is to keep things as high level as we possibly can throughout the talk so that everyone can benefit from it. Now, that being said, if anyone has any questions or would like us to elaborate more around a specific AI technology or anything in general, please feel free to shoot us a question. We will try our very best to address them when they come in. But if not, as Cooper mentioned, we are definitely going to be there to address all questions in the Q&A section at the end of this talk. And with that being said, I think we can move on to the next slide. So before we dive in, a very quick overview of what I'm going to be talking about, what we're going to be talking about for the next 1 hour. I'd like to start off this presentation with a very brief introduction of who we are, after which we're going to talk about PE-Sidious, what PE-Sidious is, and more importantly, why we decided to work on this project to begin off with. Following this, we're going to get into implementation, that is how PE-Sidious really works, and a very brief project demo. Now, I just like to raise a point here. We're not going to do a live demo for this talk, and we're going to explain this during the end of this talk, why we've decided to keep it that way. Finally, PE-Sidious is an ongoing project. We are continuously developing this tool. We're continuously improving it and finding new ways to improve around this tool. So we'd like to conclude this presentation by just talking about a couple of things that we have planned for the future. That being said, let's move on to the next slide. So my name is Bedang Sen, and with me, I have my friend and colleague, JunWei Via. We are both incident response consultants with IBM's Expos IS team. And apart from working in security, we have a lot of passion for, of course, AI. We love working with the data science. We have worked with microservices in the past. And what we find really interesting is really how all these technologies can be used together to solve each other's problem. primarily because we are definitely security focused. We love leveraging these three key technologies to solve some of cybersecurity's most current issues and problems. So if any of you are interested in doing the same, or would just like to get introduced in this field of AI and security or microservices security or anything really, feel free to reach out to us. Feel free to connect to us on LinkedIn or any other platform really, and we'd be more than happy to sit down, have a discussion, and maybe even collaborate in the future. All right, so let's talk about Presidius. Now, before I talk about what Presidius is, I think it's very important to address a bigger question, why we decided to work on Presidius to begin off with. And of course, the short answer is, it was one of the challenges from Hack in the Box AI challenge last year. So that's what got us started. But it's really a lot more than that. Now, while we were conducting research, we found that over the past 2 decades, there have been numerous solutions which use AI to detect malwares or malicious activities. And due to this increasing popularity of the use of AIs, we notice a lot of malicious actors have started to leverage the same technology to attack those very same AI models that are used to block these malicious attacks. And they do this through a number of ways. There are cases where malicious actors poison these AI models using poisonous input. There are other ways. If a malicious actor knows enough about the way the AI model functions, it's very easy for them to circumvent those security mechanisms put in place to begin off with. So our key idea for this talk was to try and understand how easy it would be to use AI to mutate malware in such a way that an AV engine or an AI-powered AV engine would consider it to be completely benign. And that's what we're here to talk about today. So let's get started about what Presidius is. Now, Presidius is our malware mutation tool, which uses reinforcement learning and generative adversarial networks. Wow, that's a lot of heavy words over there. So let's try to break this down into what it really is. In a very simple sense, Presidius looks at taking a malware file and mutating it using AI to make it appear to look benign to an AV engine. And that's all we're doing with Presidius. But what's going to be interesting is how we go about doing these changes or how we go about doing these mutations. So I would love to dive right into how Presidius works, but I think in order to make more sense of it, it's very, very important for us to really understand what those two heavy words really mean: reinforcement learning and generative adversarial networks. And with that, Johnny is going to talk more about reinforcement learning.
Hello, everyone. So what is reinforcement learning? Now, in its simplest form, reinforcement learning is basically teaching a machine how to navigate an environment to reach a goal by using a sequence of actions, right? And the way that the machine learns the right sequence of actions is by receiving some kind of a reward for every right move that it makes and receiving some kind of a punishment for every wrong one. Let's take an example, a very simple example over here. Let's say we have a dog over here, which is the agent, trying to navigate this environment, which is a maze, to reach its goal, which is the piece of meat. So right now, the dog acting as an agent is in tile number 1, which can be called the state of the dog, right? So the state of the dog is tile number 1. The different actions that the dog can take to move around in the environment are going up, down, left, or right. And this is all that the dog knows in the beginning of when the environment is initialized, right? This is all that the agent knows. Now, the first thing that the agent would do is that because it hasn't learned anything, what it'll do is just randomly move around and try to reach the piece of meat. Let's say, for example, it decides randomly to go down. The moment it does that, because it's a red tile and it's a wall, what we do is we give it a negative Q value. Now, what is Q value will make sense in a little bit, but the whole idea is that the moment the dog or the agent makes a wrong move, it should get a negative Q value or a negative reward. Now, let's say again, randomly, the dog decides to go right. Because it landed on the white tile, which is a right move, it will get a positive Q value. Again, let it make random movements. So it decided to land on a white tile. So we again give it a positive Q value. Again, it decided to go down and it landed on the red tile, which was a wrong move. So it will get a negative Q value. It will get a positive Q value, a reward for moving to the white tile. Same thing. And now, did you see what happened over here? It did move to a white tile, but instead of going down, it moved further away from the goal. So if we keep giving the same static reward for every time it lands on the white tile, the dog is not going to learn properly. So the way that the reward has to be assigned is based on how closer is the dog getting to the goal itself. So if we go back, right, when the dog was over here, if it had decided to go down, we would have given a Q value that comparatively would be more than the Q value it got when it decided to go up. And Q value is, the way that the Q values are calculated is just simple maths, right? It uses something called a Bellman equation, which is the core of what reinforcement learning is. But explaining the equation and explaining the maths behind it is a little bit outside the scope of this presentation. The only thing we have to understand right now is that Q value basically calculates the immediate reward that an agent would get for the action, plus the rewards that it will get for the subsequent future actions. So in essence, it's basically the closer that an action gets the agent to the goal, the more the Q value will be. And the further it gets away from the goal, the lesser the Q value would be. And every time it lands on the wrong tile or the wrong state, it would get a negative Q value. So as I said, initially the dog doesn't have any idea, right? It's trying to randomly move and see what are the different Q values for all the different actions. What eventually will happen is that after, let's say, thousands of these episodes of random episodes, or let's say 2,000 of these random episodes, the agent will build a table which is basically the Q values for every state and action pair. So for example, for tile 1, the dog will, or the agent will basically remember what is the Q value of going down, what is the Q value of going right, and what is the Q value of going left. So this is basically learning from the past experiences, right? When in the past it decided to go down, we gave it a negative 0.51 Q value and it stored it in the table. And after, let's say, as I said, 1,000 episodes, it will be able to build this entire table. And the next time when the learning is done during the testing stage, the dog will just look at, okay, I'm at tile 1, what action should I take based on the different Q values in my table? So because the action of going right has the highest Q value, I'll go right. And then it will land in tile number 2. And then again, it will refer back to the table. It will see that the Q value of going down is the highest. So it will decide to go down. And so on and so forth. And eventually, it should land in tile number 34. And we can see in the table, the Q value for going right is the highest. So it will go right. And then again, from tile number 34 to tile number 35, it will get the maximum reward for the environment. So this is what reinforcement learning is, right? It's basically randomly moving around and collecting the Q values for every possible action. And then once the agent is done learning, referring back to those Q values to know what is the right sequence of action to reach the goal. Now, in this case, we can see the environment was quite small, right? It's a 6x6 square, with 36 of the total tiles. And the number of actions are just 4, right? Up, down, left, and right. Now, in reality, reinforcement learning is mostly used for video games or for chessboards. And when it comes to these environments, the video games, or let's say the AlphaGo game, the environments are very complex, right? It's not just a 6x6 square. It's not just 36 tiles. It can be thousands and thousands of possible states. And again, thousands and thousands of possible actions that the agent can do. And if the agent tries and builds this table, it will be quite inefficient in the terms of storage, because where will you store all that data? Where will you store the values for each possible state and action? On top of that, let's say if you do have the storage to store the table somewhere, referring back to the table for the state action pair the time itself will be inefficient. So how do we replace this table with something more efficient, right? So if we look at the table, it's nothing but it's just a function, right? What a function does is that it takes an input and it does some calculation on it and it gives us the output. Now the calculation part is what the dog should or the agent should be learning. And what the first thing that comes to mind about how to build something that approximates a function that could replace this table is a neural network. What if, while learning, the agent, instead of building the table, actually tunes the weights of this neural network or trains the neural network to take an input and give the right output? In this case, to take the current state of the agent and give me the Q values for all the possible actions. And then I can just look at the Q value and see which action has the maximum value and then perform that action. So at the training stage, what I can do is let the neural network randomly select actions just the way that the dog was doing, and then use backpropagation to train the neural network saying, okay, so this is the Q value you gave me, but this should have been the Q value. So backpropagate the loss, train the neural network, and try and minimize the loss as much as possible. Try and minimize the difference between the Q value given by the neural network and the actual Q value, the right Q value. And once that loss, that difference is as low as 0.05, or that could be an hyperparameter, we can say that the neural network is trained. And this is what a simplified version of deep reinforcement learning is. And as Vedang said, deep reinforcement learning is just half of what Basidius is. The second half is about generative adversarial network. And this is what Vedang will talk about.
Right, so generative adversarial networks, what are they? Now, as the name suggests, generative adversarial networks are generative models. And what this means is, unlike the other AI models you've typically seen in security, which you really use predictive or detection capabilities, which means they are used to predict data or detect data, a generative model, on the other hand, is used to generate data itself. And that just sounds super cool to me from the very beginning. So what a generative adversarial network is it's a class of neural networks that's used to generate data that closely resembles the internal structure of an input data. Now, I know I could go on and on describing what this is, but I think the easiest way to kind of explain what a generative adversarial network is and how they work is through examples. Now, right now, in the industry, GANs are most popularly used for image manipulation. So some of the most frequent use cases that we come across using GANs is, say, text to image translation. And what this means is you can go ahead and describe what you want an image to look like, and your generative adversarial network, or GAN, is actually going to generate that image for you. And you'd be surprised how accurate these images tend to be. Another example or use case is image-to-image translation. And again, as the name suggests, you can convert one image to another. And an example of this is you could take an image of a zebra and you can make it look like a horse. Another very interesting one is hand drawing to image rendering. So again, no explanation required there. And of course, I could go ahead and name a ton of different ones. But the one I want to talk about the most is what made GAN famous, or rather infamous, in the past couple of months, and that is deepfakes. So let's take a quick look at what a deepfake is and how it works. Now, in this video, you notice that we do have our input data set, which in this case is the speaker speaking. And you notice the different facial expression, body movement, eye movement that the speaker employs. On the other side, we have replicas of the speaker. The way this works is just using one source image, and then the replication video that you see in this video is using GANs. In another example that we'll see shortly, over here is we have the same thing. So here you have two input data sets, one of Barack Obama and one of Donald Trump. And again, you have a number of different target images Some of them I can see is Vladimir Putin. We have Mona Lisa. And using the generative adversarial network, you can see how this AI model, these neural networks are fully capable of replicating what the input video looks like. So that's what a deepfake is. But now let's try and understand how generative adversarial networks are used to generate these videos or replications. Now, what makes a generative adversarial network so interesting is the use of two competing neural networks. So it's basically AI training AI, and that's where things get really fascinating. So the first neural network that we have is called the generator, and the primary purpose of this neural network is to simply generate an output that closely resembles the internal structure of the input data while maintaining the features of the target data provided. So let's quickly flash back to the video. In that sense, the input data would be of, let's say, Barack Obama or Donald Trump, and the target images would be whatever the GAN was replicating. The other neural network that we have is the discriminator. And the purpose of the discriminator is to basically, well, discriminate between the target or the input data set and the target data set. So what it's going to do is it's going to look at the generated output, and it's going to try to understand whether the generated output belongs to the input data set or whether it's a fake. If the discriminator does decide that the generated output is a fake, it's going to provide some feedback to the generator. And the generator is going to take this feedback and retune the parameters of the neural network to produce a more accurate generated output. This cycle of feedback and retuning keeps repeating until the generator is capable enough to fool the discriminator. And that's how we get these deepfake images. Now, if you look at the process, the way the GAN works is before anything can happen, the first step is for the discriminator to train. The first step is to train the discriminator with the input data set and the target data set. And the objective of this is to just understand, for the discriminator to understand what does the input data set look like and what the fake data set looks like to be able to understand where to place the generated output. Once the discriminator is trained, that's when we can finally feed in our fake data set or our target data set into the generated neural network. And while we do this, we also append a noise vector. Now, the only role the noise vector plays in this step is to help the generator randomize the value and give it a more efficient or effective generated output. And that's pretty much it. And then the process remains the same. The generator generates an output, and this goes to the discriminator, and the discriminator just checks whether it's a fake or belongs to the input data set. And until the discriminator is fooled, these two neural networks keep going on it in a loop. And that really is it. That's how a generative adversarial network works on a very high level. So now that we understand what a generative adversarial network is and what reinforcement learning or deep reinforcement learning is and how they work, let's try to understand how we are using them in our project Basidius. So the diagram that you see on the screen right now, on the slide right now, is a visual summary of Basidius's implementation. And I know it looks very overwhelming at first glance. So let's do this. Let's try to break this diagram up into different phases or different steps to more clearly convey how this project works. The first step is going to be our feature extraction stage. Next slide. Right. Now, as much as I'd like for AI to be capable of just taking in a binary and running it through a model and mutating or creating mutated variants of this malware, I'm afraid it's not that simple. A binary is a very complex piece of data. And in order for us to train our AI models, we have to break this down into a simpler representation that our AI models can learn from and it can train on. And this simpler representation for us is going to be a binary representation, no pun intended, of ones and zeros. So let's take a look at how this happens. The very first step in our feature extraction step is to collect our data set. And this is going to be to collect our malicious and benign binary data set. Now, fortunately, there are a number of online repositories which host malware samples that can be downloaded for research or educational purposes. A couple of ones that we used were VirusTotal and VirusShare. For the benign binary dataset, we unfortunately didn't come across any such online repository. However, it's not really that hard to get your hands on benign dataset. All you have to do is spin up a Windows virtual machine and then just run a script to collect all the binaries you can find in the system. And boom, you have your benign dataset. So now that you have both your benign and your malware dataset, you can move on to this next step, which is to extract all the features into a single feature vector. Now, when we talk about the step, the first question that automatically comes into my mind is, what kind of features are available in a Windows executable? What kind of features can I really collect? And second, out of all the features that I can collect, which features are going to impact my AI model the most? Again, it's very important to understand how these AI models work. You can't just dump everything into it and expect it to learn. You have to be very careful about, you have to be very smart about the kind of features you provide your model to learn from in order to train it most effectively. So we are going to address these questions in the coming slides. But for now, let's move on to the third point, which is, sorry, can you go back to the previous slide? Right, so the third point is to generate feature vectors for each of the binary data using the feature vector map. So once we have our feature vector map that we created in the second step, the next step is to create that representation for every piece of data that we've collected in our data set. So what this would mean is we would take a binary and we would more or less just convert it into a series of ones and zeros, where one represents the presence of a specific feature as per the feature vector map, and zero representing the absence of that feature. All right, so let's go to the next point and start answering some of the questions we raised in this slide. Okay, so when we raise the question, what kind of features do we have available? It's very important for us to look into an executable and try to find that answer there. So let's consider the example binary that we have here, an example.exe. On a very high level, a PE executable can be divided into two components. You have the header component and the section component. The header component contains sections like the DOS header, the PE header, optional header, data directory, and section tables. Now, the section table is a very important one. It contains a list of different sections and their locations in the section component. Now, when we go to the section component, this is where the main content of the binary resides. So this is where you'll find the code. This is where you'll find additional resources, such as any images used in the application, or icons used by the application, or any audio that's used by the application. So some of the different sections you'll find over here are code, inputs. Inputs is, again, a very important one we'll be touching in the next slide. And of course, the data that I just covered right now. So just looking at all of these different features, I think it's very easy to figure out that not all of this would be easy to convert into the representation we mentioned earlier. So the question then arises, which one of these would be most suitable to train our AI model? Now, based on prior research conducted, our own research, and numerous trials and errors, we narrowed down the most optimal features to these 6. The first one being section information. So this includes the number of sections with a non-zero value or an empty name, a number of sections with different characteristics. We include features of property of entry points, machine architecture, operating system. We include features of imports information and export information, such as DLLs and functions, as well as other header information, such as virtual size, debug flag, relocation, resources, and signatures. And we go through all these features while extracting them, while running through our entire binary data set, and we start storing every unique feature that we come across into a feature vector map. So let me try to explain that with a very small example. So let's assume I'm going through example.exe during the second step of the feature extraction phase, and I come across a unique DLL, say user32.dll, that I haven't come across before. I'm going to, as soon as I see that, I'm going to create an entry in the feature vector map, and I'm going to place user32.dll there. While again extracting the same binary, I come across another input DLL, which is the kernel32.dll. And again, I do the same thing. So now my feature vector map is this massive map which contains all the unique features that I've come across my data set. The next step is then to create feature vectors using this map for each of my data in my data set. So what that data is going to look like, or what those feature vectors are going to look like, is basically just the ones and zeros to fill up the values in this map. So let's consider another executable, let's say test.exe. And let's say test.exe does have a user32.dll. So we're simply going to plot a 1 in the vector location that corresponds to user32.dll in the vector map. And let's say it doesn't have kernel32.dll, then it's just going to remain a 0. So this is just to kind of illustrate what kind of data we're feeding our AI model. And this simple representation, while just consisting of 1s and 0, is what we're using to represent the identity of the binary that we are training our model with. So now that we've understood what these features or what kind of data we're feeding into our AI, let's jump into the next phase, which uses reinforcement learning.
Okay, so now as Vedang said, what we did is we created a data set that is a representation of the malicious and benign binaries, right? But these data sets are just 1s and 0s, 1 for an existence of the feature and 0 for the non-existent. Now, to understand how deep reinforcement learning works with malware mutation, let's refer back to our previous example of deep reinforcement learning, which was the dog, the maze, and the meat. In the example of the dog, the environment was the maze, right? They were trying to navigate the maze. In this case, our environment consists of two things. First is a modifier. Now, again, when it came to the dog example, the different actions that the dog was allowed to perform was going up, down, left, and right. In our scenario, the different actions that the environment or the agent is allowed to perform are as follows. So what are the different actions we are performing on a malicious file to mutate it and to make it look more benign? Some of the things are we randomly add import functions and DLLs to the import table. We randomly add sections. We rename sections. For example, let's say the malicious file is packed, then most certainly it will have a section called .upx. What we can do is just rename it to something that sounds more benign or that looks more benign. Some other things that we do to change, let's say, the size, the hash of the binary is appending to existing section. Now, when we append to existing section, and if we append enough bytes, what it can also do is change the entropy. That is, if the section is packed, what happens is that, or if it's encrypted, the entropy is going to be high, right? The randomness of the section is going to be high, which can be an indicator of a malicious file. And if we add enough, let's say just enough zeros to the end of the section, what will happen is that the entropy, the randomness will keep lowering, right? It will keep getting less and less, and the malicious file will keep looking more like a benign file. Another thing we do is append random bytes, just change the size and the hash. We remove or add any signatures to the malicious file. We remove a debug flag if it exists, and we also try and pack or unpack using UPX packer, right? So these are the different actions that the environment is allowed to perform when it comes to solving the problem. So that was for the modifier. Now, what is the classifier? Now, in the case of the dog, what happened is that the way that the reward system worked is that whenever it landed on a white tile, it got a positive reward. And whenever it landed on the red tile, it got a negative reward. So how would the rewarding system work when it comes to mutating malware? It's simple. What we do is that we first get the score of the original malicious file. And then whenever we mutate the file, we again basically query some kind of a classifier, which can be your own trained machine learning model. Or in our case, what we did is we simply queried VirusTotal to get the score of the mutated malicious file. And then we just compare the score for the mutated malicious file with the original malicious file. And if the score, the number of engines that have detected the file as malicious has gone down, it's going to be a positive reward. If for some reason the mutated file has more score than the original file itself, then it's going to get a negative reward. So that was for our environment. The next thing in the deep reinforcement learning, the main component is our neural network. Now, again, what happened in the dog example initially is that to learn how to solve the maze, it was just randomly going around to try and see what are the different Q values. So right now, because this environment has just been instantiated, what happens is that the neural network has random weights for its hidden nodes, right? So it's just randomly going to select any kind of is randomly going to give us output for Q values when it comes to actions. So let's say for the training stage, what would happen is that we'll take the malware feature data set, which would be the current state of the environment, right? Previously, it was just one single tile for the dog. In this case, it's basically a vector of hundreds and hundreds of features representing the malicious file. What we do is that we take the feature vector and we basically input it into our neural network. What the neural network, because it's just randomly assigned weights, is going to give us a randomly generated Q values for all the different actions. And what we'll do is just select the Q value with the max, we'll select the action with the maximum Q value. The next thing we're going to do is actually take the action into the modifier, take the malicious file, and for example, let's say the neural network said that the Q value for an appending random bytes is the highest. So the modifier is just going to go ahead and append random bytes to the sample. What it's going to do next is actually pass the mutated file back to the neural network to get the Q value for the mutated file itself. The reason we are doing this is, as I said, the core of the reinforcement learning is the Bellman equation. And what Bellman equation tells us is basically the addition of the immediate reward, which is the reward we'll get from the classifier, plus the rewards of all the future states, So what we'll need is actually the future state too. So that's why we pass on the mutated and we'll get the Q value for the mutated malware. And what we do is pass all these three variables, the reward, the future state, and the current state, to our optimizer. Optimizer is nothing, but what it's going to do is actually calculate the Bellman equation, right? It's going to run a function that calculates the Q value using the Bellman equation. It's going to compare it to the Q value we provided from our neural network, and it's going to generate a loss. Loss is nothing but the difference between the Q value generated by the neural network and the actual Q value, right? The right value. And we just what to do is just pass the loss back to the neural network, and it's going to backpropagate this loss and learn what mistakes it made the first time. Let's say the Q value that it gave for this malware feature was, let's say, append random bytes, right? But the optimizer told us that the actual Q value should have been add a signature. So what we do is we tell the neural network that the answer should have been this, and it basically takes the value, the mathematical value, and backpropagates it through the hidden nodes. So what it will do is just adjust the tune itself to get the right answer next time. Another thing that we do is something called experience replay. This is very similar to how a human brain learns something. Let's say you want to teach a kid not to throw its sock around, right? Not to throw a sock or its clothes around. The first time it's throwing the clothes around, what we do is we give it a punishment. And the next time, hopefully the kid won't throw the clothes around in the room. And what we'll do is we give it a positive reinforcement. And the third time, what it's going to do, it's going to learn, okay, now I shouldn't throw the clothes around in the room because I want to get the reward. And it will put the clothes back in the cupboard or something. What is this? It's an experience that the kid has gone through, right? In this case, the experience would be a particular action or a particular modification to a malicious file. What we do is store that all the right experiences into a data store. And after every interval, let's say after every 10 right actions performed by the neural network, we pass it back to the neural network. We replay the experience for the neural network for it to learn better, just like how our human brains learn better if the experiences keep replaying itself. So this is how a reinforcement learning agent would be trained for mutating a malware. Now, when we talked about the modifiers, some of the modifiers were very simple, right? We were renaming, no, let's that be. We were randomly adding bytes to the section. We were randomly adding bytes to the end of the file itself. We were adding or removing signature. But if you look at the first action that could have been performed is randomly adding imports, functions, and DLLs. Now, what we did initially is we precompiled this list of all the possible DLLs and their functions from a Windows 32-bit machine. And we realized it didn't work that well. Not all the imports and DLLs. For example, we also had a crypto library in there. Just imagine if it's a ransomware file and the neural network learns to add the crypto library into the malicious file. It's just going to make it look more malicious. And the reason that it's happening is because when it comes to adding imports, we are just randomly selecting from the list. We are just randomly selected from the library of all the possible imports and DLLs. Same goes for the sections. So what was the solution for this? The solution was simple. It was, what if we could get a list of imports, DLLs, and sections that we know would work for sure, that we know would definitely make a malicious file look more benign. Now, how do we get this list? This is where generative adversarial network would come in.
Right, so that brings us to our final phase of Pisidius' implementation, using generative adversarial networks to generate the most optimal feature list that can be then passed on to our reinforcement learning agent to mutate our malware. So let's take a look at how this works at a very high level. Now, you notice a lot of similarities with what we covered earlier with the deepfake example. So our first step is for feature vectors to be concatenated with the noise vector and fed into the generator neural network of the GAN. And once the GAN generates the adversarial feature vector, it goes through the discriminator and goes through that entire feedback loop. If you look at the diagram on the slide, you notice that the diagram is almost identical to what we looked at the deepfake. You notice an additional component in our generative adversarial model, and that is the introduction of a black box. So before we proceed, let's take a look at what that black box is and why we are using that black box. Next slide. Now, the purpose of the black box is very simple. It's simply to mimic the functionality of an AV engine. That is to classify a binary as being either malicious or benign. And of course, in our generative adversarial network model, it's not to classify the binary. But again, it's important to remember that it is to classify the binary representation, which is our feature vector. So what this black box is going to do is it's really going to try to understand if the feature vector or the adversarially generated feature vector is part of the benign feature vector set or if it's part of the malware feature vector set. And the way we do this is we train it with the most commonly known machine learning algorithms used by industry AV engines. And these are decision trees, logistic regressions, multi-layer perceptrons, random forests, and SVMs. So that's really what the black box is. Now let's go back and let's try to see how this fits into our implementation of GANs. Next slide. Okay. Now, if you look at this diagram, again, let's try to understand what's really happening here. So the first step for us in the process of running GAN is, again, to train our discriminator, but also our black box detector with the benign feature vector and the malware feature vector to classify between the two. And once that training is done, we then feed in the malware feature vector to start mutating through the generator. So we feed in the malware feature vector, again, concatenated with noise. And again, it's very important to remember this is just to improve the randomization of the generator and produce more optimal or produce more effective adversarial feature vectors. Once the feature vector is generated by the generator, it then goes and gets classified by the discriminator and the black box detector. And again, if the discriminator classifies it as being a fake, or in this case, a malware feature vector, then it provides feedback to the generator, which the generator then uses to, again, retune its neural network and produce a more effective adversarial feature vector, which is capable of fooling the discriminator. So until here, everything sounds exactly the same as what we covered earlier. So what's different? The first question that pops up is, if the black box detector is doing the exact same thing as a discriminator, why do we have, or why are we implementing a black box in this design? Additionally, a follow-up question could be, so if we are using a black box detector for whatever reason, then what's the purpose of having the discriminator? Why not just have one of them? The answer to this lies in the nature of the problem that we're solving. Unlike the deepfake case or a lot of the other use cases that we covered in the prior section, right now we are dealing with a problem use case of binary classification, which means at the end of the day, what we're looking at is whether the adversarial feature vector is classified as benign or malicious, and that is really it. When it comes to such problem use cases, the black box detector is a lot more effective in conducting that binary classification than our discriminator. So the purpose of having the black box detector here is to really aid the discriminator in coming to that conclusion of whether the adversarial feature vector belongs to the benign feature vector set or the malware feature vector set. So that explains why we have a black box detector. But the follow-up question would then be, why do we have a discriminator then if we are getting the output from the black box detector? And the answer to that is the black box detector's strength, which is its effectiveness in producing a classification output of 1 or 0, is the problem that it creates in training a GAN. A binary output like 1 or 0 is not sufficient information or sufficient feedback for the generator to retune its parameters. So, and this is why we still need a discriminator. Now, unlike the black box detector, a discriminator gives back a weighted output. So, and this weight output is crucial for the generator to understand how and where to really retune its parameters in order to improve the accuracy of the adversarial feature vector. So I hope that explains how the generative adversarial network works. Again, once the GAN works, the final output is going to be the most optimal adversarial feature vector, which is capable of fooling both the discriminator and the black box detector into believing that it is part of the benign feature vector set.
Great. So now that we understand how we trained our generative adversarial network and how we trained the reinforcement learning agent, the next step was to test it, whether it worked or not. And the way that the testing works, it's very similar, right? What we do is that we take a malicious file, we pass it to the generative adversarial network, and what we get is basically a adversarial feature vector for both inputs and sections, right? That would make that exact malicious file look more benign. We pass it as one of the actions in the modifier in reinforcement learning agent. And then we have our neural network trained that's going to tell us for this malicious file, these are the different actions that you can perform or that we can perform to modify the malicious file to make it look more benign. So what it would tell us, it's either add random bytes. So we'll add the random bytes, and then it will tell us, okay, now pack, and then we'll pack. It might tell us again to unpack because we can't go into the neural network and see how exactly it's working into the hidden nodes and the weights. So what it will tell us, okay, add a signature, add a debug flag, remove a debug flag. And then at some point, it's going to tell us to, again, randomly add inputs. And this is where the list from the GAN is going to help us, right? So we are going to randomly add it, but the list from where we are randomly picking these inputs is coming out of GAN. So we know that the list works the best for that malicious file. We know that even if we just add 1 or 2, it's going to get our malicious file more closer to looking like a benign file. So that's how the testing worked, right? Now, this is basically a graph showing how it went. So when we started off this project, which was, I guess, I think July 2019, to the time when we actually were done with, or at least the first part of the project was done for the challenge. So when we started the project, the whole idea was to make it as evasive as possible, right? So if the score of the original malicious file was 60 in VirusTotal, we want to bring it down to, let's say, 5 or 4. That was our expectation of how this all would work. And it did work, honestly. We were able to bring down the score from 60 to, let's say, 10, or even better, 5. And we were all happy and we were celebrating and it all was great. Until we actually tried running the malware in a sandbox environment. And we realized that the malware is no more functional. It's not working. And what's the point of getting the evasiveness if it's not even functional? So then we started our second step of the journey, which was to bring back the functionality of the malware. This included, so first mistake that we realized was that the imports and the imports that we were working with in GAN and where the imports that we were training the GAN with also included the imports from a 64-bit machine. So we had to filter out the 32-bit DLLs and 32-bit imports. The second is to the sample, the malicious sample, the virus that we got from VirusTotal, the sample. The samples itself had 1 or 2 64-bit malicious files, right? And because of that, the training of both the reinforcement learning agent and the GAN wasn't up to the point. So we had to filter out the 32-bit binaries too. Third step, what we did was we switched from Python to C++. Now this whole project is based on Python. It's programmed using Python. And there has been research done on something very similar, right? How to use AI to mutate a malware. And all the research papers use this one library called Leaf in Python. And we went ahead with it too. And then we realized Leaf is what was breaking the functionality of the malware, right? When it was mutating it and trying to rebuild the binary, it wasn't able to do so properly. So we used C++ instead. So that's for maintaining the functionality. Now, for improving the performance, what we did is that we used a combination of machine learning models. So as Bedang talked about for his black box and GAN, instead of using just one, let's say, random forest algorithm as a classifier, we used multiple of them. Initially, the whole idea was to just scope it down to backdoors. So the project just worked on mutating backdoors. And if we tried mutating ransomware, it did work, but not that well. So we tried to train our models to learn how to mutate other diverse malware families too, right? On how to mutate a ransomware, how to mutate, let's say, Trojan, etc. And how did we test it? How did we know that the model right now that we have is the best that it could get? What we did is we actually compared it to mutating the file ourselves. So what we did is instead of using AI to mutate the file, what we did what the dog did in the beginning, right? We randomly selected actions, we randomly selected imports and sections, and we mutate the file with that. And we checked the score against VirusTotal to see what's the score we are getting. And as soon as the AI score was better than that of the human, we knew that the AI has potentially reached its point, right? Is potentially a better solution right now. It can get better, but that was our first step to reach there where it performs better than a human being. That was for the testing. Now let's get into the project demo. So right now what we have is Pisidius is a console program, right? So what you do is just run Pisidius with a malware file that you want to mutate. In this case, it could be a backdoor or right now a ransomware. So let's see what it would do. Oops. Right. So we run our Python application against a malicious file. And it would basically start querying the neural network for GAN and then the reinforcement learning agent to see what actions to perform. So we can see that it's the neural network for RL agent is performing different action. It's trying to pack. It's again trying to pack, which in this case, it would fail. If it's already packed, we are just using one packer, which is the UPX packer, right? So it's already packed. It's not going to pack again. It's going to append random bytes. And you can see if it's going to try adding a section, the section name comes from a list that has been compiled by the GAN. Same goes for the inputs. This is great, right? Now we got the mutated malware. What's the next step to know if it's working or not? So what we did is we took this mutated malware and we actually ran it in a cloud-based sandbox environment, which is any.run. So if you want to try it out, what you can do is just go to these links and you can see the functionality of the original malware that we used with Basidius and the functionality of the mutated malware. And you'll see that the functionality remained, right? It was 100% functional, the same functionalities. Let's have a look at that. So this is the original malware, right? So we can see what the original malware is trying to do is that it's trying to connect to a C2 server, right? The domain is Amazon, and these are the threats. Now this is the original malware. Let's go to the mutated malware. You can see that the hash is different, the MD5 hash. And we come here and we see the same functionality, right? So it's again trying to connect to a C2 server somewhere. If you want to look at the detailed report, you can go to the text report over here and you'll see how the process is started, the registry keys written, changed, or read are all the same. So everything is same about the malware except for the scores. So this is the score for the original file, which is the 66 AV engines detected. And this is the score of the mutated file, 37 out of, let's say, 67 engines detected. Again, it didn't go down to what our expectations were initially, which is 5 or 10, but it did go down by almost half, and the functionality was intact. Now, if you go to the details tab for the original and compare it to the details tab of the mutated malware, you'll see all the different imports and sections that we have added during the Basidius thing. So we can see that we have added random sections, we have renamed sections, and we have added a bunch of imports. And this was our demo. What is this it? Is this it for our project, or is there more coming? Yes, there is definitely more coming. First thing is we definitely still need to improve the evasiveness. So we want to go down from 66 to, let's say, try and go down to 20 or 15 if possible. At the same time, make sure that we maintain the functionality, right? We don't want to just improve the evasiveness and not have the malware function. There's no point for that. And what will we do, right? What will we do with all these mutated samples, right? We are from the blue side. We work for the defenders. So how will we use these samples for our benefit? What we can do is we can help the next generation antivirus systems to not only detect the original samples, but also be able to detect the mutated one. It's just like deepfake, right? If, let's say, if we see an image, we would want to know that if the image is a real one or is it a fake one. Same like that. The antivirus engines should be able to detect if the file is actually benign or is it just a malicious file looking like a benign file. And that is it. But before we jump into the Q&A, we are actually going to present the same tool in Black Hat Asia during the Arsenal. And we are hoping to make our demo more interactive with a lot more features and hopefully make it a GUI application. So please, and as it is virtual, please do make sure to come and attend that too. And that is it for the presentation, and it's time for a Q&A.
Okay, well, we've got 4 questions here. The first one is, what tools did you use to extract the features from the binaries?
So again, as we said, that the whole project is based on Python. there was a library called a PE file that helps us extract different information from the binary.
Okay. The other question was, second question, how big was your data set and are you releasing it?
Dataset for, dataset for the malicious file was, as we said, is from VirusTotal and VirusShare. And if you have a good reason, VirusTotal will be able to give you access to the same dataset. As for the benign file, I think Bedang would be able to explain that better.
Yeah, again, so while we were conducting this project, while we were building this project, we didn't really come across an online database that stores benign files. But like I mentioned during the talk, it's actually not that hard to get your hands on a collection or create your own database of benign files. All you really need to do is spin up a fresh VM of Windows 7, preferably 32-bit. We're still testing it out in 64, but whatever you're comfortable with, and you can get them for free from the Microsoft site itself, so it shouldn't be too big of a hassle. And then you can just run a script to kind of scrape through all the binaries that you find in that system. And that's what we did to create our own database of benign binaries. In terms of the size, I can comment on the size of the number of benign binaries. I think from our fresh install, we'd collected around 63,000, if I'm not mistaken. I think that's the number that pops to my head.
And as for the malicious files, so what we did is that, again, we requested VirusTotal, and because we had a good reason, which was the AI challenge, they did give access to their entire malicious file database. And they had the malicious file from, I think, 2016 to 2020. The only issue that we faced is that the malicious files weren't classified based on different malware families. So what we had to do is go through the malicious file, try to see what family it belongs to, and then filter it out based on which of these files are ransomware, which of these files are backdoors, and then train the machine learning models accordingly. And as for the size, I think the size was quite less when compared to benign files because we had to filter it based on ransomware and backdoor. So when it came to ransomware, I think it was around 15K. But what we did while training is that we actually trained with those 10,000 plus. Even if we needed more data, we even trained our neural network with the mutated files itself. So we double mutated, if that makes sense.
Okay, then the next question is, does it work the same on 64-bit?
Right now, Basidius is just for 32-bit applications. So no, it doesn't work with 64-bit, although that would be the future plan. And yeah, but it wouldn't be that hard. Once we have the parameters set right, once we have the hyperparameters for AI, for the different neural networks for both reinforcement learning and GAN, we should be able to use the same training and testing stage for 64-bit too. We just have to collect the data. But getting the data set for the malicious samples would be a little hard because as far as I know, VirusTotal only gave me access to the 32-bit one.
Clear. And then have you considered incorporating the Keeling framework or other analysis tools into your pipeline for feature extraction?
Sorry, could you repeat that, the last question?
Have you considered incorporating the Keeling framework or other analysis tools into your pipeline for feature extraction?
I'm not sure. So we haven't looked into anything else for feature extraction, but a very interesting point. I'm not sure if this relates in any sense to the question, but one of our to-dos for future work is to kind of replace the black box that we have with something like VirusTotal. So rather than relying on our own made machine learning algorithms to detect malicious from benign, we would rely directly on VirusTotal, which would be scoring that against a number of different AVs. And we're hoping that would improve the performance of our entire tool set.
And I think there are analysis tools that can also extract the features for us, but PFile does it pretty well. It's easy to use, and because it's Python based, we can automate the whole thing. So yeah, we went ahead with the PFile.
One of the questions that was asked fairly early on was, does the modification result in an unstable malware binary, or does the exploit functionality remain the same? I think you pretty much covered that in the talk. Don't know if you want to elaborate, but
it would depend on the number of modifications you're making too. So as I said early on, when our whole focus was on just make it as evasive as possible, the total number for the modifications made were up to like 160 or 200. And then we realized the more modifications we make, the lesser chance there are for the malicious file to remain functional. So after a lot of trial and error, we realized that the number 80 works the best. So after 80 modifications, after 80, we don't let the environment make any more modifications, no matter what's the score. If it's reached to the 80 threshold, it doesn't make any more modifications.
Thank you for that. And the last question I've got is, how much work would it be to add more file types, say Android malware or OS X?
Well, we'll need to understand the structure of the files. It would be like an entire different project, because we'll have to again create the data set from the very beginning. We'll have to train the machine learning models from the very beginning. But as I think if you understand the structure well, it should be fine. And we still would need support for extracting features. We would need support for the classifiers. While when it comes to PE32, there were already, for example, as I said, PE file that was already existing there to extract the features. There was another library called Leaf that I talked about, which was able to modify, even though was not able to keep the functionality intact. There was a library to play around with the PE32 files. But I'm not sure if there are similar support frameworks for the other types.
Yeah. Also, if I may add on to that, in my opinion, I can see one challenge rising up the others, and that comes in the feature extraction phase. Now, and this really stems from the fact how different PE files are from, let's say, ELF files in Linux, or Android files, or OS X files. And right now, our neural networks, both reinforcement learning as well as the generative adversarial networks, are built on the features that we have extracted, built around the structure of a PE file. So to have these feature vectors kind of incorporate all of them in the same model, that would make it very challenging for the neural network to really learn. And in my opinion, so it really depends. You can always fine tune it a lot more, but it would be a lot harder compared to having a single AI algorithm working, or AI model rather, working on these independent file types.
Okay, well, thanks guys. That is the full list of questions. We are a little bit over time, but hey, it's the last talk of the day, and it was a nice topic to end on anyway. So again, thank you very much for your talk. We will be back in like a minute to say our farewells. Dylan has a closing note. Please stick around for that.
Sure.
Thank you.
Right, and we have Dylan.
Guys, So ends another HITB lockdown edition. I really hope you guys enjoyed the talks and the labs that we put together for you for this time. Firstly, a big thank you to all our speakers, the lab trainers, the village chiefs, and of course to our tireless crew. These guys worked around the clock. We had a multi-channel stream this time around, so we actually had Cooper, the video overlord guy, in the Netherlands helping us to run track 2. And then in Asia, over in Singapore, we had Sriman, who courageously stepped up, agreed to be MC. And he didn't really realize that actually being MC means that you also have to be like at Cooper number 2, right? So the learning curve was super steep. So really, really a big thank you to these guys for taking their time out of their weekend to run this lockdown live stream for you guys. So I really appreciate that. As always, the slides, the materials, white papers, if there are white papers, will be released on the HITB website. You can find a link to it on the lockdown webpage. We'll put a link at the top. Individual videos of each talk, we'll probably post it in about a week, maybe 10 days or so. It really depends on whether Cooper's feeling up to editing them. But in the meantime, if you go to the YouTube channel, you'll find that there's day 1 and day 2 stream complete. The only thing is that you have to kind of like scroll through it as you want to find which talk you want to listen to. But stay connected to our Twitter, and we'll announce like when the individual talk links are out as well. We'll probably tag the speakers, so you probably notice that they'll also tweet it out as well. One of the things that we would like to ask you guys, right, is if you have suggestions on ways that we can kind of like improve the experience of attending a virtual conference like this, please let us know, like email us and let us know, because, at the end of the day, we're doing this stuff where we like doing it and we enjoy it, but, it's for you guys, right? So just let us know, what you think we might possibly do to kind of make this whole online stay at home virtual conference, more fun, more interactive. As hackers, we always like trying new things. So what's next for the rest of this year? Well, firstly, we're planning on actually adding in a few more virtual trainings. We'll kind of curate the subjects and the trainers, the ones that we think are cool and awesome, or the subjects that we think that, you guys would be interested in. Similarly, if you guys have trainings that you would like to attend, right? You're stuck at home or working from home, maybe you might want to upskill. Let us know if there's a particular course or a particular dude that you would have loved to go for his training, but time constraints last time, maybe you couldn't go for it. We will help to try and see whether we can facilitate that. Just email us. Yeah, let us know about that. At the end of that, we're also going to be actually doing these trainings in different time zones, right? Because of it's remote. Most of you guys probably are in the States or in Europe. So we try and maybe do it in multiple time zones. So we might have like 2 different trainers teaching similar subjects, but one in the US time zone, one in the Europe time zone. If you think of ways that we can make that more feasible for you guys so that, it's more better value, email us, let us know. What else? Oh yeah, so okay, Cyber Week. Yes, of course. Needless to say, there's no in-person conference, unfortunately. The whole COVID thing is still too unpredictable. I mean, while it's July, the Cyber Week event is still going to happen. It's just going to be online. The dates remain the same. So November 15th to the 19th is what we originally planned for. And we're going to stick with that. But because it's mainly online, there's certain elements that probably won't translate, right? Like, so the whole big exhibition part, maybe not. But we're still going to have most of the components that we had last year, that we introduced last year. So, for example, like Cyber Battle of the Emirates, which is like an EDU CTF for students. We won't have a cyber battle as in on the scale that we did last year, mainly because we can't. But we are working on trying to do an EDU-focused CTF for you guys, and we'll hopefully have some information to share about that. About Pro CTF. Last year, as you guys knew, we flew in like the best hacking teams from around the world, and then you guys competed for like a 100K prize. We're probably not going to have a Pro CTF either, but we will merge with the standoff. So if you were at Cyber Week last year, or maybe you saw photos of it or saw some videos, The standoff was kind of like a city model that was actually hosted where you could kind of interact with the components, so real life components, SCADA components, real life systems, and you would hack it basically. So you had a red team and a blue team. It's like an attack and defense kind of a CTF, but modeled after the real world. So basically, we're in talks with the guys from PhDs who actually run the standoff, and we're trying to see whether we could make this more of like a fully like global standoff, right? So that it goes across more days. So Cyber Week runs 15th and 19th. Maybe we'll start the CTF even earlier and maybe slightly later. Mainly is so that, teams are all around the world, right? You guys, maybe there are teams in Russia, maybe there are teams in Asia, teams in US, and just doing a very short CTF over 2 days or 3 days, considering that, the time zones is not like fair really, because some guys have to stay up to ridiculous hours, some guys have to stay awake when the sun is out. We don't like that. So we'll have some news about the Pro CTF / global standoff, hopefully soon. The CFP, so call for papers for Cyber Week. We'll probably open it around the end of August. We're also actually looking for more labs, right? So more hands-on sessions. This year or this time that we did the Singapore, Lockdown 002, we had like an SDR lab, we had like, the chilling framework lab, we had, a car hacking lab. We also had Lenster from the States who did like an awesome hardware soldering lab. I was watching it and it's like super cool, super fun. So because Cyber Week has like a much wider audience, and also we're trying to inspire the next generation, to think like hackers, right? And like kind of the fact that hacking isn't about just breaking stuff and, exploitation and all of that good red teaming stuff, which I love personally, but that's not what hacking is, right? Like hacking is actually creative thinking. It's outside the box. It's kind of like inspiring you to be creative and to solve problems, because that's what hacking is, right? Solving problems, creative ways. So if you have something that you are passionate about, some lab or some kind of like project you're working on, hardware related, software related, whatever it might be, submit it, man. Like, email it over to us, submit it to the CFP. So for example, I'm actually considering to do a session, about like building a small RC self-driving car, using the Donkey Car project. If you've been to one of the Hack in the Box before, I'm like into AI and I do the Leapdog AI village thing. So maybe I might do that since I'm stuck at home anyway. I spent this lockdown this time playing a hallway track, playing some music. So, if you're working on something fun, doesn't have to be security related. It could just, as long as you're passionate about it, you think it's cool, send it over to us. Be reasonable. Obviously, if it's about cooking or something, maybe we won't add that in, but, just send in your proposals, guys. We're always looking forward to hearing from you guys. I guess that's it. You guys have a great week ahead. It's been fun as always. Really love doing these things for you guys and seeing all the comments on Discord and on Twitter. So thank you so much. As always, stay safe. Wear your mask. And we'll see you guys on the internet, man. Eat dog out, man. Ciao.
And that was Dylan. So, of course, I also have to say something. First of all, thanks every single one of you who decided to tune in and watch and partake and be on Discord and etc. We really appreciate every single one of you who decided to join. Very big thank you to Shriman, who decided to run the second track. I should actually say he was the first track, because I am running the second track. He came from just running the track as in at the live conferences, just being in charge of what's happening in the room, and all of a sudden he gets to deal with a video rig of mine complete with construction. Imagine that. He did great, so tip of the hat to him. Big thank you to Bray, to Kemeng, Ryan and Eka, who were dealing with social media and the Q&A on Slido. I believe they even managed some things within Discord. Big thank you to Max Salar for doing the website, Henry Limargo for doing all this beautiful artwork that was made. Massive thank you to the speakers, to our virtual lab trainers, to the Car Security Quarter. They had a CTF. It has ended. The winner of that was a Tactics Defense. Second place went to Goose CTF. Third place to 0 points, which clearly they didn't get. Another thank you is for Airglow. I used their music for the times in between. You can find them on Twitter at airglow_sounds. Thank you to Amy, Wang Liang, and Dylan. The Zenith Labs Crypto Challenge is still going on. It ends at midnight tonight, Singapore time. That means you have about an hour and what will it be? 40 minutes to partake in that should you want to. Keep an eye on the Twitter for Hack in the Box for the published slides, etc. The materials, everything will be found on the website. And I hope to see every single one of you next round with Hack in the Box for Cyber Week in November. Have a lovely evening and I hope to see you soon.
should go to another plan and servers